I am from IIT Kharagpur. I did my PhD from IIT Kharagpur. So now, in spite of that fact, Professor Tiwari and Professor Vishwas have come out of it and then organized this fantastic topic. And I hope that all of you would have nice talks as well as would communicate with each other, and we would definitely take this particular field progressive. As Professor Dr. Srivastava said, that not many people are publishing in this particular field, but this is the new beginning, I would say. And I would wish all the success to this conference. Thank you very much.
Professor Kishanu, your mic is mute. Now it's okay.
Yeah. So has Professor Mandal finished his talk?
Yes.
Okay. I think there was some disturbance because we started the YouTube channel. So it was a delay, maybe for a few seconds. Thank you, Professor Mandal, for your nice words. Okay, let it pass over. Okay, so I request all of you to mute, please, because this disturbance will come otherwise. So can I now request Professor Karavi Das from IIT Kharagpur to speak few words about the conference? Yeah, all of you please mute.
And then you save, that tells you the local strain at every point, right? So you use a beam that's focused down to about a nanometer in size, or maybe a little smaller than that, and you just measure the shift of the peak, the diffraction spots. We have a paper by Elliot Paget. It's called Exit Wave Power Kepstrom. It's a very useful trick of how to process this data quickly and efficiently, and in a way that minimizes tilt and diffraction artifacts. If you don't, the alternative of that is you'd be forced to do a precession, which badly degrades your spatial resolution.
Okay, one more question is that how accurately one can determine the dose and how it is done dynamically?
Yeah, so the nice thing about the 4D stem detector is you've basically collected every electron that went through the sample. And it's quantitative. So you've just integrated up the signal on the 4D stem detector. That ought to look like your incident beam current. And that's probably the most accurate calibration you've got. What we used to do is, before, we would use the spectrometer as a Faraday cup and deflect the beam onto the side of the drift tube and read the current off the drift tube. That's not something you can do during an experiment. But with the 4D stem detector, because you don't saturate your central beam and you can collect out to very large scattering angles, basically just integrating up the counts on the detector is the total incident. Because if you go off the edge of a sample, you can see what those numbers are like, and they might vary by maybe 1% or so.
Okay, there are a few more questions, but I think they may send you by an email, and if you feel like you, whenever you can give the answers. So now,
Yeah, I
because the
see.
time,
I see one quick question, which was, how do we measure the magnetic fields of magnetic
yes,
imaging? And I just think I should quickly address that one.
yes, please.
And the answer to that one is the first thing you have to do for magnetic imaging is you have to turn off the objective lens to get rid of the field. And then you can use the magnetic main lens to use as an external B field. So one of the things we had to do is we actually had to build a Hall probe that we could mount in the sample holder. So we actually did that, a relatively simple design. And then we used the Hall probe to calibrate the main lens and the mini lens to figure out at what point that actually hit exactly zero field. And that calibration is very robust for a particular microscope. So once we'd done that calibration, we knew by turning off the objective lens where zero field was. And we used the condenser lenses as our focusing lens. And that's why tychography is so important, because you start out with very low spatial resolution, and the tychography gives you a resolution improvement. So I think now we're probably out of time, is my guess. So thank you.
We should, on behalf of our committee, organizing committee, let me thank you for giving your valuable time, and particularly almost at the midnight. So thank you very much.
Thank you. And maybe the rest of the questions by email.
Yes. You can stop sharing your window now.
Yes. There we go.
Thank you.
Thank you.
So now we shall move to the next speaker. It is Dr. Partha Ghoshal from Defense Metallurgical Research Lab. He is the head of electron microscopy at DMRL, Hyderabad, and it is a well-known figure in our community in Electron Microscopy Society. He doesn't require any introduction for that. And basically, he did very Herculean task by conducting APMC 2020 at Hyderabad. And today he's going to talk about the phase and microstructural characterization using advanced techniques like in-situ SEM and TMPD. Dr. Ghoshal, over to you.
Hello.
Hi.
Yeah.
Yes, Partha.
Yes, he's here. He's here now.
He is probably not mute. Unmute your mic.
Dr. Ghoshal, please unmute your mouth.
Yeah, I've done that. You able to hear me?
Yes, yes, yes.
Okay, you able to hear me. So I'll share my screen first.
Yeah.
David's window is still on. David can actually stop sharing.
He did that.
David,
now I can see on him. Yes, yes.
You have to see my screen?
Not yet. I just see the name there. Your name is not the screen.
Yeah, please share your screen.
Okay, sure. Now I think you'll be able to see that.
Yeah.
Yes, yes, yes.
Okay.
Yes,
okay.
You can go to the full view and then start.
Good morning to you all. So at the outset, let me thank the organizing committee, particularly Kisanu and Chandrasekhar, for giving us the opportunity to come to this forum after a long time, because the EMSI particularly has the last event in 2020, and you know that after that we have a very devastating time, and it's very fortunate that things has now a little bit under control in almost all the countries. I must say it is not fully controlled, but trying to be under control. And it's a better time that we actually nurture our intellectual habits to discuss and have seminars and talk about and listen to others. So I must say it's a very good initiative, and I thank for giving us the opportunity to share our part of research with you. So today I'll be talking of the phase and microstructural characterization using advanced techniques. Basically, I'll be telling that how we do different types of TEM and how ACMs, basically in situ ACMs, and in TEM, what are the advanced techniques like PED, which is electron diffraction. So I'll be sharing some of the results. Not only I'll be sharing about the technique. There are two parts of it. One is to tell about the technique, and the other part is to tell that how these techniques are used for real life problem. So I'm going to show you an example that how the real life problem is solved using these techniques, advanced techniques. It's not only that we are going to present some only results. So I must acknowledge in the beginning that these results are not only a research by myself, my team, those who are my few of my team members like Rajdeep, Bajinder, Deepak, Suraj. They are part of the research, and I acknowledge them. Although I am presenting the results. So very quickly, I just want to tell you that, as you know, DMR is expertise in doing for different types of alloy development, for for structural alloy development, for high temperature applications. For all doing this, the main part of it, one of the main part of it out of the 4 arms is microstructural analysis. You also along with analytical characterization. So microstructural analytical characterization is a part of any alloy development program. And that's why we are, as you know, that the many people also worked here to develop new alloy. One of them is Dr. Banerjee has worked on orthorhombic alloys, the new invention from the laboratory. Like that, there are various alloys development programs take place, and we cater to them with advanced techniques. Now we are coming out advanced instruments and advanced technique and how to understand. So I am going to explain to you that our real life problem, how to understand them. So I'll be explaining out the 3 techniques basically initially, because I can see the property of the material. Then one of the research is gamma titanium aluminum alloy. How to find out the different phases, various finding, how the small distribution. So these things I'm going to touch upon. Yes.
Dr. Partha, actually, I think your screen is not moving. Can you go to the full screen mode?
Yeah, I'm in the full screen mode only.
No, it is not showing. It is showing the normal mode. So probably we need to redo that because it's the first page which is stuck there. Now it is showing the dual beam.
Able to see now?
No, Partho, I think you are basically sharing your PPT screen, not the slideshow. The slideshow has to be separately selected, I guess. So we can see your PPT in the actual PowerPoint application. It's not in the slideshow. So the share should be changed.
You able to see now?
No, not really. The full screen.
Okay, once more I will share.
Please.
Partha, actually put F5 or something, it goes to full screen, or the icon at the bottom.
No, I
you able
guess,
to see full screen now?
No, I guess you are sharing the wrong app, you know. When you go to share mode, you will see the slide as well as the PowerPoint. Otherwise, you have to share your entire display. Either way. You are sharing a specific app. That's the problem.
Oh, okay, I'm able to see the full screen when I am presenting from my end.
Please use Alt Tab and then go to the other one. That's the problem. I think come out of the full screen and the sharing you do. After doing the F5, you please try to share.
So now you're able to see? Now?
No, boss, no. There is a sharing issue. So there is one way, you have to go to full screen and then use Alt Tab to basically go to your sharing mode and then share this. Alternately, share all screens.
I've done all screens here.
No,
you able to see now?
Do F5. Now do F5.
You able to see now the full screen? No.
No. Otherwise, in the view, no, reduce the size of these sidebars.
Okay, yes, that I can do easily.
So that we
yes.
One, and also the ribbon. Get rid of the ribbon at the top.
Yes. So it's okay.
The ribbon is still there.
Yeah, I think it's okay now. We can proceed.
I think so. Okay, let's go ahead.
I want to see the full screen. Achha, this is like this preview. Okay, so view. This is full screen. This is the one, na?
Yes.
Full screen. To kya? This is not going.
Dr. Partha, I think it's okay. We can proceed because we lose time there.
I think, okay. So I'll just go ahead, maybe. Yeah,
it's fine. We can read it and it's okay.
Okay, Dr. Partha, please go ahead.
Okay. Right, I'll just go ahead. Okay, so I just go ahead. So basically, I'll be talking of. So as you know that the first I'll explain that why do we use, because you'll be using that because this is mainly few slides are there basically to address the young researchers. Basically, as you know that a dual beam system we use basically to actually have the name itself, because one is the electron beam and the ion beam, to basically mill out or to remove material. And to do that, so you can see a lot of examples. You can look at the two beams are there. Basically, we use the focused ion beam to remove materials like this one here, and then we use the electron gun to image them. So you can see, look at an IC device. We can remove one part of it, and you can see number of layers which is into it, and like that. These techniques, how we'll use it, I'll show you later on. So basically, I've given some of the examples to see, and what do we do? Basically, we use this machine to take out sample from a specific region. That is the most important part of it. And this is an example given, like you can see, you can mark an area, and then this we can remove both the sides. You can look at it, and slowly thin lamella is left out.
Partha, I'm sorry, these slides are not moving here. I just see the slide where DMRL has over years developed a high degree of expertise. That is the slide which is being displayed. Now TM.
I don't know why. So it will be slow.
Now, yeah, it will be a bit slow. Now it is showing TM sample preparation using dual beam SEMs.
Yes.
That slide is not. It is 8 number slide.
Yes. This slide I am speaking of. So it is not moving at the other end.
Now you are at the TM sample preparation side. It was not moving in between.
Okay.
Please go ahead.
Okay. So basically, you can see how the thin foils are actually removed. So we use the different types of. One is called Omni probe here. This is a probe. It's like a forceps. So we basically we weld this pond region and we remove this sample. So this particular technique, and then you put into. So I'll come to the actual examples, and I just want to explain to you. This is how we can remove from a specific region using FIB. There will be different samples, and you can start actually putting them in the TM grid and put the whole thing in the TM. You able to see the screen moving now? Raghavendra, the screen is moving.
Yes. Please go ahead.
Okay.
Now it is showing EBSD.
Okay. Yes. Sorry. So now I'll be touching upon tell you that how to do EBSD. Basically, EBSD is a general technique now. It's more common for last 20 years. It's been a very hot machine because a lot of information can be collected. As you know, it is attached to an SEM. Basically, it is a attachment to SEM. And what do you get it? How do you get it? Because as you know, the sample has to be tilted to 70 degree to get Kikuchi bands like this. These are the signature information of any crystallographic information of any material. So these particular informations are online matched. These are called Kikuchi lines, Kikuchi diffraction pattern, and these Kikuchi bands are online and matched with the database of the computer to find out that what is the orientation mainly. First comes the orientation, then so many other parameters from this information we can find out. As this is signature information, that means this for all different materials, this information is different for different materials. So one of them is the orientation. The other is you can find out the phases, you can find out the strains, you can find out the grain size, you can find out various other parameters. So basically, as you know, that any material, basically, if you look at the grains, they are initially randomly oriented, and you can see this is a random picture orientation, all are carrying different colors. So these colors are actually international standard colors which are given for this sort of full figure map. For this thing, as you know, this third means 001 and 010 is the green and blue, and this is a combination. So you can look at this map and you can see it's a random oriented. Similarly, for actual alloy, once you orient it, once there is a grain morphology, if you look into it. If you look at these are the grain studies we can do, and if you look at it, that if you want to look at the phase values, like how the phase also distributed, you can look at this as a structure, and this is how the phase distribution. Two different colors represent two different phases for an experimental alloy, which is happening. So you can look at the grain orientation. So now each from one end to other end, you can see this side grains are elongated, whereas these grains are actually having equiax structures. So similarly, for different types of alloy, like TI3L based orientation have been imaged here. Then the gamma orientation based imaged here. So this sort of informations can be easily acquainted as far as the magnification. If it is within say 30, 40, 50,000, that means the big gains are quite big enough. That means although it's in the size of sub-micron or in the nano form, but not beyond around 20 nano, not below 20 nano. So as far as these studies are concerned, this is a routine thing now. So basically we can find out, this is the example, that how do the orientations, how it changes once you go different sorts of heat treatments, and you do a different rolling, processing, how the grain structure changes. Basically what we do also in the TM, so this is what the techniques which we'll be using to do the analysis. Basically, you know that why to go do TM, basically the sizes are of nano, that means the small size phases, precipitates, we need to do that. You can look at, they are all different sizes, like say 200 nano to 50 nanometer particles, they'll all start seeing very clearly in the TM. So look at the image of this sort of particle, which is a tungsten thing, and this sort of images are basically to tell you that these are high resolution images. That means these lines will tell you that they are the interatomic planes. So they are the signature of any material. So we can go in this direction. But what happens? What information is not available in this particular conventional methods? We'll try to investigate and try to say that how we can find out in situ techniques, how we can get the different sort of information. So I'm just coming back to this thing, just to tell you that what TM can do. Even you can, this is the image of a carbon nanotubes, as you know, and you can keep on magnifying to see the walls, boards and walls. You can see these nanotubes, basically each one of them you take and start magnifying up to 10 lakhs, you start seeing the walls and boards. This is like you can count the walls, even this is the number of walls. So this way you can find out the structures. And here if you go in the tip of it, like this, each tip is having a crown, each nanotube is having a crown. If you want to know about the crown, you have to go to the high resolution mode to find out this particular crown. What is that? This is magnified to see each crown is having a nano iron oxide. That means you can find out the iron is sitting at the top as a crown. So this sort of investigation, sometimes this is, if it's much bigger, you can start looking at an ADS attached to it or an yields attached to it to find out and to distinguish between the different types of carbon. You have to use and yields in the attached to microscope to find out how they're different from the carbon grids and the carbon nanotubes. So all different characterization is possible and the standard things to do that. What we investigate is that what using this conventional techniques and the machines, what you start doing is that the advanced, because you know that as our understanding and the arts for understanding and knowledge is not basically fixed. So basically we keep on try to understand much better. So one of the technique is to do inside the microscope. If you want to look at it, there is something called in situ mechanical property evaluation. You can have a probe which is inside the microscope. It will go. I just show you that as you know that this will go here along with that, and we have the attachments to come to the details of the in-situ. This is the tip of it where you load your samples, and what you do. So basically you have to do a lot of in-situ studies in the SEM to find out that how to take one single, suppose nanofiber or a nanotube. So this single tip, each one is been loaded. It's a technique, and it takes a huge amount of time and expertise to load one particular, suppose, carbon nanotube. The difficulty as on date for the in-situ studies is one of the difficulties that the measuring tool itself, like the indenter or the sensor, is still not up to the mark till as far as the machine is concerned. So the sensitivity, the measurement part of it is still not developed, is developing. So we also collaborate with the instrument manufacturers to tell about what is the type of instrument, like each single carbon nanotube also we want to find it out. So basically if you look at it, the results are not that consistent in carbon nanotubes. So we have given an example of carbon nanocoil or a nanofiber. If you look at it, see, I think you can see the video also. I think the video is working. So basically this is the indenter, and this indenter keeps on actually pressing. So I don't know if this video is working. No, it's not working in this mode. So you can get a test and curve. Basically I can find out first find out the elastic modulus of each individual carbon nanocoil or the fiber. So this is estimated, and it is calculated again and again for number of samples. It is coming around, say, 180 GPa. So this sort of values for each individual thing is very, very important once you want to use them, basically. So I think the video is not working in this mode. You have to see the video? No, not now. So basically these are the loading and unloading curves, and you can see how this is this fracture of a fiber has been taken with a indenter.
Partha, this indenter will not work in this thing. Your video will not work in this mode.
Oh, actually, video will not work in this mode?
In this mode, yes.
Why? Okay.
The source is not added in the same folder, so the video will not work. It's not.
No, it is in the same folder. Okay. It's in the same folder that I've done that.
Mode.
Only in the presentation mode only it works.
Right.
I know that, but still it is not working. I don't know why. Okay, we'll go ahead. We'll not do most of the time. So I'll just tell you that okay, how to use those things. I just come back in the real life. So I'm just telling you one more in-situ testing. What we do is inside the SEM. That is, we do actually inside the machines. We can also do and in-situ heating and in-situ cooling. So I'll just show you some of the examples. But anyway, if video doesn't work, it will not be encouraging to show. But we have an heating arrangement up to 1000 degrees centigrade. We can go and these arrangements we can actually load a samples in that, and you can study this is a sample enlarged view. You can look at the sample is loaded, and this is a ceramic heating arrangements here. And if once you start heating, I'll just show you the examples. Like see, you can study now inside the machines how the heating and the cooling cycle takes place. So one of the established aluminum alloy which is used for structural application, you can see that how we can arrive at a stable structure instead of the conventional structure of heating for 5 hours. We can just heat very fast and just you can cool down, we can attain the same structure. So this sort of information and the research is going to be very, very encouraging for industries also. Anyway, these are also videos. I don't know, this also not work, as in some problem with the PPT and the presentation. So it will not be very encouraging to see these videos once it doesn't work. So this is also
just a second. Again, this is stopped. I can see only that image where you are showing the deformation of the carbon nanotube. So this is
again it is stopped, huh?
This is on the slide 32. This is slide 32 on display.
Able to see now? It has moved. I think it's slow, huh?
No, it's not moved. Yes, now it is moving.
Okay. Able to see now?
I can see the 2 images, SCM images.
Yes. Okay.
Yes. Okay. Go ahead, please.
Okay. So in this particular attachments, what we do, we can also find out different types of materials. Like you can look at it, the video is not working. So if you look at an ohmic contacts, that is, if you look at from room temperature, if you slowly heat, how you are able to get the distribution of the other phase, how these are on a gallium arsenide, on a device structure. So you can see how from room temperature, how slowly, at what temperature you start getting the ohmic contacts. So this sort of information, it was earlier not possible. In the same machines, we can also do and EPSD, what I told you earlier, and also heating. So you can look at the grain structure. For say this red color, suppose grain. I think the slides are moving.
Yes. Please go ahead.
Okay. So this grains, how this is growing. So this much grain with the orientation. So grain enlargement or recrystallization along with the temperature is also seen in this method. So basically, what is not possible in the machine, which is just started off, is actually something called orientation imaging in TEM, which is by electron and diffraction. What we attach is a camera here in this place of the binocular. Just below that, there is a camera attachments, and which is and a hardware part of it to control the lenses in the condenser area. We condense the lenses to actually rock the beam, and also the software. So we can do we use variety of materials. We can studies to find out even the TM level. Once you start going up to 5 lakhs magnification, then you start looking at the sizes, the very small size grains, which are not possible to see in EBSD. Okay, so those we can start getting all information what you used to get in EBSD. So that is possible. So look at the example, which is from a nanomegas, which has given us the instrument part of it. So you can look at it that this particular image, which you observed earlier. Now, suppose this only region you want to. So this information you can look at the image that in this particular region, SEM cannot give you more information beyond the image what is given here. So if you look at that, you would take this area and start imaging in the TEM. You can look at this image is now having this sort of information. So I'll tell you how these things are coming. I'll slowly come to it. So basically, it's a method. Is unlike an EBSD where the Kikuchi bands are used. What we do here is a selected area diffraction, and we basically each point, and we can actually these steps you can change and vary and put according to the user's requirements. So each point you take a diffraction pattern. It's a selected area diffraction pattern. And also one more technique is there. It is that we will tell you the precision electron diffraction. We will do the precision. I will explain to you. We will do the precision to get the exact zone axis or to excite more number of planes so that you can start getting more number of spots. So these two combined together, and we start actually comparing this with the standard database. So this is the standard database which is then stored in the machine as a software. So these particular things we can and we can do calculation using the structure factor calculation. We can give the lattice parameter, cell parameter A, B, C, alpha, beta, gamma, and start doing the structure factor calculation. And what we can do is that we can find out the unknown phases, the crystal structure of the phase, everything you can find out in this method, in this nanoscale. So this particular matching of this is experimental, this is a theoretical one. This particular matching has been done, and you start getting investigating. So basically, and it is very quite fast actually. So you can get from the very small grains to large grains, all of them you can start getting. These are the nanoparticles. You can get the orientation of the nanoparticles. You can look at that these are nanoparticles, because now in this particular attachment you can get the orientation of the nanoparticles also. So with these techniques in the card, so this is the precision. So I think in the precision, like a walking curve, we actually do the precision here, and we can start getting this sort of pattern. So you can look at it, and the precision also has got an actually animated view. You can look at it. You able to see, Tiwari?
This is not able to. No, you can't see the motion. You just see the still pictures. We can see the precision file, but
okay, you can see the precision. Okay, so it was earlier. It was like this precision. So you once you do the walking curve here, if you rotate the beam here along the vertex axis, you start getting the image, and you can start excite all the planes. So this is an not precise, not precision diffraction pattern. This is the after precision. So this sort of images we can change the angle of the precision. We can look at it and to have the maximum number of planes excited. So with this, what happens? You get more number of planes excited. You get much more accurate data to do analysis. So basically, you can look at it that once you can get the phase maps, you can get the orientation maps in this particular magnification. So basically, now I'm come to the case study. So I'll tell you how the actual real life pictures, our real life solutions of material investigations uses these methods basically. So this is one such case.
It is stopped again, Partha.
Oh,
yes.
sorry. Yes.
Case study. Yes. Thank you.
It has come, na case study. It has come. Yeah. So basically, I'll take a example of a aero engine blade. If you look at it, as you know that these blades are actually, we fabricate them, we actually manufacture them. The technology lies with us. These are aero engine blades basically, and they are of nickel-based superalloy. And these blades are very important to have. That where if it fails, how do you know them? So this is actually fitted in engine. You look at it now. If you look at the engine, one blade, I'll just take it out and say that each blade, as you know, that once it requires different types of temperature, different types of atmosphere. It sees very hot atmosphere, very at different oxygen levels. So it requires different types of coating. As you know that any blades have got so much of to see the temperature difference, to reduce the temperature difference as the blades work almost towards its melting point. So different types of coatings are given, ceramic coating, then ATS stabilized zirconium coating, so and to see the hot gases. So these coatings are sometimes difficult to understand when it doesn't work. So sometimes, suppose this is a failed component, I just tell you. So you need to understand why it has failed, what thing it has formed, what formation has failed this component. So basically, when we find out from the component directly, we find out a small area, and from the component level, we start actually taking out samples like this, and then whatever I discussed, these components are big components. So basically, the area of interest is, suppose where this start failing, this is the crack area. So we are interested in very small area of around say 20 micron. Then from this region, we started doing an average analysis using an EDS. So what are the elements and phases present? But then we go to actually an FIB, focused ion beam. And in the focused ion beam, as I told you, we remove the material from both the sides and start taking out. So these samples are now using ONI probe are removed and started using we are putting them in the TM holder. So in this TM holder, we actually put them and start investing in the TM, and we find out that this is a tungsten-rich carbide, which has a structure of around M63, that is metal carbide, and they are mainly decorating the grain boundary. And this information is possible only once you take a sample only from that region and go up to TM level. So this information is not very this thing. We are able to find out a gross analysis that what type of carbon, what is the phase. Suppose you want to, you're interested to know what actual composition is formed. So we go for what I told you, the technique called persistent electron diffraction. After precision on, we collect a set of informations, a set of diffraction patterns from all different zone axes after orienting and changing the tilting the samples, and we do online analysis. And these are the steps to do that. I'm not going to details because the time is taken for all the adjustments. And so now we are trying to identify the cell parameters. So basically, you can find out, you can put the parameters and start doing what is the best match basically, and we're trying to attain what is the best match with the diffraction pattern. And we are able to find out that this particular is M23C6. So this sort of information, which we have arrived at, is not possible by any other conventional techniques. This is an in-situ, by doing an in-situ removing material, by selecting it, we remove them and putting a TM and doing a precision. So all these techniques are used to come to a conclusion like this. So I'll tell you an example of this coating material, what happens in the same coating. See, sometimes there are different, as you go from one end to the other end, you can look at it, there are different sizes of the grains happen. Some of them are columnar grains, some of the very fine grains, some of the big grains. So these grains, once you are not able to see in the ABSD to say the grain orientations, all those things, if you want to look at it, and you can look at this. This is an ABSD map which shows that this is the grain size distribution and this is the sizes. So these sizes are not enough to understand. So look at this. So this information is not at all having very high resolution. So this information, so we need to go in a small area. We need to now do the similar exercise like selecting an area, removing it using an FIB, use extensively, and start doing, and inside the TM you start doing and orientation imaging machine, and you start finding out that there are very fine grain structures. We can look at it, this fine grains, you can look at the fine grain structure. These are not possible any other technique. So this fine grain structure, we are able to find out that now the grains have recrystallized, and at what temperature it has formed, what grains it has formed, what is the phase values. This is all possible to find out even if there are minute in sizes. And they play a very important role in the whole alloy development and the coating behavior. I'll tell you one more example, which is a very recent alloy development program. It's a gamma alloy. In this gamma alloy, as you know, this is very interesting alloy. You know, I'm not going to details of why the alloy is important, but it is very important to know that once we do to find out the mechanical property, one of them is the creep values, what property and what structure changes and what level. It is very important to do. We will tell you, those who are actually in the material science, they will know that very small quantities of the carbide or the phases play a very important role. Like in the steel, a very small quantity of carbon, of carbide and the carbon plays a very important role. The whole structure, the whole chemistry, the whole phases, everything changes. Similarly, for the titanium alloy, the very small phases, distribution, precipitates play a very important role. So basically, you can look at it that any ABSD, if you start doing that, there are very, very fine phases distribution in this particular alloy. So these phases were not in a position to be analyzed and understand, but to understand it is there. So we start doing actually the OIM inside the TM to find out how the different what are the finer details of it, and you can find out that these finer details using this thing, which are not possible to use thing, we are able to find out they are having a different labs and how the phase distribution is different. So these orientations, orientation images, which are obtained using ABSD, and beyond that, see these areas, these small areas and now has been done using an PED to see the detailed structure analysis. So in this sort of structural analysis, earlier we have never done. We have done work on gamma titanium alloy, and we have not gone to analysis on the phases and the strains, and this possibility was not earlier, cannot be explored, even if you know it is there. So this sort of details analysis is possible only using the PED techniques with the automated orientation mapping. So I'll not go to the details of these things, and I'll just show you that different what beyond EBSD. Once you want to resolve them, the lathes which is not possible using EBSD, you can start resolve them using the PED. So PED can resolve the small size lattices and the phases very distinctly, and what is the symmetry of them, what is the stain map, everything is possible. What EBSD is to do, and now it is possible inside the TM. So basically, I was not going to details of this thing. The time is past. So I'll just say that in this investigation, these three types of investigation, how we used SEM, EBSD, and then along with the TEM, along with the in-situ techniques, and how to use the precision electron diffraction and the automatic crystallization method along with the FIB to find out this investigation for three different types of cases. Basically, so I'm just want to conclude by saying that we like to thank Dr. Kamath, who is our Director General, and Dr. Mohsen Reddy, who is the Director of DML, to encourage this sort of advanced research and advanced techniques. And this is my lab. This is my van. This is a new center which has been established, and which is called Advanced Material Characterization Center. So thank you very much, and I hope I am able to convey that how to analyze our material, how to do our case studies using different advanced techniques. Thank you very much.
Thank you, Dr. Partha. See, any question is there? Dr. Partha, I just had one question. This carbide, which you found out after taking the lift out, does it bear any orientation relationship, or it is a completely incoherent phase?
This is in which carbide?
It is in the failure analysis.
Okay. Yes. There with the phase, it is a coherent thing.
It was coherent.
They are in phase.
Because it was sitting at the grain boundary. That's what you said. And was it the reason for? Was this precipitate was the reason for the failure?
Yes, you're right. That is the reason for the failure, because as you know that anything sitting in the grain boundary, that creates the problem for the grain to fail. It was supposed to be coherent, so the coherency is lost. The coherency is only when you find out that this particular carbide, that M70C66 carbides, they are not coherent. So because the coherency is not there, so they cannot hold the grain, so it will crack up.
Okay, so now there is...
So that leads to the failure. That's it.
Acha, one question is there. What is the range of precision angle you have used for collecting EBSD?
For collecting EBSD?
At least in one of them where you had a very fine distribution of precipitates. Means that boride and carbide you were showing. So very fine size were showing. I think that is why he is asking about the angle of precision.
Okay, the angle of precision.
I think the question pertains to PED part though.
Oh yes. Okay, the question part PED. PED around 3 to 5 degree. The 5 is the maximum. Around 3 degree.
Around 3 degree are taken. That's
yes.
Okay.
You need to optimize. Actually, you need to optimize that. Basically, you can go up to 5 degree, but what angle, what sample thickness, this matters. That it matters to give you, which will give you the better on-zone pattern.
Okay. So one more question has come up on the will there be any issue of oxidation of sample after FIB before it goes into TM?
if it can, suppose you have a steel, okay, it can. Okay, so you have to have one to one in the next door, or you can actually carry them inside. Yes, of course, you are right. In some samples where they are very much prone to oxygen, and because with the surface is very nascent, you are very right. So some samples should be very, very careful how to transport them from FIB to TM. You are right.
Okay, actually, the another see regarding the gallium ion. Gallium ion implantation in your sample, how you are taking care of that?
How we are taking?
That is, you have a nanomill or something, or you are just taking after fibbing directly, you are taking the TM?
No. We are doing it after we are having the Omni probe. With that, you can deposit and you can also remove. So what we are doing, we are using that gallium to remove the material, and then using platinum to actually weld it.
No, during the after fibbing, generally sometimes some gallium damaged layer is forms on the sample.
Okay. We are talking about damage. Yes, the damaged layer can be cleaned. We have the plasma cleaner. It can remove the surface. The plasma cleaner can remove the whole holder, the sample holder. Before the TM, it goes to TM. You can put in the plasma cleaner and clean it. So the surface things which is there can be cleaned out.
Okay, I
think it is a plasma cleaner. It is a plasma cleaner for the TM holder.
Yes. Okay, thank you, Dr. Partha. On behalf of the committee, it's my pleasure to
thank you. I am sorry that this thing has not worked.
In spite of that, it was excellent talk. It has very wide spectrum. I think it has 1 or 2 items for everybody. So it's an excellent talk in spite of all
Thank you very much.
Okay,
thank you very much.
Thank you. Now let us, stop sharing this.
Yes, I'll do that.
Okay. So now let us move to the next talk. And this is by Professor Oshiyama Yoshifumi from JIST, Japan. And he is an expert on the nano characterization for innovation in situ TM observation. Basically, he studies on the electrical, mechanical, and electrochemical properties. And his final goal is to discover the frontier materials which are based on understanding physical, mechanical, chemical properties at the atomic level. So and his talk is on the mechanical properties of.
Okay. So thank you for. Okay.
Yeah, please take over.
Okay. Thank you, Professor. Okay. Theory, Professor Theory Sensei. So, okay. Can you see?
Yes, I can see your first slide.
Okay. So, first of all, so thank you for giving me an opportunity to show our recent works. So, in this very good, very nice conference. So, anyway, so I think so many professors in India have made much efforts to organize and hold this nice conference, and I respect these professors. So anyway, thank you for inviting me. So my title is a mechanical property of platinum atomic chains measured by in-situ TM technique. So we are very interested in the such atomic scale or nanoscale. So mechanical property, which is recently so many researchers have interested in. So I'm from from Japan. So Japan Advanced Institute of Science and Technology. So JIST. So my name is Oshima. So this is content. So I briefly explain the why. So we are interested in atom or nanoscale mechanics, and so I introduced a method. So we developed the special TM in-situ TM holder. So for measuring such mechanics, and so today I will show the two main results. So first is a stiffening measurement of the platinum monoatomic chain. So this is exactly the monoatomic chain. So recently we succeed in this measurement, and also the we also we successfully measuring the critical shear stress of gold nanocontact. So introduction. So here this is a application for using the atomic or nanoscale mechanics. So nano actuator, so like that. And here this is atomic scale devices. So here in this case is we need to understand the mechanics of such molecule or something. Also here, this is a shape stability of nanomaterials. So here, also this is this phenomena, of course, is related to the such nanomechanics and also the soft electronics. So anyway, so nowadays, so many researchers are interested in such nano scale mechanics. But you know, so as you know, so the atomic or nanoscale mechanics, this mechanism different from the bulk traditional mechanics. So here, this is the previous methods of measuring such nanomechanics. So one is this is a MCBJ plus a quartz resonator. So MCBJ, this is a mechanical controllable breaking junction. So this is a kind of making a atomic or nanoscale nanocontact. And then this quartz resonator, this is it's a kind of frequency modulation method to measure the stiffness or spring constant of target materials. So here, this is a result of the platinum atomic chain. So here, this is this dark dot, this corresponding, this is effective stiffness here like that. So here, this measurement is was achieved. So during the stretching, the platinum nanocontact. So it shows a clear results. But the problem is they couldn't observe the structure. Means they don't know no information about the structure. That is a problem. So of course, if to understand the mechanics, we need to understand the structure of the target, so nanomaterials. But here in this method, it's impossible. So here, this is another. So this is I think there are many papers about the nanomechanics using TEM plus silicon cantilever here like that. Okay. So in this case, is of course we can observe the structure directly. So by TEM. So, but the disadvantage is difficult to measure the stiffness precisely. So, because here, this case, using silicon cantilever, so in order to estimate the stiffness or spring constant, we have to measure the displacement of these nanomaterials. So this is displacement. So displacement, so precisely. But that is quite difficult. That is a problem. So this is the purpose of our study. So first is development of in-situ TM holder equipped with a quartz resonator as force sensor. So because we want to measure the stiffness more and more precisely. The second is a measurement of not only the stiffness of metal nanocontact, but also energy dissipation due to plastic diffraction. So this is advantage of using frequency modulation method. So we can obtain not only stiffness, but also the energy dissipation. So this energy dissipation is also important information to understand the plastic deformation something. The third, so now, so this is so our result is first estimate the bond stiffness of Young modulus and or estimation of critical shear stress. So this is a related plastic deformation. So the next is so I will introduce briefly the principle of frequency modulation method. Okay, so using the quartz resonator. So in this studies, we use this length extension resonator. So this called LER. So it has long this bar like that. So this quartz resonator is oscillated. So like that. It oscillated at resonant frequency. Okay, this resonant frequency is if contact that doesn't exist. If contact doesn't exist, it has a own resonant frequency F0. But this resonant frequency is shifted when the contact is making like that. So it means so the resonance frequency of the quartz is shifted by delta F when metal nanocontact is formed, delta F. So from this delta F, so we can estimate this is a stiffness of the target material. So like that. So this is a advantage. So here this case is also here LER has so this advantage. So it has high stiffness and resolution frequency is relatively high, about 1 megahertz, and so high stiffness 9 times 10 to 5 Newton per meter. So this is a very high stiffness. So due to this advantage, so here the amplitude of LER oscillation is only 25 picometer, quite small. So such a quite a small amplitude, we can estimate the stiffness here, like that. Also, as you know, the Young modulus. So if we can get this value, so Young modulus was obtained by. So here, this is measured spin constant. This is my length, and this is a cross section. So this is the shape. So these information can be obtained by in TEM image. So so it means we can estimate Young modulus easily like that. So here, this is so I use so this ultra high vacuum TEM. So this TEM are special. So because of this such a very high vacuum condition, about 10 to minus 7 Pascal. So to avoid the contamination. Yes, and also this is a photo of our developed TEM holder, this in-situ TEM holder. So here, this is a schematic illustration. So here, this is a LER. This is a counter electrode. So gold, platinum or gold nanocontact is formed. So between them, okay, here like that. We also measure the electrical conductance, and also the stiffness was measured by this LER here like that. Okay. So here, so this is a one typical in-situ experimental result, TEM experimental results. So here, this is so TEM image. So, and then this is simultaneously measuring electrical conductance, and this is a spin constant of platinum nanocontact here. Okay, this is a snapshot or snapshots. So here, this is the time evolution of conductance and spin conductance like that. The A, B, C, D, E, F. So these so these TEM images were taken from such point. Okay, here like that. Here, this point, this is it looks this plateau. So this plateau corresponding to the formation of platinum monoatomic chain. Finally, this is the contact was broken. So it means so zero. So zero and so yeah, like that. Here this is the conductance zero and also spring conductance becomes zero here like that. Here in this experiment, the stretching speed is 0.08 nanometer per second. So this is this was controlled by tube piezo. So we fabricate the two different monoatomic platinum atomic chain. So one is here. This case is a 110 chain. So this is a so both electrode, the orientation of the both electrode is 110 direction. This is parallel to the monoatomic chain here, like that. The another is here. In this case is a this side is orientation is 111 orientation is parallel to the monoatomic chain. So this side is a 110. So it means here case is shape of the electrode is different. So here like that. Okay. We call this part, so this part is a base part. This supporting part is we call base part. Atomic chains form, so monatomic chains formed. So like that. So here, this is also typical experimental results. So here, this case is so this is a intensity profile. So along this line. So we have so here this point corresponding to the darker spot. So it means that platinum atom were located so correspondingly so at these darker spots here. So here this case two platinum atoms here exist here. So it means that this is a single bond. Bond is single. Here this is a 3 platinum atom. It means so it means a monoatomic chain is formed to 3 atoms, 4 atoms, and 5 atoms. The this interatomic distance is almost the same, so 2.5 angstrom here. This is a conductance. Here, this monoatomic chain corresponding to that here, this plateau here. Plateau is so it means so this monoatomic chain is very stable. So even in this case, at this moment, so this monoatomic chain was stretched continuously at a speed of 0.08 nanometer per second. So very stable. Here, this is a stiffness. Stiffness is also shows us such plateau here like that. Okay. So this is a typical experiment. We measure the stiffness of about 550 platinum monoatomic chain and make this histogram of the stiffness. So in the case of this is it makes this is a 2 atomic. So this chain, this monoatomic chain was formed by two atoms. Here, this case is in this case is stiffness like that. The 3 like that. 4 like that, 5 like that, here like that. This is a 110 chain case. This is another case. Another case is also 2 like that, 4, 3, 5 like that. So now, so here we have to take care of this point. We have to take care of this point. So this notice the measured stiffness includes a contribution of base part, not only atomic chain, stiffness of atomic chain, but also this base part. Okay, so it means we have to remove the contribution of the base part. So we analyze this data more. So here, this is a measures. So because base part and this monatomic chain is almost the series. So it series coupling of base part and monatomic chain. So here this case is the case of 2 atoms. So this is a major spin constant. So this is equal to the this is a base, the spin constant of the base. This is a spin constant of the this bond here. So it can be expressed by like that. In the case of 3, like that, 4, like that, 5, like that. We also take care of the spin constant here. This bond is connected to the edge of the base part. So, but here this is a middle atoms. So this is a bit. This is a this bond corresponding the bit correspond the bond between the middle atoms. Here also middle pass. So we think the maybe stiffness different. This part. Also this part is different. So we take care of this matter. So and then such expression is obtained. So from this equation, so we can obtain the each stiffness here like that. So this is the result. So here this case 110 case. In this case is a base. It has a stiffness like that. And this is another case is here like that. Of course, the shape of electrode is different between them. So of course, stiffness also different like that. Also, we also calculate the simple based on the simple shape model. We calculate the stiffness of base part. So this result is also similar to this value. I think so that we think so this is a reasonable value. And also this is a 2-atom chain. So only the contribution of the 2-atom chain. 3, 4, 5. Also, this is another case, 2, 3, 4, 5, like that here. So from this, from this, we found the here stiffness of this bond. The bond stiffness is 25 Newton per meter. But here this is a 23 Newton per meter here like that. So this bond stiffness is slightly higher than the bulk one. So bulk one was calculated to be about 20 Newton per meter. So slightly this value is higher than the bulk bond stiffness. So anyway, so this is to my understanding, this is a first time in the world to successfully measure the individual bond stiffness. So they also we have interesting in this plateau. So this long plateau is it means that this monatomic chain is stretchable. So elongated. So structure. So we try to estimate the maximum strain, elongation, the maximum elongation. So for each each case is 2 atoms, 3 atoms, 4 atoms. Here, this is just this histogram of this length, for 2 atoms, 3 atoms, 4, 5, the 5 atoms here like that. So, and then, so maybe this is a maximum elongation length. This is a maximum length of elongation. Here is a, we think this is a broken monatomic chain, may be broken due to thermal fluctuation or something. Here, this so we this is so we think this is a maximum elongation for each monoatomic chain. Okay. So also we just a little bit precise measurement estimation. So because this elongation also occurred not only at the monoatomic chain, but also at the base. Base part also maybe slightly elongated. So, yeah, this is a base part, contribution to the base part and the edge part, like that. So from these calculation, we can identify so this is the maximum elongation bond is for 2, 3, 4, 5 monoatomic chains is here like that. So these values are quite similar, about 0.06 nanometer. For this is for each bond. Okay. So so as I said, the typical means maybe this typical means equilibrium atomic distance is 0.25 nanometer. So 0.25 nanometer, and the maximum elongation is about 0.06 nanometer. So the maximum strain is very huge, 24%, very huge. So this is so our experimental results. So this is a very specific feature, I think, the atomic scale mechanics. So, so in order to understand, so this experimental result, we achieved the DFT calculation here like that. This is a result of the DFT calculation. So the model is like that. This is it means so monoatomic chain is formed to infinity. So this is assumption that gets us this value. So here this is the 2.4 angstrom is looks minimum energy. This is binding energy. So is but the problem is here. So it means the potential is minus 2.4 electron volt, but bulk is minus 8.8 electron volt. So it means the atomic chain is unstable compared to the bulk FCC crystal. So here, so we have to think more to understand the real atomic chain. So we have to use this concept of spring tension. Okay, here. So this string tension. This concept was developed by Tosatti. So this concept can explain the stability of the atomic chain or nanoscale nanowire or something. So here this string tension is so here we calculate this one. This one is this is the string tension is equal to the F minus chemical potential times the number of atoms per length of the wire here. This is a tension. It's a physical. This is a corresponding to the tension. This F describes a generalizer with string tension that the tip suspended wire will seek to minimize. So here like that. The Tosati says that the local minimum of this F value of F L is would be realized like. So here this is our obtained string tension. This is a calculated string tension is like that here. So here in this graph, the local minimum is 2.5 angstrom. This is a same value or the experimental result. Also here, this value is this curve is like that. Here, this local maximum. This is a corresponding to the breaking point. This breaking point is 3.2 angstrom. So this is close to the experimental result. Is break point is 3.1 angstrom because atomic distance is 2.5 angstrom and the maximum elongation is 0.6 angstrom. So the 3 point. This is almost close to here this value. Also this curve, this energy curve. Energy curve. No. Differential second differential of the energy derivative is corresponding to the stiffness. So stiffness, so we calculate the stiffness. So this is 26.2 about 26 Newton per meter. So this 26 is almost close to the experimental result is 25 Newton per meter. So anyway, so our experimental result can be explained by this concept of this spring tension. Okay. So this is a summary of the bond stiffness of platinum monoatomic chain. So we observed platinum atomic chain, and we could estimate the stiffness, bond stiffness, individual bond stiffness 25 or 23. Also the maximum strain is 24%. So long elongation is possible, so stretchable. And also, so these phenomena can be explained by the concept of string tension. Here. And the next, next is here. So critical shear stress of gold nanocontact here. So here, this is a gold contact. So when stretching, so we can observe such sliding. So sliding. So here like that. So we the gold crystal breaks with slippage. So as you know, the critical shear stress, this is one of the important parameters to understand the mechanical strength of crystal. So, but bulk cases are a little bit complicated because dislocation, grain boundary or something, so influence on the critical shear stress. So anyway, so gold and nanocontact with several nanometer in diameter here like that, in the state is in a state close to a perfect crystal, so with almost no defects. So therefore, for metal NC, so we believe near ideal CSS can be measured. So that's the reason. So we try to measure a CSS for using the gold nanocontact. Here, this case is contact is stretched along the 110 direction. Here, this is a slip plane. So slip image is 111. Of course, this is a plane is 111. Also slip direction is 112 direction here like that. So we use again this same. And so in this case is so I'll skip だけど、also from this system, so we can obtain the dissipation energy here, by monitoring the excitation voltage here, like that. So here, this is the key point. Key point is that resonance frequency is shifted so that the phase becomes 0. And the excitation voltage is controlled so that the output voltage becomes constant. So using a feedback system. So and then using the monitoring the excitation voltage, so we can calculate the energy dissipation. So here, this is a dependence of LER oscillation sample. This is also the property of this LER. This is a method. So briefly, so LER is oscillated like that. So one frequency is 1 megahertz. So if below the critical value, below the, so it means oscillation amplitude is small. In that case, is no slip. So it means we can measure the elastic deformation. So of course, energy dissipation well quite low. Only energy dissipation is occurred by the friction inside the LER, mainly LER and also the gold contact, but no plastic deformation. So, but above the critical value, so such as slipping occurred repeatedly because of the oscillation. So precipitation is occurred. So the energy dissipation is largely increases. So from this difference, so we can measure the, we can estimate the energy dissipation by this slipping. Here, so this is a formula that here. So here, this is so maybe you know this. This driving, this is corresponding to the driving excitation voltage, driving force. This is a driving force. This is a friction, or sometimes this is friction or some slipping, so something. So this is caused by gold atoms. So here like that. From the energy dissipation is described like that. So because here and here, this is a conservative force. That these terms can be ignored. So when integration of the by one cycle. So here like that. The energy supplied to the systems. So one cycle, so supplied energies can be expressed like that. This are equal here like that. So this is a sort of any result. So if gold contact doesn't appear, exists, means that this value is 0. In this case, it's a dissipation energy is like that. But with after making a contact, so this like that. Okay, and also the like that. So be careful is that this is an excitation voltage. So with gold, and so this is with gold. Here this is without gold. Before making a gold contact, energy excitation voltage here, after making like that. So any key point is a high, this is a Q factor. So this higher Q factor is so more sensitive energy dissipation. You can understand so from this formula. Here, so, これちょっとあれだな。ちょっと待って、sorry。ちょっとムービーが。Okay. So here, this is a typical result. So this is a TM image. Sorry, the video doesn't work. So this is a TM image, and so we simultaneously measuring this is a output voltage. So this is corresponding the the amplitude of amplitude, LER oscillation. This is the amplitude. This is the excitation energy, different change of the excitation energy, and this is a spring constant here like that. So from this data we can make such a graph. So this is the excitation energy dissipation and the spring constant as a function of amplitude of LER oscillation. So amplitude is small. So in this case, the spring constant is almost same, and also dissipation almost no more very quite small dissipation energy because this is an elastic region. But above about 110 picometer, so here this part, so dissipation increase like that. So spin constants decrease. So it means that in this region, plastic deformation was occurred. So, same again. So the actually the measured spin constant is a series connection coupling of this contact part and the base part here like that. So from this and also considering this point, so first according to Fuchs law, the yield force can be given by here like that, and then yield stress can be obtained from the measured spring constant and the critical amplitude. Critical amplitude. This is in this case is a 110 picometer, and the cross-sectional area S of the. So this value can be obtained from the TM image and here like that. So anyway, so from this formula, so we can retrieve this relation. So this relation is that this yield stress can be calculated by the measured spin constant and the critical amplitude and this cross-sectional area. So we measure the yield stress about the 10 different samples like that. So 1, 2, 3, this 6, this 6, 7, 1, 2, 3, 4, 5, 6, 7. This 7 is a y-axis is parallel to the 110. This case is a 111. So different orientation. So 110 case. This case is about 2 giga. This is a yield stress, not CSS yield stress. These are 3 gigapascal like that. So, and then we obtain the yield stress. So this yield stress has a relation with this is a CSS. CSS. So this is a yield stress. This is a CSS, critical shear stress, has a relation with a Schmidt factor. So here like that. But this is a geometry, so determined by geometry. So here like that. So 110 case is a Schmidt factor is here. So 11 case is a Schmidt factor is here. So by this Schmidt factor, so finally, so in this case is a CSS is 0.94. Also 111 case is 0.94. So these results were matched. So in this case is we believe this value is correct. So we believe correct. So also that time to here. So also here so we also checked the estimated critical shear stress CSS by using the dissipation energy. So here this is briefly explains what's the energy dissipation. Okay, so this is this is stress strain curves. Yes, when elastic response, this is a linear, in this case, a linear elastic, linear response. So tension, the compression like that. But plastic response is occurred here like that, plastic like that. But it's this curve also depend on the brittle or ductile or something, but like that. So this area, this corresponding to this energy dissipation, this energy dissipation. Then also the measured spin constant is like that. Basically the measured spin constants during the this kind of average, so during the plastic response. So the basically spin constants are reduced. So during plastic deformation. But here, this case is we use a LER. It means amplitude is oscillated. LER was oscillated. So it means so sometimes a tension, sometimes a compression. So it has repeatedly. So because the cyclic plastic response may be occurred here like that. So in this case is this area corresponding to the energy dissipation. So we try to calculate this area and compare to the experimental results. Here, so this is our model. So here, like that. First, this is a elastic response. After that, due to the slipping here, like that. This value, so calculated by this here, so we obtain that. So this is a dissipation, so calculated dissipation energy as a function of the amplitude. So amplitude is above 150, so slightly increased rise. This is an experimental result. If the near critical value, so looks similar, but after that, maybe I guess as the amplitude becomes larger and larger, so more complex phenomenon, plastic becomes more complex. So that may be different from this simple model. So anyway, so like that, we calculate, I think we can calculate the critical shear stress. So the gold non-contact case is 0.94 gigapascal. So anyway, so conclusions, our developed in-situ TM holder has a great potential to understand mechanical response of nanomaterials. So like that. And also we welcome so collaborative research, and so we have JIST. So we have some Indian professors like that. Manoharan-san, so he graduated IIT Kanpur, and then so many Indian students studied in this university. There was a Bandam sensei. This is he studied lithium-ion battery or something. So here, this is please. So if hopefully, please visited my university. So thank you for attention. Okay, that's all.
Yeah, Professor, there are some questions. Can we take it now? Some questions are there. Hello.
Hello.
Can you hear me?
Hi.
Okay. See,
Hi.
one question is from Professor Deepankar Banerjee. He is asking, why are you talking about slip direction as 112 and not as 110 in in gold CRSS measurements?
So this case is 112. 112 is a partial, maybe corresponding with a partial dislocation. So in this case is from TM observation, in-situ TM observation. So we identify the direction it's 112.
So you think that the dislocation has broken into partials? Okay.
Yes.
Okay. I did
Okay.
one more thing. When you are calculating this spring constants, and
Yes.
so how you are separating the shear component with the tensile components?
Sorry, we have to separate the contact part and the sorry, and yes,
because when you are deforming, because the sample size is very small, lot of atoms are on the surface. Okay, so they will see more of a shear force for readjustment rather than going under complete tensile forces.
Oh, sorry, tensile force.
Yes.
Tensile force. So which slide do you
see? Yeah, when you are
so which slide かな? ちょっと待って sorry. So sorry, I couldn't hear this
yeah, I think this slide 10. Okay.
Done.
So when you are making this chain and you are giving the deformation, so atoms can deform in any ways, can go through a shear mode, can go in because there is a one string attached. So it can have a shear component as well as tensile component.
Shear component.
Yes. So when you are calculating the bond stiffness,
yes.
So you are pulling the bond.
But yes. Here, this case is so continuously we stretched.
So
stretch, yes.
Okay, but do you think the atom will also go in the complete tensile mode? They will not having any readjustment done?
No だね。Here, this experiment done during the stretching, not compressing or something. We didn't observe the compressive process.
Okay.
Yeah.
So, Dr. Tiwari, I have a question.
Yeah, please go ahead.
So, Professor Osima, so you have shown these results for pure gold and pure platinum.
Yes.
So, did you try with platinum, silver, platinum, gold alloy or something like that?
So that is a good question. So yeah, now so we have a plan to try such. So the influence of the such alloy, yes.
Then how do you differentiate between different atoms like gold?
So also good question. It's quite not easy. So, one is if possible using the as you know the STEM scanning TEM because Z contrast atomic number contrast but this is in situ observation. So yeah, yes, you are right. So we have to think more to identify the element. Yeah.
Okay. Can I ask a question?
Yes.
Yeah, please go ahead.
Okay. So one thing I was wondering, so how you, the sample preparation is really critical, right? So is it you thin the nanoparticle or how you take care of the thickness part, or you just look at age and try to do it? That was my, I couldn't.
So so your question is about the sample preparation.
Right.
Yeah, this case is quite simple. Just first we suspended the very thin gold or platinum wire. The diameter is about 10 micrometer something, and so this wire was cut by the stretching, and then we start to make a contact like that.
Thank you.
Very simple. Yes, sorry. Very simple.
So you can do, in principle, you can do any nanoparticle possible. Like most of the nanoparticle can be done in.
Nanoparticle. Nanoparticle. Yes, maybe nanoparticle, but maybe possible. だけどちょっと little bit maybe by chance, after you see, means so after, by breaking the wire, so we make a base part, and then so if we can attach the nanoparticle on the surface of the such base part, so we can, I think we can measure the yes, mechanical property of nanoparticle. ちょっと little bit ちょっと maybe ちょっと harder. I think.
Also the problem in case of alloy is going to come with your spring constant, right? Because you have to determine spring constant of those alloys and then try to fit with your model. Is it going to be challenging as well, right?
Yeah. Yes. So sorry, challenge. Sorry, ちょっと I couldn't.
Yeah, there will be several constants.
Right.
There will be, in one equation, there will be several constants.
Right. Okay, perfect. Thank you.
Okay, thank you. Okay.
So let me thank Professor for giving very, very detailed talk and giving almost covering all the aspects of the nano mechanics. Thank you very much. And on behalf of the organizer, it is my pleasure to thank you for giving such a talk.
Okay, thank you.
Thank you very much.
Thank you.
Kindly unshare you are sharing.
Okay. Okay. Hi.
Yes. Thank you very much. So we shall move to the last talk of the session. And this is by our Abhay Gautam from IIT Gandhinagar. Abhay has passed out from University of Roorkee in 2000 and then gone to Alabama at 2003 and the Virginia 2009. He is one of the few handful Indian research people who are doing the dynamic TM related work, particularly high resolution, some of the impressive work done by him. And today talk is study of interface structure and dynamics using of in-situ transmission electron microscope. So to Professor Gautam.
Thank you, Chairperson. I hope everyone can hear me clearly. And then
yes, we can hear you. We can hear you and slide as well.
Okay,
please
thanks
go
a lot. Okay. So first of all, I'd like to thank the organizing committee, especially Professor Kishanu Biswas and Professor Chandrasekhar Tiwari for organizing this symposium. And also I would like to thank the Electron Microscopy Society of India for supporting such an initiative, keeping us busy in a positive and constructive way. So I'll not take much time, and I'll present one of the work that I had done long back, and then I have done it in parts, and it continues to be one of the problems that we keep looking forward to. And then this is about the structure and dynamics, studying structure and dynamics of an interface using in-situ electron microscopy. So this work actually started when my supervisor had made some observation at Stuttgart. So before we get to that, this is just one motivation slide. I thought I'll bring it here. This is an old 1999 paper which came out in Physics Today. And then the question there was that as we are going towards smaller and smaller dimensions and designing our structures at that level, we typically focus more on the structures and on their functionalities. But one area where we typically do not pay much attention is their stability. Of course, there is a lot of work, but stability in terms of their dynamics or the changing shape that comes along because of their kinetics being small. So here is an example of externally influenced dynamics or fluctuation where an electric field was applied to a silicon surface. And then these styrations that you see, these are single atom steps. And then the second image is doing the same thing using a thermal activation, and that was at 900 degrees centigrade. These bright lines that you see, red lines, those basically show how the single atom step at the surface were fluctuating, just sitting at a high temperature. There was no additional factor that was causing these, right? So, I mean, one of the accidental observation was in gold copper alloy. So before I walk you through that process, let's just quickly understand for those who are not familiar with this system. Gold copper is a very nice system, provides us 3 ordered phase. phases, basically A3B, AB, and B3A type. So we are looking somewhere around this 1:1 ratio, where we have one gold copper ordered alloy. Basically, the crystal structure is similar to a face-centered cubic, but an alternating layer of gold and copper when looking through along the C-axis. So that's the easiest way to imagine this system. So we will be looking at a composition which is slightly below this 1:1. So we are looking into an area where we are going to see some ordered phases and some disordered phases. And then the area we are most interested is the interface between these ordered and disordered phases. Now, these ordered disordered phases are extremely coherent. So they have very low interface energy, and then that gives them makes them quite mobile. Although crystallographically, depending upon the interface direction, one of the facet is kinetically stable, but still these facets tend to be kinetics-wise quite active. So so the specific alloy that we are looking at is 41 atomic percent copper in gold. And then in here, you see, we'll try to be in the region where we can have both these ordered and disordered alloys. And then so the temperature would be typically of the order of 250 to 300 degrees centigrade. And then so we'll take particles of these alloy, roughly 30 to 40 nanometer, and then we'll heat it up to this temperature, and we'll just see in an electron microscope in a nice interface region how this behaves, right? So the samples for these were prepared through physical vapor deposition. These were deposited on an amorphous carbon film. This was core deposition. It was done at 550 degrees centigrade just to make sure that everything mixed together properly. They were annealed up to 8 hours in vacuum, almost ultra high vacuum. And then finally, we targeted for 20 to 50 nanometer particle size. And then the first set of observations that I'm going to show were done in Stuttgart by my supervisor. It was using the dual ARM microscope nowadays. So it's extremely high beam energy. That's the key point that we have to remember. Right? And then, so here's the schematic of how everything looked like. From the side, it was almost spherical, although there was a little bit of wetting on the amorphous carbon substrate, but by and large, they were quite equiax. This is the typical particle size distribution. The one we are going to be interested is going to look something along these lines, right? Where we have, well, these are Moira fringes, but you'll have an ordered phase and a disordered phase, and then we'll be looking at an interface. This is just to convince you that what we are looking for at the temperature that we are looking at is going to be an ordered disordered combination. So we have all the respective diffraction rings for ordered phase as well as the disordered phase. And then this is the image. So this image is actually from a movie that was recorded. So the movie was recorded at 30 frames per second, or 30 frames per second. And then that's why the resolution of this image could have been better, but since it was recorded back in day on a TV rate camera, you see some fuzziness. So on the top that you see here, we have this ordered phase, and then there what you're not looking at are the So what you're not looking at are these copper planes. So we can see the gold planes, and then the copper planes. The reason why we're not seeing them properly is because the intensity from the copper plane is quite small. We can also go ahead and take the structure of a gold copper system and then do the high resolution simulation, and then for the given microscope imaging condition and roughly the thickness of the particle, you can clearly see that the gold planes show up in this imaging condition, while the copper planes are barely visible. And then you can see some areas, you can see presence of copper planes. On the disordered side, however, you can see both the planes, which is 002, because both gold and copper are mixed on each and every plane. And also, if you look at the transition where you go from the ordered side to the disordered side, there are these, you gradually see these copper planes, or on the ordered side, they start to show up, right? And then while we transition towards the disordered side. So we can take a nice line profile and follow up the intensity. And then there you can see these 001 spacing of the gold planes. And then you have on the disordered side the 002 spacings, and right in between where you have the transition from only gold to gold copper plane combination, we'll call them as a diffuse interface region. That's just our definition for these measurements, right? So what we'll try to track in these images is the position of the ordered side, the position of the disordered side, and this width of this interface region between ordered and disordered part of this nanoparticle, right? So I'll just run this movie. I hope it works. Yep. And then if I put the cursor here, you can just see that the contrast from the gold plane pop in and out of as the time goes by, right? And then you'll see that these will actually extend a couple of atomic planes. They'll walk through, and then they'll go back, right? And then these kind of fluctuations, we are again roughly around 300 degrees centigrade. But other than that, being sitting stable at 300 degrees centigrade, we are not doing anything else. So this fluctuation is combination of both beam radiation in all likelihood and the high temperature or relatively high temperature that this material is sitting at, right? And then this phenomena will continue to go back and forth. So what we can do is basically we can take a series of these movie segments and then export the individual images out of it. And then in all those individual images, we can go and track the position of the ordered side, the disordered side, right? So the disordered side, if you try to, if the resolution is clear on your screen, the disordered side would basically go all the way up to 7 lattice sizes, right? So the fluctuations are large, relatively speaking. So let's go ahead and then look at the same thing, which is going to be a little more visible in this plot profile. So I'm basically using the same line profile, and then for each frame I'm drawing on the line profile. Now instead of looking at the movie of the actual image, now we can actually look at how these intensities are coming in and out as a function of time. These are accelerated because just to show that how significant these fluctuations are. So these are not just the noise in the imaging system. These are a real signal that we are looking at. So if you look at it, the fluctuation on the ordered side, it almost goes all the way up till here. And then the fluctuation on the disordered side will cover this almost this entire distance. So at one point, we'll have the 7 crystals of gold copper unit cells over which the entire interface would be distributed. So this is showing the same thing. Like I said, here we are just measuring the ordered and the disordered side of the interface. So the red line here shows the disordered. And then one thing to notice is the disordered side of the interface clearly shows a lot more fluctuation, right? In the sense that the frequency of shifting of the disordered side of the interface is much higher compared to this green line, which is the ordered side of the interface. The ordered side, of course, jumps the jumps are discretized because one, we cannot track the jump of the ordered side from gold to copper plane because we are not looking at the copper plane in current imaging situation or condition. So we are only catching up gold to gold plane jump, and that's why these jumps are further. So the jump on the ordered side of the interface is one gold plane to another gold plane, which is twice of what we see on the disordered side, where the jump is from the for each of those 002 planes that we are looking at. Right. Now, another thing to notice is the distance between, or the width of the interface, which is simply this distance between the red and the green lines, right? So it remains fairly constant for a while. After that, it changes, right? As the position, the average position of the interface changes. And then as the position tries to go back, that distance also tries to track that. So somehow the position of the interface and the diffuseness of the interface is interrelated, but we'll try to see that in our next plot, which is this one here. Here, the blue line is showing precisely that the average position of the interface, which is basically, if you want to see it in terms of the previous plot, which is the halfway distance between the ordered and the disordered side of the interface that we have marked. And then that average position with small fluctuation stays constant. And then after a while, it jumps. And then after that stays steady a little bit. And then it gradually goes back towards the initial average position. So what it shows is that we are moving back and forth in terms of average position of the interface. So the interface is fluctuating. But one thing to remember that the fluctuation of the interface that we see is more on the disordered side of the interface, while the ordered side is fairly steady, right? And similarly, the thickness of the interface stays pretty steady. And then it follows up as the interface position tries to shift, right? So they're somehow correlated, but we don't know yet as how they are. I mean, so in terms of if you want to see the statistics from these measurements, then the interface thickness, we measured it to be roughly 1.7 nanometer to be the average interface thickness over the period of observation. The minimum thickness was about 8 angstrom, and the maximum was about 3.3 nanometers, right? The frequency of fluctuation was roughly 1.2 every second. With the minimum frequency, the most stable was 0.4, and the most frequent fluctuation was at the rate of 7.7 fluctuations per second, right? And then we can also go ahead and then the region where the transition happens, where the interface is moving, we can try to measure the velocity, average velocity with which the interface is moving, and that would turn out to be roughly in the range of, on the ordered side, it's slower, like I said, it's 0.3 nanometers per second, and on the disordered side, we measure it to be 1.3 nanometers per second, right? Now, this is all the observation that we make, and then of course the measurements that we made from it. Now comes the difficult part of understanding what's happening inside it. So the first question is, what is the structure of the interface? So the diffuseness that we see in between ordered and the disordered side of my phases, what is the basic reason for that? And then there we looked into at least 4 different conditions which can lead to such a diffuseness. And then that included that we have an ordered and disordered side, and we just go ahead and then chemically diffuse our system, or we physically diffuse the system, or we take or the physical diffuseness can be, instead of bowing, I can have an inclined interface, or we can have combination of all, which is the inclined and the chemical diffuseness. Or basically by chemical here, I mean the order parameter variation from ordered side to the disordered side. And then based on that, we can build up our unit cell and then create a crystal of decent size, and then run the TM simulation. So these were done using the MacTempus commercial software. And then using again the same imaging condition under which we did all those imaging. We get these output. And then frankly speaking, I mean, there are small variations that I can point to, but as far as the practicality is concerned, there's not much difference between these 4 images. So just from these, it's very hard for us to say that the exact 3-dimensional structure of my interface from available images, right? Then we can also go and look into the individual frames and try to figure out if there's any evidence or indication of how these fluctuations are taking place. And then typically the literature on interface migration, it relies on 2 key phenomena. One is the nucleation of a step on the interface, and then the second one is the flow of those step or migration of the step leading to the lateral motion of the interface. And as it turns out, in our case, we were able to observe both of these. So it's not one versus another dominant phenomena. For instance, here, if I draw out, outline my, visually, where is my interface? This is what it looks like. And then this would be a typical candidate where the step on the interface will flow laterally, leading to the transverse motion of the interface, the one that we see. But then we also see the evidence of this pillbox type nucleation of the ordered phase inside a disordered side of this interface. And then this second image, on the other hand, is a pure step motion, as the step flow process through which the dynamics was happening. So we can take the evidence of both, but then when it comes down to the details of the unit processes, just from these images, it's very hard to get to those details. Now, so I mean, so this work was concluded. We tried to we published it, and then one of the key comment on this was how much of that what we see is driven by the radiation or electron beam, and then the answer to that for us was we don't know. The temperature, of course, was playing a role, because if we run the same experiments at room temperature, we don't see any fluctuation. So the temperature has to be a critical factor, but we don't have the luxury of removing the radiation because we have to see it in the TEM. So we cannot say with reasonable certainty that radiation was not the necessary required condition for these fluctuations to take place, because we know that electron beams do kick in vacancies, and that can create these kind of fluctuations. So the idea was to repeat those experiments, but under different conditions. So instead of 1.2 mega electron volt, we went to 200 kV dual microscope and tried to do the same experiment. And then like you'll hear all the time that in-situ experiments are hard, difficult, and then difficult to interpret. Repeating in-situ observation is near impossible. So I mean, that same observation for 200 kV, just to prepare the sample and get to the same kind of a particle which has the same ordered disordered interface, which is surrounded by a same crystallography of disordered interface, it took us about 2 years, and then we were able to repeat that experiment in this. Again, the rest of the conditions were kept similar, 300 degrees centigrade. We used condenser aperture and In-situ lens to basically change the beam sizes so that we can have different dose. And then following are the observations that we saw. The kinetics was definitely slower under 200 kV beam, but the fluctuations were still there. So this is my relatively low beam condition. This is the readout from the fluorescent screen that typically all microscopes have. So I mean, the number is not that important. What is important is the small variation that we can manage. So this is roughly 135 picoamps per square meter. And then again, qualitatively, the observations are same. The disordered side tend to move much more than the ordered side. The ordered side stability is there. The steps are larger on the ordered side. The steps are smaller on the disordered side. The frequency is higher on the disordered side. So qualitatively same. As far as the kinetics is concerned, the whole process was slowed down considerably, right? Then we can go ahead and condense the beam a little bit. So this was right about halfway through of the best condensed beam. And then we basically just move up by 10 picoamps. So there's marginal increase in terms of the dose rate. So we are looking at 145 picoamps per square centimeter, right, in this case. And then all we see here is that, yes, the kinetics may have picked up a little bit, but that could be just a statistical variation. The rest of the observations, of course, are similar. Again, the disordered side fluctuates more than ordered side more stable, and so on and so forth. And then we look at the highest beam current that we can run through given the microscope limitations. And then again, we are stuck with very similar observation that we saw in case of low beam current, medium beam current, and high beam current. So at the end of it, it's very hard just based on these observations to say that radiation related effect on these fluctuation, how much was it, and then will it happen if the radiation was not there? The only thing that based on which we think it's a realistic phenomena is even in the absence of electron beam is because what we see is thermodynamically validated that it's not the ordered or the disordered side which are showing similar kinetics. Because if it was just an electron beam motivated phenomena, then in that case, the knock-on damage or the vacancy creation would be very similar on either side, because roughly the compositions we are looking at are similar. And then therefore the kinetics should be very similar on the two sides. So the asymmetry of the fluctuation is the only reason based on thing we can say with confidence that these fluctuations are real. And then as we go for a smaller particle size, it should become more and more obvious for us. So it's just a matter of designing a better experiment where these observations can be made in a more comprehensive way. So I mean, I'm going to summarize this, and then I already mentioned that running these experiments on order disordered interface in copper gold system roughly at 300 degrees centigrade, we see the interface fluctuation. These interface fluctuations do show more stability on the ordered side of the interface than the disordered side interface. We see both motion of average interface location and the width of the diffused interface both fluctuating, somehow correlated. The process through which the fluctuation takes place, that we saw both the evidence of pillbox type nucleation event as well as the step flow process, which was leading to these kind of fluctuation. And then our attempt to understand the role of electron beam radiation, although gave us some clarity, and then we are reasonably confident that this is not just electron radiation driven phenomena, right? But we need better sensitivity in terms of measurement, better quality in terms of imaging, and then better microscope parameter controls in terms of the range over which we can do the imaging to actually say it conclusively that's what the case. And then all these data that I'm showing, those are roughly about 10 years old, where the technology was still developing. So in last decade, the microscopy field has seen a massive growth in terms of the detector technology and then the in-situ holder technology, right? And then just to give you an example that why we are willing to go back and then repeat these experiments, I'm going to leave you with this one slide. This is gold thin film, right? And what you see here is a grain. A small grain, which is embedded inside 110 oriented gold film, right? And then this is just under the electron beam radiation, no heating. And then our sensitivity is good enough nowadays that we can actually measure most of the millisecond unit processes, and from there gain insight into what actually is driving these systems, right? So I'll just run this movie in loop, right? And then if you keep looking at it, suddenly that whole grain disappears, leaving behind the net residual defect, which was part of the initial grain boundary. So I can go around the grain boundary and basically add up all the defects that were present there, and then sum total. And as the grain is gone, right, that leaves behind these defects, right? Something that would be very interesting for I guess, field of grain growth or gain. So that's the last slide. At this point, I'll stop and then I'll be open. Thanks for your attention, and I'll be open for questions and comments.
Yeah. Thank you very much, Abhay. Now let me see. This interface, how you are counting for the steps?
So in the images, you mean, right? So so we basically just go in there and we take the line profile, and from there we try to distinguish between the ordered side of the interface and the disordered side of the interface. And then from there we draw the outline where we say that this is where the step is, where the interface is. And from there we draw out the step, and then that's how we do the step counting. So it is prone to human error, but we try to use as much as possible the quantitative intensity-based approach, so that we are, if we have an error, it's consistent error.
But generally, the size of the steps remain more or less within an error bar, or it keeps changing because.
Well, it stays. I mean, in most of the cases, we were not able to find this two-step, two atomic layer step. By two atomic layer, I mean two gold atom layers, right? So these step sizes are pretty consistent. They go from one gold atom plane to another gold atom plane, and they hardly go to jump two atomic planes in them.
Okay, Professor Satyam wanted to ask some question.
Sure.
Professor Satyam. Yes, Professor Satyam.
One wants to ask question by the time.
He can speak now. I have made him. He can speak now. Is it Satyam?
Me?
Satyam?
Yes. Can you hear me?
Yes, we can.
Yeah. Okay. So thank you, Gautam, and good talk. Just wondering a few questions. The thing is that first of all, when you look at the atomic steps, the vacuum plays a big role because you are kind of talking about a reconstruction at the interfaces, right? Number one is the system is not very stable at these vacuum pressures -8, -9 in your sample chamber. It's extremely difficult to get the atomic steps unless it's a UHV microscope. That's one comment I have it, particularly, and also the rate at which you take the vibration, the stability in the image, it's also plays a big role. Of course, fortunately, you are not running a water circulation. If you circulate the water in the heater, that spoils further. That's number one comment I have. The second one is probably you should also look at energetically. Theoretically, can you make a point of that one? For example, can you calculate energetically? Is it possible? Kind of a such steps are possible or not? Right.
Sure.
Third is copper 3 gold is a standard system, and it has a structural phase or phase transition. Ce3A is one such thing, right? Around 400 degrees Celsius. So I thought probably you could extend this to a structural phase transition as well. Okay, these are the few remarks.
Sure. So, I mean, just to comment on, so the steps that we are looking at, these are not the surface steps. We are looking at through thickness step here, right? So, I mean, there, of course, there is this nuisance that depending upon the three-dimensional geometry of my actual interface, I may be constructing an interface in the 2D projection, which may not necessarily be the right position of the step. Right. So in that respect, yes, the step counting is a difficult process in that respect. But I mean, the step counting which is on the surface of these nanoparticles, that you're right, that is extremely sensitive to the vacuum environment, and then you need an UHV environment. But in TEM, it's very hard for us to actually measure the surface steps in TEM. All we are looking at is the throughput.
No, I think Frances had been doing these things. If you look at Frances Rose's experiments, she had been doing such experiments, and they really did wonderful measurements. But I think one of the big issue is what you said, the 2D projection of a 3D system. It's a big. So
yes. And then you need sorry.
Please go ahead.
Yeah, so yes, I mean, and the reason is unless until you know the three-dimensional structural geometry of the interface, any conclusion you make is going to be, to some extent, speculative. There are always alternatives. And that's why we try to simulate the structure, taking the inclined or the bowed interface. But unfortunately, the imaging condition did not allow for differentiating one with respect to another. And then also coming back to, we did think about the A3B type phase. The problem there is this AB type ordered phase. It gives us that, because of that chemistry, it gives us very nice way of differentiating between one ordered phase and the disordered phase. But if we go to A3B phase, at least when we were doing this experiment, it was hard to, in the image mode, differentiate between the ordered and the disordered phase with details so that we can actually mark the interface position. But now new microscopes are capable of doing that. So we are revisiting this whole thing. And hopefully if we see any evidence of it, we'll definitely like to take this to more general interface and their fluctuations. But those are really good comments.
Thank you.
Yeah, now.
There is some question from Pavan.
Yes.
Yeah, can I quickly ask? So the last video that you showed, it's a clarification. So you said something on the lines of you have millisecond resolution, right?
Yes.
Time resolution. Okay. Yes. So you're using, this is in a STEM mode and you're using K2 kind of a camera, is it?
Yes. So, well, it was not K2 then. So this was done at Berkeley Lab. So so Berkeley Lab was developing this experimental camera. And then it would that technology was transferred to Gatan, which became K2. So it's actually a generation older.
Okay. All right. Thank you. Got it.
So there's a question from Professor Casey.
Yes. Yes.
Hello, sir. Go ahead.
Can you hear me?
Yes, sir. We can hear you.
Okay. One thing, Abhay, nice to hear your talk.
Thank you.
After some time, because of all this. Now, one thing is, I did a lot of high voltage microscopy in Oxford. Now they have dismantled it. But one thing I was looking at, you see, you need a driving force for getting step to. Either it is a pure fluctuations, you don't need any driving force, or there's some driving force which should come from a temperature fluctuations because it's the order disorder transitions. And kind of stability 10 years back that your high temperature holder had, this may be explained simply because of the temperature fluctuations. Because if you have a fluctuation in temperature, you have fluctuations in the driving force of a order disorder, and therefore it can go back and forth because volume fraction will change. Because these are first order. So I think that may very simply explain what you are seeing, rather than fluctuations. It's fluctuations, but temperature fluctuations. Second thing I just like to point out that step can nucleate, step can form by fluctuations. So nucleation and seeing step, these two are may not be different because both ways step can form. And we normally do not know what is the root cause of forming step. So we only say in phase transform it's from random. Thin film people see island growths where they can see clear, nice island. But when you talk about step growth, origin of step is very difficult. It can be two-dimensional nucleations. It can be fluctuations. It's very difficult to point out which one exactly.
I agree. In fact, I said the nucleation, but actually the pill box that we are talking about, it's essentially a fluctuation, right? And then in that case, whether it is even a critical size nuclei for that 2D step to form on the surface of the ordered interface, you're extremely right. That is a very difficult thing to say, especially looking at the 2D projection. And so I think, and also the instability of the heating holder. Yes, the Gatan holders are known to fluctuate up to 10 degrees plus minus. So you're right. So that kind of fluctuations do happen in Gatan holder, and it varies from holder to holder as well. The only thing we know is that we took two different heating holders, one in Stuttgart and one in Virginia, and both of them gave us fluctuation results. And then oftentimes those heating holder temperature fluctuations are happening when we are moving things around. So these observations, we just sat there for 20 minutes before we started recording. So we try to take all the precautions, but nonetheless, your point are extremely valid. And that's why I was saying that now the technology has come to the point where we can say yes or no to some of this.
Yeah, you can look at prototype folder and see what happens.
If we get some money, yes.
No, you can talk to Ravi Shankar and come and do it.
Oh, that would be nice.
He is very much interested in gold, copper, and all this.
Well, I think I'm going to send some emails now. Right. Thank you, Professor.
Okay.
Yes. Now I think with his talk closing, we are going to close this session. So over to Professor Krishanu Biswas.
Thank you, Dr. Tiwari, for nicely conducting the session. I think we are half an hour late from the original time. That's okay. We'll break for lunch, but let me assure you that we have always 100, 150 or sometimes 200 audience in this Zoom meeting. So we like to keep it up. And in the next session, it is from 2:30 onwards. Please join after lunch, and in the evening, panel discussion followed by 3 important talks. So I hope to see you back in large numbers again. Thank you all, and please come back after your lunch. Anything, Chandrasekhar, you want to add?
No, I think 2:30 again. We'll have a 3 important industrial talks and demo and panel discussion. So we hope to see you all at 2:30. Thank you.
Okay, so we break now. So we come back after the lunch. So good afternoon, Waikawa.
Hi, good afternoon.
Okay.
Hi, hello.
Hi.
Thank you.
So we'll start soon.
Now starting.
Yes.
Okay.
So what's the time there? 6 o'clock?
Pardon?
In Japan, it is now 6 p.m.
Yes, I am now in Singapore.
Oh,
Now,
you're,
5
okay, okay. Singapore is 2.5 hours. So that means
yes,
5 p.m.
5 p.m.
Okay. So you have time till then you can have a dinner at 6 p.m. after the talking. So this is the problem of organizing this online symposium. We have different time zones and people of different parts of the world, they come together. Okay, we'll wait for the chairman to join and then we can start.
Okay. Give me another 10 minutes.
Yes.
Can you rest my sound?
Yeah, sound you can test it. It's okay.
Okay, hi, thank you.
Good afternoon, Professor Mukhopadhyay and Professor Mandal.
Hello, hello.
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 Good afternoon.
We have around 3 minutes time. Hello, Professor Mukhopadhyay.
Hello, hello. Hello, Kallol.
Hello, good afternoon.
Hello, Kallol.
Where are you? I'm not able to see you.
Yeah, I can see you. Right. You can see me now. Where is Professor Mukhopadhyay? He vanished? No, he is there.
Hello.
Hello. Hello. Yes, Professor
Hello.
Mukhopadhyay.
Kallol unmute karo.
I was unmute, but right now again I have done unmute. You are not able to hear me?
No, we can hear you. I think
Okay.
Professor Mukhopadhyay is not able to hear us. His mic may have some problem.
So you can, what you can do, you can just come out from Zoom and again rejoin. That could be a process.
Okay, he has gone there. Let me see. Professor Mukhopadhyay, can you hear us?
He has joined. Actually, he is unmute. He has to unmute it himself.
Yes, yes.
Yes. So, Professor Mukhopadhyay, are you able to hear us?
Yeah. Are you able to hear me?
Yes, yes. Now it's all clear.
Yeah. Okay. So you are able to hear the sound system is.
Yeah, maybe you can switch off your video.
So what is the status? We can start now. Hello.
Yes, yes, you can start now. The first speaker is here. First speaker.
Can you start?
Yeah, let me just explain.
Okay. So speakers are here. Let me see. The speakers are basically. Let me see.
Okay.
Just a minute.
Yeah.
Dr. Tetsuo Oikama-san.
Yes.
Then we have Dr. Benjamin Miller. I think who will be giving on video mode, isn't it? This recorded video.
Yeah. Deepak will give. I am making him as a panelist.
Okay. Then Dr. Syed Asif. He is the third speaker today.
Yeah, he is not.
And all the speakers are here now.
No, Asif has not joined, but I think Chandrasekhar will take care of that. He is in touch with him. He will join soon. Then he's the third speaker.
Right. Asif will join soon, after say half an hour.
Yeah.
It's midnight. It's already 1 o'clock. I think he will wake up at 2:30. Yeah.
So all the speakers have joined?
Right. All of them are here.
Okay. So let's start.
Yeah. So let me just
welcome. Okay.
Yeah.
So can
just
you start?
Just a minute, Karola. Let me just take 1 minute or 2 minutes to explain. Hello.
Hello.
Yes, Kishan.
Yeah. So let me just explain. This has two sessions. One is this industry talks and demos, and second one is the poster session, right? So the industry talk and demos will be as usual. the talks will be given by the industry person and it will be open for question and answer. But in the poster sessions, we have 6 posters, 7th or 8%, I don't know, they have not submitted. So what you can do is you can give maximum 5 minutes for each poster. They can make a small presentation if or whatever, and then if some questions can be done, but it must not be more than 5 minutes because we have half an hour time there.
Okay, so is there any possibility of having any prize or award in the poster session?
No, there is no, because numbers are very small.
Okay, that is fine, understandable.
So
now,
please keep the time management properly because we have a panel session starting at 5 p.m.
Okay, now another thing is, if I understand correctly, each speaker is given 45 minutes of time.
Yes, maximum with question and answer, not with the talk.
Total time slot per speaker.
Okay, so good afternoon, everybody. We have session 3, and this will be chaired by Professor Kallol Mandal, Head of the Department of Material Science Engineering, IIT Kanpur, and Professor N.K. Mukhopadhyay from Head of the Department of Metallurgy of IIT BHU, and both are distinguished, scientists and electron microscopists. So I just hand over to both of them, and next session, which will start now. Okay, so over to you.
Good afternoon, sir. May I have a word, please?
Yeah, Deepak, we can hear you.
Yes, sir. The session at 3 o'clock, the talk by Dr. Benjamin Miller will be broadcasted by me. It's a pre-recorded video. So
okay, Deepak, yes, Deepak.
Yes, sir. That's right.
Okay, fine.
Thank you, sir.
Okay, so Professor Mukhopadhyay, are you starting or shall I start?
Sure. Let me start.
Okay.
First of all, let me thank the session, this symposium organizer, Professor Kishanu Biswas and Dr. Chandrasekhar Tiwari. They have taken initiative to organize this in-situ electron microscopy under the aegis of Electron Microscope Society of India. So myself and my co-chairman, Professor Kallol Mandal, I hope you all know, he is from IIT Kanpur, and Professor Biswas has already introduced us to all of you. Now, let us start first. Kallol, you would like to say a few words, or we can start right away?
I think let us start because we have time constraint, isn't it? So I think...
Sure. And each speaker will be 30 minutes, right? Whatever the time program I see, the 2:30 to 3, 3 to 3:30, and 3:30 to 4:15. So last lecture looks like 45 minutes, but rest of the lecture is just the 30.
Professor Mukhopadhyay, your audio, video, can you switch off? You have some connectivity problem. Kallol, can you take over?
Okay. So let me just get to the speakers. Today the first speaker is Dr. Tetsuo Oikawa-san. He is basically from Geol Asia Private Limited, and his area of interest electron microscopy, definitely. And he got award from Technology Development Award from Japan Institute of Metals and Materials, and he has got several publications and books, and one of the book chapters is on analytical electron microscopy for material science, Springer Halla's Tokyo publisher, and he is eminent in his own field. Without spending much time, let us welcome Dr. Oikawa-san for his talk, and I would request him to keep the talk within 25 minutes so that we have little time for discussion. Okay, so Dr. Oikawa-san, it's over to you now.
Thank you, Professor Manda, for the kind introduction. My name is Oikawa of JEL. First of all, I'd like to express our appreciation to organize the committee to inviting me to this conference. Okay, I'd like to share my presentation. Please.
Dr. Oikawa-san, I might just ring a bell, or I would say that this is 25 minutes. Is that okay with you?
Okay.
Okay, fine. Thank you.
Share. So a small problem happened. The window size too big, and I cannot push the share switch button. Just a moment, please.
Krishanu?
Sorry, my window just one is a little bit too big and difficult to touch the shared screen. How to operate? See?
Sir, your Zoom window is visible to you? Yes, it has come. It has come.
Okay, coming. And
yes, it has come.
Screenshot, okay?
Perfect.
Okay.
Yeah,
it's perfect, visible.
Okay, thank you. Okay, today I'd like to introduce in-situ observation data using our aberration collected transmission microscope. Okay, as you know, we have a high resolution aberration collector technology. It was introduced to the market about 10 years ago. Zero has a long history of this technology development. We introduced the product of the JEM ARL 200F till 2008. Okay? And since 2008, and now we can observe the atomic resolution, both TEM and STEM, like this picometer order resolution is now very popular. And also, we can make an X-ray elemental analysis with atomic resolution, and also ELS analysis with atomic resolution are now commonly used. This is the current technology. But on the other hand, in the microscope, conventional microscope, specimen is kept on the very special environmental situation. As you know, specimen chamber is in high vacuum condition. Okay? Then specimen is well dry, like a dried squeeze. It's a very special environment for the sample. In the practical functional materials or metal or normal actual environment, not in vacuum. Okay? And also sometimes heating situation or cooling situation. The environment, gas pressure, gas tension should be higher, such as the atmosphere. In order to observe, in order to evaluate the performance of the specimen, material performance, we need the live condition, live situation necessary. Then now, in-situ observation technology is strongly requested in transmission microscopy. And recently, owing to the many vendors of specimen holders, cooling holder or heating holder from Gatan, and also nano indentation by Histron, and gas cell or liquid cell prototypes, and also heating gas cell or liquid cell by dense. Those are just an example of like this. Owing to this kind of a lot of in-situ observation specimen holder, we can now easily set up the environmental condition in transmission microscope. Now, dedicated environmental special electron microscope is not necessary. Okay, today, I'd like to introduce some of the example of environmental observation using the prototypes, gas cell, and liquid cell. The prototype is now has a gas cell product name, atmosphere, like this, and also liquid cell, Poseidon. Gas cell atmosphere is applicable to catalysis observation, fuel battery, and redox reaction and corrosion reactions. And also, liquid cell, Poseidon, can be applicable to living specimen observation, battery, electrochemistry, and corrosion reaction observation. Okay, I'd like to start at first application of gas cell for the application. Okay, this is just a configuration of the gas cell of atmosphere. Specimen is accommodated in each chip of a very small chip here. This chip is fabricated by MEMOS technology, and specimen is accommodated between silicon nitride, thin silicon nitride film, upper and lower both sides. In this small space in specimen chamber, the gas can be filled. The gas tension up to 1 atmosphere, very high pressure is available, and also heating simultaneously possible. And also transmission microscope used in this experiment, newly developed JEM ARM 300 F2, new model of the version. The feature of this microscope, accelerating voltage up to 300 kV, and zero-made own technology, aberration corrected TEM and STEM collectors. And also, as objective lens, wide gap fold piece are available. Owing to the big gap we can accommodate any kind of specimen holders. But resolution is very high. For example, 59 picometer is available in STEM aberration correction condition. As like this, we can accept any kind of in-situ observation holder owing to the big wide gap of the voltage. This microscope can accommodate the large scale of detector of X-ray analyzer, 158 square millimeter detector, and both dual detector can be accommodated. We can obtain very high sensitivity electron signal intensity from this X-ray analysis system. And also combination with electron energy loss spectroscopy And also cold field emission gun is applied as the standard owing to the energy resolution, small energy spread with higher energy resolution of cold field emission gun, we can obtain the chemical analysis, not only the elemental information, but also we can analyze chemical state analysis. Today, I can introduce this chemical state analysis with in-situ observation. First example of the STEM image in high pressure high gas tension condition. Specimen was anatase single crystal here with hard disk high angle dark field imaging and high magnification image like this. We can clearly observe the atomic resolution, 134 picometer resolution, even the 1000 Pascal gas tension condition, and also heating 300 degree of Celsius. And we can observe high resolution atomic imaging owing to the higher stability of microscope and holders, and also even the high tension gas pressure. But we can observe high resolution at 100 picometer order with owing to the aberration corrector technology. And Fourier transformation provides a resolution as like this. Now we can obtain about 88 picometer, higher than 100 picometer order resolution can be obtained under 1000 Pascal high tension pressure condition as like this. This is very effective to high resolution is in-situ observation. And also increasing gas tension up to 1 atmosphere like this, but resolution 136 and also almost 116 picometer can be obtained. Almost 1 angstrom resolution can be easily obtained, even the high tension pressure condition at 1 atmosphere. Okay, so this is the second application. The specimen was iridium and cerium oxide is a substrate as like this. First stage, hydrogen gas applied. Okay, so oxygen reduction, then iridium particle can be obtained on the cerium oxide substrate here. Then gas switch to the oxygen. Oxidization process, then iridium particle disappear like this. Okay. Once again, hydrogen gas fill. Okay. Reduction, oxygen reduction process. Once again, we can observe iridium particle as well. Owing to the in-situ condition, reduction and oxidization was processed by iridium particles as well. Also, we can observe the high resolution atomic imaging like this. And next one, this is a reduction process from copper oxide as like this. The in-situ observation was gotten 1 view camera in situ mode. We can observe as like this from the porous copper oxide and changing into the single crystal of metal copper like this. Very interesting observation can be obtained. And next stage, we fill the oxygen as H2O. The metal copper is now oxidization process and going into the porous copper oxide powder as like this. We can really observe as the reduction and oxidization reaction as in the live image like this. Okay, so this is another condition, but copper oxide can be analyzed by both X-ray analysis, elemental analysis, and ELS analysis. in the bottom layer, this is the original copper oxide layer. The stem image and oxygen, copper, and copper oxygen overlayer by the EDS mapping. But EDS analysis, we can observe the metallic copper L peak, and also copper oxide L peak here. Okay, and environment controlled by hydrogen gas field, then reduction of oxygen process. Less oxygen in the EDS mapping, copper relatively increase. Then metallic copper yield spectrum can be obtained. Once again, we fill oxygen gas. Oxidation process, copper oxide, oxygen mapping, copper mapping can be obtained. And also yield peak, copper L peak become very sharp, so-called the copper L white line. Okay? And also, as observing more high resolution condition, we can observe chemical shift, 5EB chemical shift from monovalence copper oxide and comparing to the bivalence of copper oxide, 5EB chemical shift. As comparing the fingerprint, as like this. This is a fingerprint yield analysis by standard sample. Okay, this is a monovalence copper oxide and also bivalence copper oxide here. Then 5EB chemical shift can be standard. As comparing the standard fingerprint, we can observe the monovalence and monovalence and bivalence. Oxygen peak can be obtained in high resolution yield analysis owing to the higher energy resolution of cold field emission gun. As like this, as simultaneously with reaction, oxidization, and reduction, we can observe not only elemental analysis, but we can observe the chemical bonding state analysis like this. Next one, I'd like to introduce the application of Poseidon with liquid cell. Okay. So, example here, this is a configuration of the liquid cell Poseidon. So also, e-chip was produced by MEMS technology. Okay. Owing to control the gap thickness with spacer, liquid thickness can be set as 50 nanometer, 150 nanometer, and up to 3 micrometer thickness. As left hand is the live virus, as like this, rotavirus can be obtained. So here, okay, accelerating voltage 120 kV applied, but the thickness 150 nanometer liquid thickness, we can observe the live rotavirus clearly as like this. And also right hand, the yeast bacteria, okay, 200 kV applied, we can clearly observe live condition, live environmental yeast bacteria can be clearly observed like this. And next example is a particle of sunscreen particle distributed in the solution. Okay. So we can observe the sunscreen particles such as zinc oxide, some aluminum oxide, some particle distribution clearly. And right hand is the ink printer. The ink printer color pigment distribution can be clearly observed in solution like this. Okay. And next application is the electrochemical reaction. So copper plating reaction can be observed. On the e-chip, there is an electrode here, 2 electrodes applicable. Then we fill copper sulfide solution. Then voltage applied between 2 anode and a cathode like this. Then electrochemical and chemical plating is processed, is progress like this. You can observe this video, the process 10 times fast processing. We can observe the surface of cathode here, copper plating layer increasing And also, some of the small kappa particle can be growing up and growing up like this. Okay? As like this, we can clearly observe the chemical processing, electrochemical processing, and also live image can be recorded that on one view, right in view, here like this. Going to the liquid atmosphere, liquid environment condition, we can clearly observe the chemical reaction in electroplating like this. Okay, so as like this, I'd like to summarize as gas cell. Today I introduced the two types of environmental specimen holder. One is gas cell atmosphere. Okay, gas cell system here like this, gas tension up to 1 atmosphere and heating temperature up to 1000 degrees. Then simultaneously, in-situ observation and simultaneously we can observe the atomic resolution imaging. Almost 1 angstrom resolution can be observed. Okay? This is owing to the high stability, high performance aberration corrected technology. And also in-situ elemental analysis. Among the elemental or reaction, we can observe the elemental concentration, change in the elemental distribution, and chemical state analysis with combination with high resolution electron loss spectroscopy. So now higher sensitivity of EDS is very effective, and also high resolution combined with the cold field emission gun is very effective as well. Then this gas cell specimen holder can be applicable to catalysis and catalysis reaction and redox reaction as introduced today. And also liquid cell Poseidon is applied to our observation submerged with up to 3 liquid can be compatible, and temperature can be applicable up to 100 degrees Celsius. It is applicable to submerged observation, electrochemical reaction, and submerged living specimens such as biological or polymer, and also electroplating and battery reaction should be applicable as well. So as like this, a newly developed transmission microscope, aberration corrector microscope, JEM 300F2, and also environmental cell application is very exciting, and we can expect the good result with this kind of in-situ observation situation. Thank you for attention.
Thank you, sir. And the floor is open for discussion. Anybody wants to comment or have some queries, you can discuss with Okawa-san. Please, anybody who wants to ask, please raise your hand so that. Anyone? Anybody wants to ask some questions? Okay. Just wait. Let us see. Yes. Yes, we have one from IIT Bangalore. Please, sir.
Yeah. So I joined late, but so what is the magic for not losing resolution when you have these 3 micrometer liquid cells thickness? So what makes that possible?
So I have no example today, but we can expect almost 1.5 angstrom the resolution, even the 3 micrometer liquid thickness.
Yeah, so but how is that happening? Because 3 micrometers typically you should see nothing. It's liquid, solid, whatever, but right? So what is it that GEOL is doing? And
it depends on the element, but normally the liquid atomic number is not so high.
I see.
This is different from the metal or ceramics. Those are heavy elements, but normally the liquid is like water or something, relatively lower G number.
All right, thank you.
Okay.
Any other questions, comments? Okay, Dr. Okiawa-san, I have one small query.
Okay.
Now I work in electrochemistry. Now I find this work to be fantastic. So you have specifically shown how that reduction and oxidations in case of cerium and iridium, and then in case of copper, you have shown very clearly, which is exciting, very exciting. Now I have a small issue, small query rather. See, when you have small query, question.
Okay.
Okay, so let's say copper oxide situation. You have both the phases, those are appearing, that is copper monovalent and copper divalent, bivalent states, CuO as well as Cu2O, both are forming. Now, is it possible to capture that, how those formation takes place through this microscopy? Because I should be able to see that at what point, at what location this CuO is appearing, because first Cu2O will appear and then CuO will appear. But can I see that particular boundary?
Okay. Yes. Okay. As today, I have no data, but generally, in our experience, I can show example here. Sorry, my computer, a little bit slow response. Yes, we can identify the monovalence and divalence by the 5eV chemical shift.
Okay.
Then after acquiring the spectrum, we can apply the energy filter. So apply the filter to the 5eV chemical shift position. We can select only the monovalence elemental monovalence distribution and apply the 5eV chemical shift, higher energy position. We can select the bivalence kappa position.
Wow.
We can identify.
That is fantastic.
It is very easy, and applying the spectrum imaging of the iris analysis, and very effective.
Okay, great. Because this has a huge implication in electrochemical reactions,
Yes.
understanding electrochemical reactions.
Yes.
So that has
Yes.
huge implications.
Yeah, as like this here, you can see, if apply the white line of monovalence kappa and apply divalence kappa, 5eV energy shifted, we can apply the position of the elemental distribution.
Wow.
Chemical, so-called the chemical distribution analysis.
Great. Thank you.
It's a very exciting.
Yes, I do agree. Anyone else? Okay, if not, Dr. Okinawa-san will be available. You can contact him. Hopefully that is fine, sir.
Yes,
so because we have time constraints, so let us thank the speaker, and thank you for giving a fantastic talk, and it's an eye-opener for many of us. Thanks a lot.
Thank you.
Okay.
Thank you. Kallol.
So,
Kallol.
now we have.
Hello.
Okay, so
Yes.
How to switch the
Yes. Hi. Yes, I'm able to see.
Okay.
I'm able to see. I'm able to hear Professor Mukhopadhyay.
Yeah, actually, it seems that my video mode is not being allowed, being stopped by host, it seems. So if
No
I
issues.
sent
No
a
issues.
message, so I sent a message to Krishanu just to be allowed, but Krishanu I think is not available. But anyway, I can
No
speak
issues.
if that is audible.
You can actually speak and you can introduce.
Yeah. So let me. Who will be giving a talk
The
next?
next speaker, let us call.
Yeah. So it is Dr. Benjamin
Next
Miller.
is Dr. Benjamin
Yeah.
Miller.
Good afternoon, sir. My name is Deepak. I'm from
Yes.
IIT Gatan
Yes.
Business Unit, and I have a pre-recorded video of Dr. Benjamin Miller, since he's based from the US, and due to the time difference, I'll be broadcasting the video on his behalf, sir. Thank you.
Okay. Okay. Great.
Hello, my name is Ben Miller, and today I'm going to be talking about mapping crystalline regions during in-situ heating. And I'll talk about two different but related techniques for doing this with both TEM mode and 4D STEM. So first, I'm going to give a little introduction to 4D STEM, in case you're not familiar with this technique. So 4D STEM is a technique where we scan the beam along the sample as a normal STEM, but instead of just collecting the signal from your normal STEM detector, like you see here in the middle, we actually acquire an entire image of the diffraction pattern at every point where we scan the beam. And so this gives you a vast amount of information about your sample from all of these diffraction patterns, and there's a number of different ways that we can analyze these patterns to give different information about the sample. So what you end up with here is that for each pixel in your STEM image, you have a two-dimensional diffraction pattern. And if we continue to zoom in here, there's a lot of information that we can get out of these two-dimensional diffraction patterns in each pixel. And so there are many different ways that we can analyze one of these 4D STEM data sets. And I'll just talk about one particular way today, but there's infinite possibilities here. All right. So 4D STEM is the technique. STEMX is the name of the Gatan product that enables our cameras to collect 4D STEM data. And this allows us to do 4D STEM over large areas and do it quickly and easily. And really anyone can collect 4D STEM data sets with this STEMX product and one of our in-situ cameras. And there's a number of different techniques that we can use to process and analyze the data, as I said before, and this just shows you a selection of those. So for 4D STEM, visualization is essential. Really for all TEM, visualization is important. And one thing that I like to point out now these days is the size of images that can be obtained using modern TEM cameras. Modern monitors are far smaller than the largest TEM images. So if I just look here at a K3 image in blue and the size of my laptop monitor in green, you can see how much smaller that is. And it's really impossible to see all the details of my TEM image in a single view on the monitor. And even a 4K monitor, if I add that in here, this largest green rectangle, is still far smaller than a standard K3 image. And then with the K3, we can also do what we call half-X binning, or sometimes called super resolution, where we even make the image 2 times larger in each dimension. And so there's just no way to see all of the information in that image in a single view. And so this makes it somewhat difficult to analyze and understand your images if you can't even see the entire image on your screen. But this is where processing and visualization can be very helpful. So if I look at this image on the left here, I don't see a whole lot. If I looked at this in detail, zoomed in significantly, I would begin to see a bit more. But we can process this data to bring out the information that I really want. So here, I want to know what areas of this sample are crystalline, where are the crystal nuclei starting, and to what extent are they growing over time. And so I can map this data, and I'll talk more about this in this talk, but I can map this data to show where are the crystalline regions of this sample. And now if I zoom in on this small area here and just get the TM image, I can see that indeed this region has some crystalline areas. And if I overlay my map on top of that, then it becomes even a bit more clear and obvious. But this processing and visualization was really essential for helping me to understand my image and make some sense of the vast amount of information that's contained in this TEM image. 4D STEM data is really inherently difficult to display, right? There are 4 dimensions, and so of course it's impossible to directly display all 4 dimensions. So we're always showing 2-dimensional representations of some subset of the data. And if you look here on the slide, I have a number of these subsets of the data that I'm displaying, and some subsets are more representative than others. So if we look at this first one, there's not a lot that I can see here. That's probably not a good representation. But maybe here on the right, this is getting a bit better. And in each of these cases, I'm just putting a rectangular region of interest on my diffraction pattern and extracting the information from that region of the diffraction pattern. But this is just a very simple rectangular region of interest on my diffraction pattern. But we could do more clever things. So we could, for example, do an annular type detector. And so from that, we get this image on the left here. Or we could do mapping, as I just did for the TEM image. And we could somehow map the different crystalline regions of this sample similar, somewhat similar to an orientation map, although this is not an orientation map exactly, and I'll talk more about that as we go on through this talk here. But this representation is perhaps much more representative, much more informative than some other representations of this data. But inherently, 4D STEM data is difficult to display. So I've showed a couple of examples of these color maps that are generated from my data, and now I'm going to talk a bit about how do I do that using Python in GMS or digital micrograph. So GMS, Gatan Microscopy Suite, also commonly known as digital micrograph or DM, has many different visualization options. This is true for standard TM images, and it's also true for 4D STEM datasets. That we can do virtual apertures, as you see here on the top. We can align the 4D STEM data with the central spot. And so you see that here, we can measure all the shifts of the central spot over the entire field of view and align the data. We can do more advanced techniques like strain analysis or differential phase contrast, DPC. We can do binning of the data, or there's a number of different visualization options that we can do right within digital micrograph, and these are built in, easy to use, we hope, and quite nice. But there may be things that you want to do with the 4D STEM dataset that are not yet built into GMS. And so this is where it's very useful that GMS can be extended with Python. Starting in GMS 3.4, we have this embedded Python in GMS. And so we can extend the capabilities by either writing your own scripts or, especially for 4D STEM, using script packages that are already out there that other people have published. And one great example of this is Pi4DStem, written primarily by researchers at Berkeley in the US. And this Pi4DStem package allows you to do a number of other techniques like classification, which I'm showing here in all of these images. And you can also do things like differential phase contrast or tychography, doing something as simple as producing a maximum diffraction pattern, which you can see here in the sort of yellow and blue image here. There's a whole number of techniques that we can use by extending GMS using Python. And if you want to know more about this and how you can extend the capabilities of digital micrograph using Python, this is a great resource here. So today I'm going to talk about a script that I wrote myself in Python that's not part of any package online. This is just something that I have done over the past year to process 4D STEM data sets so that I can see the crystalline regions. So the way that I do this is that in each diffraction pattern, I just find the maximum pixel in that pattern. The maximum intensity in that pattern, find the angle, as well as the intensity of that pixel. And then I map that information as a color map. So the orientation, this angle, is represented by the hue of the color, and the intensity of this brightest pixel is represented by the brightness of the color. And so this, as you do this for every single pixel in the pattern, or in the 40 stem data set, then I get a very nice color map that tells me something about where are the crystalline regions, as well as where are boundaries between different crystalline regions, because different orientations or different different materials, different phases will have a different maximum peak position in the diffraction pattern. So what I found in using this technique is that it could be fairly easily extended to processing high-resolution TEM images as well. And the way that I do this is to take a TEM image and to split it up into a large number of windows, and I'm just representing a few of those here. And for each one of those windows, take the FFT of that window, and that FFT becomes like the diffraction pattern in my 40 stem data set. And so now, instead of a diffraction pattern at each pixel in my 40 cube, I have a diffractogram in each pixel of my 40 cube. And so now I can do the exact same technique as I did for the 40 stem data, where again I measure the angle and the intensity of this brightest pixel in the diffractogram, and I can map that over the entire 4D data set that again was generated by taking FFTs of small windows of my TEM image. One last thing that I can do with these data sets is to actually upscale the data in the spatial dimensions. And so I do this by combining interpolation of the data to expand it in the spatial dimension with binning the data in some other dimension. So for the 40 stem data sets, which I'm playing back here, I am summing in the diffraction dimensions while doing the interpolation in the spatial dimensions of the stem scan. For the TEM images that I'm showing now, I sum over time and interpolate again over the spatial dimension to increase the spatial resolution of the final maps. And this specific technique in doing these sums over time is something that I got from this paper by Lewis Jones in 2018. So if you want more information on that technique and why this is a viable procedure, you can look in that publication. So one of the great things about this processing, and specifically doing this Python processing within digital micrograph or GMS, is that you can do this during acquisition. And if you can do this processing during acquisition, that can really help you to make good decisions about what to do next. Often you need to know what's happening to my sample right now so that I can decide whether to change the experimental conditions or capture better data. And so processing this data live during acquisition can help me to make good decisions. And so here now I'm just playing back that data set that I captured live and processed live using this same Python code. So finally, I want to talk a bit about the relationship of these two similar techniques, mapping either with high-resolution TEM or with 4D STEM, and talk a bit about the limitations and benefits of each one. So they're, as I mentioned before, they're very similar, where in the HRTEM case, I just have one additional step where I'm taking FFTs of many different overlapping windows in my image to generate a 4D cube. But then I treat the data very similarly in the 4D STEM case and HRTEM. In both cases, finding this brightest point in the pattern and mapping that in color. So why would I want to do one or the other? Is one of them always better? And I would argue that there are good reasons to do both of them in different circumstances. So the best reason to use the HRTEM technique is for temporal resolution. High resolution TM can be very fast. For the K3 IS camera that I was using to collect this data, we can collect up to 150 frames per second at full resolution of the camera. And in this data that we're looking at here, this was only collected at 20 frames per second. But even at 20 frames per second, we can catch these particles crystallizing at different times. And so you see that in this video, that one particle crystallizes before the others. And using the 4D STEM technique, we would never catch these subtle differences in the crystallization time. Yeah, and so here you see that again, slowed down a bit. So the blue and then the red and then the green particles crystallize. For 4D STEM, the temporal resolution is much lower. So even if the camera or detector used to capture the diffraction patterns could operate at 5,000 frames per second, it would still take half a second for a 50 by 50 pixel map. So you would get these maps generated at 2 frames per second. And for a map that was equivalent to what you would get from the K3, that would take 4.36 seconds. So compared to the up to 150 frames per second that we could get using the HRTEM technique. So 4D STEM is between 2 and 3 orders of magnitude lower, slower for mapping than HRTEM. Now that said, that is just one of the considerations that I think are useful in comparing these two techniques. So while high-resolution TEM mapping is much faster, or can be much faster, the spatial resolution for TEM mapping is generally going to be poor. This is because you need to have a large area in each FFT to generate a good high quality FFT. And so you really end up with poor spatial resolution, where for 4D STEM, you can get spatial resolution up to the resolution of your probe. And with an aberration corrected stem, especially probe corrected stem, you could get very high spatial resolution. In the TEM case, you get delocalization of information because these FFT regions are overlapping. Then you get some delocalization of the information in the spatial domain. Also, the processing is slower for the HRTM technique because you have to process the image with FFTs. And in 4D STEM, you don't need to do any FFTs at all. So that provides much faster processing. In HRTEM, you also, and this is really important, you get a smaller volume of reciprocal space because of the parallel nature of the beam. And so in STEM, you get a larger volume of reciprocal space that you are sampling. And actually, if you are interested in that topic, there's a very nice paper from 2005 that I've cited here that explains the volume of reciprocal space and how likely is it that you will get fringes of a particular lattice plane in a TEM image. And then finally, to some extent, which approach you should use, TEM mapping or 4D STEM mapping, may depend on the microscope. And if you have an image corrected TEM, then maybe it makes more sense to do the HRTM mapping. And if you have a probe corrected STEM microscope, then probably it makes more sense to do 4D STEM. So there are a number of factors that go into this, and on the whole, I would say that in most cases, 4D STEM is going to give better results, but it really depends on what you want to do, and if high temporal resolution is critical, then TEM mapping might be the way to go. So to summarize this talk, I started out talking about visualization and how important it is to visualize information with the very large images and 4D STEM data sets that we can collect today. I talked about how Python can be used to map crystalline regions and showed that we can even do this live at the TEM during acquisition. And then finally talked a bit about the benefits and limitations of these two techniques for doing this sort of crystalline mapping. So if you have any questions, feel free to email me at benjamin.miller@amatech.com. And if you are interested in Python scripting, here is a helpful link for Python scripting in digital micrograph.
Thank you, sir. Thank you, everyone, for your attention. And Dr. Benjamin Miller is not available to take questions because he's based in the US, and due to the time difference, we had to record the video. So I would request you to please send your questions by email to benjamin.miller@amitech.com. Thank you.
Okay. Thank you, Mr. Deepak, for presenting this nice video lecture by Dr. Benjamin Miller. And I would request all who have queries or some sort of informations to seek, please send that email what Mr. Deepak has just now suggested. And he also, Dr. Miller also said this same thing. So thank you, Mr. Deepak, and thank you, Dr. Miller. Someday we'll catch up with you. So let's move forward. I think let's go to the next speaker. Next speaker is Dr. Syed Asif. He's a currently Managing Director of Industrial Nanotechnology Private Limited. He has over 30 years of experience in designing and developing nanochemical testing instruments. Before Industron, he was Director R&D at Bruker Nanosurfaces. He has completed his PhD from Oxford University, Material Science background, and hold Masters and Bachelors from Indian Institute of Science, Bangalore. So he has 22 patents and over 120 publications. He has won 4 R&D 100 awards. So let us welcome Dr. Syed Asif. Dr. Asif, I request you to concentrate, request to maintain the time. So I'm sorry to say this because we have other sessions. Please don't mind. And I'll put a buzzer as per the time slot given, and so that you get to know that when you have to end. So that I request you to give some time so that we can discuss your thing. Okay. So the floor is for you now.
Okay, thank you very much, Professor Mandal, for the nice introduction. I hope everybody can see my screen. If you have issues, please let me know. Greetings from Minneapolis. And today's talk, I'm going to talk about in-situ nanomechanics, basically studying the deformation mechanics of materials inside a transmission electron microscope or a scanning electron microscope. So, before I set the stage, go deeper, I would like to start with this particular example, which actually I presented many years ago at EMSI in person. Nevertheless, it's a pretty good example to start with. What I am showing over here is pillar compression, and that many groups in the world have done. And one observation they've noted is that when you reduce the size of these pillars and measure the strength, you can see that as you reduce the size of the pillar, the strength increases. This is a common observation, and originally been reported by Mike Uchik at the Air Force Research Lab. And many groups followed up that work and with many materials. And I've given a clear indication that as you decrease the size scale, the property that the strength particularly goes up. And there were many theories and models were proposed at that time. And Professor Bill Nix came up with a proposal that it is due to the starvation of dislocations. And during that time, we were developing in-situ TEM holder to do in-situ nanomechanics. We thought it may be a good candidate to put this thing into test. So here what I'm showing is a pillar, a nickel pillar fibbed out, and underneath you can see a flat diamond tip. And when you do this fibbing, you introduce a lot of defects. You can see these dark patches on this nickel pillar are basically dislocations. They are on the bulk of that pillar. And what I'm going to show you is that when you apply the stress on this pillar, you can see that all these dislocations are kind of moving out to the surface and disappearing, and making this material with less and less dislocations. This is totally different than what normally expect when you have a deformation. So the deformation induces more dislocations. But in this case, you can see as you apply stress, these dislocations moving out of the pillar and becoming less and less. So what's happening over here is that for the dislocation to multiply, it has to move a characteristic distance. And if it happens, if, for example, in this case, this pillar dimension is about 100 nanometers, and before it multiply, it disappears from the surface. And that kind of what is happening over here, which causes the dislocation starvation and ultimately gives you increase in strength. This is the one mechanism was proposed by Professor Nix, and we were able to prove it by doing this experiment in situ in TEM. So I thought this may be a good example to start with. So we have this power of observing deformation mechanics in situ that will allow us to understand the mechanisms that are involved in the deformation behavior of the materials. Okay, so what I'm going to talk about today is about the recent developments and the tools and techniques that are available to study this inside TEM or NSEM. So we have different holders for TEM, whether it is a FEI or GEOL or Hitachi. There are holders for that. that you can directly put inside the TEM and then do all these nanomechanical studies. We also have holders that that you can put it inside a CM, and it can do all this mechanical characterization inside the SEM. I'm not going to talk about those holders, the transducer that works with the biological microscope. So I'm just going to talk about only the TEM microscope as well as SEM microscopes. So the heart of the system, the technology behind is that you need to have some kind of a sensor, the force actuator, as well as the displacement or the strain sensor. So we use electrostatic force actuation, and we use capacitance-based displacement sensing to measure the displacements or the strain. So for the stress or the load, we use electrostatic force actuation, and we can generate up to 1.5 millinewton force, and we can measure displacement in the range of sub-nanometer. And the force sensitivity is kind of limited by the vibration isolations that you have in the system, typically about 200 nanonewton force sensitivity and less than 1 nanometer displacement sensitivity. So with this, we can kind of do a variety of things. For example, if you have a sharper probe, we can do nanorendition. And if you have a flat probe, you can do compression. And by using a wedge type probe, you can do bending experiments. And with some fixtures, which we call push-to-pull device, you can do tensile experiments. You can also direct pull experiments with these holders. And you can also apply a dynamic load to understand the dynamic behavior or the fatigue behavior of nanostructures. And finally, with the 2D transducer, you can also do tribology inside the TEM or the SEM. Okay. So I just mentioned that you can use this kind of a fixture, which is basically a push-to-pull device. If you want to do tensile experiment, for example, in this image that I'm showing, the gap of about 2.5 micron, within that gap, either you can have a nano wire or a thin film deposited around that in the gap. And then if you apply a pushing force, this part of this arm is fixed and this part is movable. So you kind of create a tensile force that allows you to do a tensile deformation of the specimen. So in the next slide, I'm going to show and present one particular example where a zinc oxide nanowire is being anchored in the gap. And you can see there is a kind of four lead connections. And through this connection, you can measure the resistivity change as you pull this nano wire. And you can see the gap is increasing here. So with this kind of arrangement, you can apply a known stress or strain, and you can also measure the change in resistivity as you do this mechanical deformation. So in the next slide, I'm going to show the plots where you can see we can convert the load and displacement into true stress and true strain because we know the dimensions of this nanowire. And then for a given strain, for example, you can load up to a maximum load that gives you a kind of a percentage strain applied onto the sample and measure the resistivity change by applying a current or by changing the voltage. So that gives you kind of a resistivity measurement as you apply the strain. So if you plot the strain as a function of this resistivity, you can see there is a 13 to 14% increase in conductivity when you have strains up to 4.25%. So what it helps you is basically you can do the strain engineering even for electronic materials like zinc oxide nanowire. And you can do this in situ in the TEM and have a good understanding of what is happening when you do this deformation. Okay. So similar thing with the same push-to-pull device, you can deposit a thin film of copper. And because it is electrons transparent, you'll be able to see through this. And instead of doing a quasi-static load, we can do a dynamic load, that cyclic load. And when you have a pre-crack in the specimen, you can observe along the crack tip what is happening and what kind of mechanism is happening in front of the crack tip. And it can do a cyclic load with in this particular case is about 40 micronewton force. And then we can also, what we can do is we can also kind of measure this crack growth as a function of the application of this oscillatory load. So here in this particular case, you can see that the crack is growing as you increase this time. If you have number of cycles going up, you can see the crack tip is also, and the length of this crack tip is also increasing. So you can measure this at different states. For example, if you spend about 20,000 cycles, we have measured about 130 nanometer increase in crack extension. And this crack extension also can be observed by measuring the stiffness because we are applying oscillatory force. We can directly calculate the stiffness. If there is a stiffness reduction, we know there is crack is advancing. So you have all the tools that we can use to precisely monitor this crack growth. And also we can directly observe what is going on ahead of the crack tip, what type of grain growth or plastic blending of this crack tip is happening. So you can do all of that inside now in a dynamic way. This is another good example that thought may be interesting. Okay, so now I would like to shift to tribology. We were able to do pretty nice mechanical studies, both tensile or compression or inundation. But to do the tribology applications, you need to have sensor which is capable of measuring forces in both normal and lateral direction. And with that, we were able to simulate this tribological condition inside a transmission electron microscope or the scanning electron microscope. Tribology is a field where it's very complicated to understand. Even when you assume a single aspirated contact, it's a lot complicated. So by doing this experiment inside the TEM, you were able to kind of understand the underlying deformation mechanism when you have a tangential force along with a normal force. So to do that, we need to have a sensor which is capable of applying force actively in both lateral and normal directions. So we do that through a MEMS transducer. And this transducer is capable of applying up to a millinewton force, and the stress or the displacement or the strain less than about a nanometer in dimension. So with that, we can examine, in this particular case, I'm presenting the results on a perpendicularly magnetic recording medium. This is it's a very important, technologically important material. What you see here is basically a stack of layers of material. You can see the columnar grains, and there is an overcoat which is protecting this magnetic media. And in this top view, you can see this nano grains, typically about 5 to 50 nanometer in cross section. And each grain in the kind of records a bit of information. And this mechanical integrity of this grain is very important. For example, when you apply a lateral force, if there is kind of a plastic bending or reorientation of this grain happens, basically what it means is the loss of data. So the mechanical interaction is very important, particularly so when you want to increase the data density. You need to reduce the fly height between the read head and the top of the surface. And this coating that protects this columnar grain is only about a nanometer, and they are made of dimer-like carbon coating. So mechanical interaction, our understanding the mechanical interaction is very important. That is the reason that we did this experiment inside a TEM. For the experiment, what we did was we deposited that stack of material on a silicon wedge, so that at the apex you have an electron transparency. Then you use a wedge type indenter, and then you slide up and down and observe what's happening inside the TEM. Here I'm presenting a video of that. You can see when I play that when the tip comes and makes contact, this is the stack of material. You can see the columnar grains. The tip makes contact, and then you apply. This is the load about 2 micronewton. It's a very small load, and then you can move in the lateral direction. You can measure the lateral force as well as the normal force, and you can see kind of a stick and slip action that is typically that we expect on a tribological condition, sliding condition. And if you look at in this plot, I'm plotting the lateral force as a function of time as well as the lateral displacement as a function of time. You can see when the tip is stuck, the lateral force gradually increases, and then when it slips, and during the stuck condition, you can see the displacement is, there is no displacement. When it slips, you can see a displacement jump. This kind of a stick-slip events that you can directly observe in the TEM. And in this particular case, at lower forces, we don't see any plastic bending of these columnar grains. But when you increase the force to 20 micronewton, you can see that some plastic bending of the columnar grains, it happens. And we kind of figured that with this particular type of experiment, you have to apply about 20 micronewton to have this irreversible plastic bending of this columnar grain. Kind of gives you what kind of forces this material can tolerate, and kind of also tells you what needs to be done to protect that. Okay, so I thought it would be a neat experiment to show. So what I'm trying to show is that you can do these tribological experiments, and very complex tribological experiments, and we can do that inside the TEM, directly observe and develop mechanism, our understanding of the deformation mechanisms. This is the same information that I provided before. At smaller forces, you can see the asperities are getting smoothened, but nothing much of a plastic deformation of this columnar grain. But when you increase the forces to 20 micronewton, the plastic bending of this columnar grain can make the data to bit of information will be lost. Okay, so this is one application. And this is another application where three-body kind of a sliding condition, where this particle, which is tungsten disulfide, is in kind of trapped between the substrate and tip. And when I play the video, you can see that exfoliation of this particle along with the friction changes when that happens. Kind of a direct observation where we can see under sliding condition what is happening to this particle, and we can have a good understanding of that. Okay, so again, this is another example on a geological material. This is olivine, is a mineral's Earth's mantle, in Earth's mantle. And at University of Minnesota, there is a group that trying to understand the deformation behavior of this olivine mineral. It's very important to understand. And they're trying to develop deformation processing maps. So we had the opportunity to collaborate with them. Here you can see the tip making and coming in contact with this olivine material. And we can do this at different loads. At loads about very low loads, about less than 100 micronewton, you can see you start to see this dislocation, nucleation when you increase the force. And as you increase the force, you can have more and more dislocation, kind of accumulation of this dislocation. We don't know that this is just a preliminary result. When you do more of this strain hardening, the material may become brittle and then may delaminate from the surface. Okay, but this is a nice tribology experiment that you can do inside the TEM. This is a good example. Okay. And now I want to move on to scanning electron microscope based nanomechanical study. With SEM, you have much more space, so we can put good manipulators or stages that allows to position the samples in different orientation. And if, depending upon the configuration that you have in SEM, whether if you have EBSD detector, you can go back and forth between the detector and map the crystallographic orientation, and then bringing back to the transducer. Here you can see the transducer with the shaft. You can put different types of probe on this transducer, and this is a modular transducer, which means that you can change the actuator basically, which allows you to put a force onto the sample. So there are different types of transducer that you have with the forces from 10 millinewton to about 3.5 Newton. So you can do a high load. You can do these experiments at much higher load. from 10 millinewton to 3.5 Newton. And you can see on the other end, you have, in this case, the three-axis stage. You can put the specimen on this stage and move in all X, Y, and Z direction. And also this transducer is mounted on another stage so that we can bring this transducer closer to the specimen, apply stress, and measure the displacement response or the strain response. Okay. You can also have additional rotation or tilt by putting a tilt and rotation stage on this three axis. So you can have a 5 degrees of freedom. And there are two types of configuration available. Configuration A, where the axis of the rotation axis is perpendicular to the tip axis, where configuration B, where the rotation axis is along the axis of this the probe that we can use to apply stress. And so I can see that clearly in this particular slide, where you can see the tilt action of the specimen holder. You can mount the specimen on here. You can see the specimen, and you can also see this rotation motion. So with this 5 degrees of freedom, for example, if you want to understand the orientation dependency on the mechanical property, in this particular case, this is on a calcite sample. You can rotate the sample at different degrees and then apply, for example, in this case, is inundation. You can see how the deformation mechanics is changing with the different orientation. Or in this particular case, this is a pillar. We can see the by rotating, we can go and see on all the direction what the deformation, how the deformation is progressing. So this 5 degrees of freedom stage is very important. And with the EBSD or some other detectors on in-situ, you can go back and forth between the detector and the force actuator, so that you don't need to take the sample out each time when you want to do this combined study of about if you want microscopy as well as deformation mechanics. So there are many kind of options available with the SEM holder. You can do tribology like I have presented for the TEM. You can also do on SEM, and you have options of heating the sample up to 1000 degrees C. So you can do high temperature study. You can do accelerated property mapping, and you can do all tensile or compression test as I presented with the TEM holder. You can also apply dynamic load or nano-DMA we call. You can do that, okay? And we can do that with the EBSD or a TKD type detector, and have a correlated understanding between the deformation mechanics and the crystallographic changes. So here in this video, you can see that this is a high throughput mechanical testing. This is a sharp Berkovich tip doing indents. You can see that you can do a series of a number of indents. For example, we can do up to 5 indents per second. And over an area, you can do this multiple indents. And from this low displacement curve, we can measure the hardness as a function of position, which gives you the mapping capability of the properties. Okay, so and we can also use the stages to get a profile, a line by line, to construct a 3D profilatometry. Gives you accurate information. For example, in this case, in inundation, if you have a pileup, you can measure this pileup height pretty nicely with the scanning arrangement. Also, we have fixture, which allows you to use the TKD detector. So, for example, if you want to understand the deformation mechanics of thin film, in this particular case, a different load under tensile condition, you can do that with the TKD detector. So there is a fixture we can directly use even if you have a TKD detector. Okay, and tribology I mentioned, where we can do that with a lateral force transducer attached to this shaft, which allows you to measure the lateral forces. So with the TM picointender for tribology, we can go understand atomic level interaction. With the SEM holder, we can go and understand single aspirity or multiple aspirity contact, much higher length scale. So here I'm going to show in the next video a scratch experiment done with this particular setup, where the tip is sliding along the surface. You can see for some critical normal load, the delamination of the film, and you can calculate what is the stress and the adhesion strength of this thin film in this particular example. you can measure both the lateral force as well as normal force inside the SEM. Okay. So I think I wanted to finally give you an idea of that you can do these experiments at higher temperature. In this particular case, you can do up to 1000 degrees C. You can heat the sample, heat the probe, and you can do these experiments. For example, this is a compression experiment done on a nickel-based superalloy, and you can observe the deformation mechanism. This is done at 1000 degrees C. You can see, you can observe the deformation in the SEM, as well as we can get this low displacement data, which we can convert into stress and strain. And this, you can do it up to 1000 degrees C. So comparing to room temperature experiments on the same material, you can see there is a change in deformation mechanism, whereas at room temperature at 400 or 600 degrees C, you can see multiple slip bands. At 1000 degrees C, it's kind of a major deformation appeared on a single plane at 1000 degrees C. So this allows you to do high temperature experiments, and there is much more coming out pretty soon from Bruker and Hysitron. So, but I think I understand that my time is up, so I have to stop over here. And in a nutshell, that we have tools and techniques that are available for you to do this mechanical deformation inside a TEM or an SEM. You can do all this compression, tension, or dynamic or bending type experiments. And with that, I will stop. If there is any questions, please let me know. Okay. That's all about it. Thank you. So if there is any questions, you can also contact me to my email address. Okay. I stop here.
Thank you, Asif.
Professor Mukhopadhyay is back. Chandrasekhar.
Okay, good. Okay.
Can I go?
Hello.
Yeah.
Hello.
Hello.
Hello. Yeah, am I audible?
Yes. Please take over.
Yeah, only thing, my video, I'm not able to open it.
That's okay. No problem.
Yeah. Okay. So, thank you. It's a good talk. Only last few minutes I could hear it, but as usual, this talk is very exhaustive and it's gives a insight that how one can do in the in situ mechanical testing and what is the micromechanism takes place. I'm sure there will be lots of questions. I think we can take a few questions quickly. Let's see if there is any question. I think Krishanu, one or two questions we can have it, no?
Sure, sure.
Yeah. Dr. Shahid Asif, let us see that if there are any questions.
Pawan wants to ask question. Pawan has raised hand.
Yeah. Thank you. So very impressive talk. I just wanted to actually I have two questions. So let me see if I can slip in both of them. So this PTP devices, what is the actuation mechanism? Is it resistive heating or?
No, it is basically a mechanical push, but because one angle is fixed, other angle is moving, you kind of convert that into a tensile.
Okay,
so you have a mechanism where you can push or pull. Sometimes you wanted to put thin film, so it's kind of a mechanical. The actuation is through electrostatic force actuation. There's no thermal actuation.
Okay, all right, yeah. So all right, good. Then so in this magnetic hard drive thing, I didn't see any dislocations or anything when in the active layers when the deformation was happening. Is it because it's a
Yeah, I think we saw bending, but I don't think we did a pretty thorough study on at a higher magnification. So it was evident enough that there is a irreversible plastic bending happening. So this was collaboration work with an anonymous source, so we can't go much deeper into that.
All right, thank you.
Okay. Good.
Dr. Asif.
Yes, Professor.
Hello.
Yes, yes.
Yeah,
Sir.
yeah. I have because I missed the much of your lecture, but I have one question. When you record the data in the nano indentation curve, you get that strain burst, and this burst may come because of dislocation, because of shear bands, because of phase transformation, because of cracking. Now, can you differentiate and tell us to our students as well that what is the basic or fundamental differences in the strain burst in each cases, and whether both can play together or whether one at a time, something like that, if you can throw some more light from your experience.
Very good. Actually, the whole thing on in-situ nanomechanics, we started to understand exactly that. We call it pop-in behavior when you do this low displacement measurement. And the very first experiment that we did with aluminum grain, I think this was published in 2005 in Nature Material. I usually have that video, but I forgot to put that in this particular stack of slides, where you can see when you make the tip contact with the sample specimen, you can see underneath the with the jump in the low displacement curve, you can also see the direct nucleation of the dislocation. So we can directly observe that. Okay. So by doing that inside the TEM, we have a direct verification that the burst is due to the dislocation nucleation. Okay. When before we had this capability, we were also able to observe the difference in deformation mechanics by putting an acoustic emission sensor and processing the data that comes out of the acoustic emission sensor, whether it is due to a fracture event or it's due to kind of a dislocation multiplication. So there are combination of techniques that you can use to kind of deconvolute to what is it due to, whether it is due to a crack or just the dislocation, nucleation and multiplication. TEM directly helps because you are seeing it, what's happening as that happens. But when you don't have that in-situ TEM capability, you can have additional, for example, acoustic emission sensor to kind of deconvolute that. Okay.
Okay. Thank you. There is any other question? Any comments or suggestion? Okay, seems to be that there are no further questions. Okay, so let us thank Dr. Sai Dasi for a very interesting lecture and very insightful lecture. This will always help understand the nanomechanics and also nano deformation in the in situ electron microscopy mode. Okay, so thank you, Dr. Asif.
Thank you very much.
Thank you.
Just to, sorry to disturb, Dr. Asif, please do not leave. The next session,
I got it.
Yes, you are also one of the panelists.
Yeah, I'll be there. No,
yeah.
Okay.
Go ahead.
So now I think this session is.
Hello. Professor Mukhopadhyay?
And some interactions were also there. I am sure there will be many more interactions once all the lectures are over and the participants are a bit free.
Yeah, no,
so with this, I will.
Hello.
Yeah.
So now we will have
yes.
small poster session. The poster presenters will be allowed to present their posters.
Okay.
Yeah.
So I will start calling the poster people.
Yes, the first person name is Devarshini Samantare. Maybe let me check whether she is here or not.
Yeah. So
now let me check it. I'll allow. Yes, she is here. So I'm making her. She can now present. Devarshini, you are there?
Hi. Controlling polarization through defects in silicon integrated barium titanate.
Yeah. So
is Samantha available?
Yes, sir, I'm available. Should I share my screen?
Yeah, so you will get
Yeah.
maximum
So
2-3 minutes to present and then some
Okay,
questions.
sir. Okay, sir. I hope my screen is visible now.
Yes, yes, but you have to present something.
So, good afternoon all. I am Devdarshini and today I'll be presenting controlling polarization through defects in SI integrated barium titanate. So, as we know, barium titanate is uniaxial.
Devdarshini, your screen, nothing is visible.
Okay, okay.
Now it's visible. Go ahead.
Okay, sir.
What happened? You closed it?
Is it fine now, sir?
Yeah, but the presentation is okay now.
Okay.
Yeah.
Okay. So, as we know, barium titanate is uniaxial ferroelectric material which has polarization along C-axis. And depending on the orientation of C-axis with respect to the substrate, it can find many application in memory device and other integrated photonics. So earlier study shows that if we grow barium titanate epitaxially, we can actually control the orientation. And the system that we have chosen here is barium titanate, titanium nitrate, and silicon thin film. A temperature-dependent XRD study shows that when we have anti-side defect, anti-side defect could be responsible for the outer plane orientation in this thin film. Further, in this study, we have used aberration-corrected STEM to understand the structure and chemistry of this SI integrated system. As we can see in the figure 1, we have head-up STEM image of barium titanate film grown along 001 zone axis, and we can see this alternate brighter and darker contrast, which can be which corresponds to barium and titanium atomic columns respectively. And when we so it clearly suggests that we have a barium rich sample, and when we do a Bragg filtering, we can clearly see that we have anti-side position that is clearly identifiable. Further, we have gone ahead and done peak pair analysis, which, as we know, is a real space technique unlike GPA, and we use this technique for strain analysis. So here we clearly see the anti-side for the anti-side. It clearly shows the anti-side defects, and we can see the domain size ranges from 3 to 4 nanometer in these cases. And further, to find out the displacement of the TI atom in this particular sample, we have used a home-built algorithm, as we can see in the figure 2. And we can clearly see the magnitude of displacement of TI atom varies from 0 to 50 picometer, and the right-hand side image shows the corresponding polar plot. And we see that it is more or less symmetric about 0 degree. So the conclusion that we take from this study is that although we have tetragonality, which is out of plane, but the displacement of TI atom is more or less in plane. So this quite clearly indicates that we have a less symmetric system structure than tetragonal, and this can be possibly attributed to the defects that is present in the sample. Further, we are trying to understand through PPA analysis, we are trying to understand the polarization, and we have come up with the hypothesis of defect mediated polarization in this silicon integrated system. Thank you, sir. I'm done.
Thank you.
Okay, thank you. Just wait for questions.
Okay, sir.
Please, if there is any question, please. The paper is now open for discussion. Okay, can I ask a question?
Yes, sir.
Hello.
Yes, sir.
Yeah, you have done head-up STEM.
Yes,
Yes.
sir.
And instead of that, if I do the straight thin film kind of these experiments and do the high resolution electron microscopy, what will be the difference and why we cannot use that technique?
Okay, sir. Sir, here in head of stem, the intensity that we see, it almost goes as Z square. So it is quite directly interpretable. But since in the normal high resolution TEM image, that is, we cannot directly interpret because it doesn't follow any, there is phase involved. So that is not directly interpretable, just like stem.
But through simulation, it should be possible, no? Through simulation technique.
Through simulation, it should be possible.
At various defocus condition,
Yes,
you can
yes.
simulate and then you can match.
Yes, sir, that
Right?
should be possible.
So what is that electron microscope you have used here?
Sir, here we are using FEI Titan 300 kV.
And aberration corrected?
Yes, we have aberration corrected.
And what kind of aberration corrected? Probe and image both?
CS corrected. No, sir, only CS corrected.
Okay.
Yes.
Okay. Thank you.
Thank you, sir.
So if there is no further questions, I hope there is no other questions. So we'll thank Samant Rai.
You can just remove your presentation.
Okay, sir.
So Dhananjay, can you just start your thing?
Yes, sir.
Yeah, the screen. Diversity, please.
Okay.
Yeah. Okay.
Sir, is it visible? The poster?
Yeah.
Okay. So my poster topic is on in situ electron backscatter diffraction of stainless steel 316L. Basically, this is a austenitic stainless steel with carbon content having 0.03 weight percent, and it offers high tensile strength and good ductility, and it has also excellent corrosion resistance. My objective is to study the evolution of microstructure and texture with the deformation of stainless steel 316L and simulate it using crystal plasticity fast Fourier transform, that is Damask. This was my in situ sample, which was deformed at a strain of 5%, 10%, 20%, and 40%. So as a result, we got this is the inverse experimental inverse pole figure map. At 5%, we can see the twin starts initiating, and at around 10%, twin bundles can be seen here. Similarly, I tried to simulate it using Damask, and again, I found that around 5% twin starts initiating in some of the grains, and again twin bundles can be seen around 10%. This is the kernel average misorientation map. Uh, as the increasing. This is the CAM plot, which shows that 40% deformed sample has the highest value. And this is the CSL deviation, which is number fraction versus the deviation from the sigma 3 grain boundary. And again, we found that for the 40% default, it is the highest. This is the misorientation profile. We see that at 60-degree misorientation, we saw twins on 111 plane. This is the von Mises strain distribution map, which we got post Damask post processing. So, in a nutshell, we found that the deformation of the stainless steel 316 reveals that the twin starts nucleating at around 5% strain, and at the higher strain, we got the twin bundles. And the misorientation profile depicts that at around 60-degree twin misorientation, twin is formed about 111 plane, which is the closest backplane. Thank you. Have a nice day.
Okay. Thank you. Thank you, Dhananjay. Let us have some questions. Is there any question for Dhananjay?
Let me check. There's a question from Somya. What is the possible reason for variation in IPF orientation? CPFFT from experimentally deformed sample. Say 10%. Dhananjay, can you answer this question?
Sir, what is the variation?
What is the possible reason for variation in IPF?
Can you repeat, please?
What is the possible reason for variation in IPF orientation using CPFT from experimental deformed sample? So you have done simulation, right? What is the variation from simulation and experiment?
Right.
Can you answer the question?
Okay, if you are not very clear, leave it. Are you going to answer? Hello?
Yes, sir. We saw at around 5% in both experimental and simulation. That twin is initiating around 5%, and at 10%, we saw twin bundles. Yeah, there is variation. I need to change the parameters, I think, like for the Damas simulation.
Okay. What is that equipment you have used? You might have missed it. That to get your experimental results.
Yes, sir. What is the decorum?
Equipment. What is the model?
Okay. Yes, sir. Yes, sir. We for experimental, we in situ, like on SEM, installed in situ, we use to deform the sample.
What is that SEM model? I'm asking.
Okay.
That MEC and supplier.
That is
Hello.
Geol from Japan, like.
Yeah, Geol supplies lots of SEM. No, which model it is? You are not sure.
I have to see, sir. I'm not sure.
Yes, forgotten. Okay, that's okay. I think let us thank Dhananjay.
Thank you. Thank you, sir.
So, Professor Mukhopadhyay, Professor Mandal is back.
Mandal, welcome.
So, next person is Khushbu. Khushbu, can you start sharing?
Yes, yeah, sir. Khushbu, next is Khushbu. Yeah, Khushbu, please go ahead.
Dr. Mukhopadhyay.
Yes.
The SEM tensile test was done using Isotron. Isotron test mechanical testing stage.
Okay.
That is what is there at IIT Kanpur.
Oh, I see. That's good. But student was not able to tell what is that model of SEM. Maybe he has not remembered, or he may not have looked into it.
He would have not taken note of it because it is there sitting inside. And some of the senior students who help in running the experiment, they will be actually handling, and these people only come when their results are running. Okay, that way you would have not taken note because it is inside.
Yeah.
Okay.
Yeah. Right. Okay, Khushbu, are you ready?
Hello.
Khushbu, please go ahead and present.
Okay, sir. Good evening, sir. My topic is phase transformation of silver copper alloy nanoparticle embedded in nickel matrix. So my objective is to see the allowing and melting of these nanoparticle. Lot of studies has been done where they have chosen the matrix which is not miscible with the nanoparticles, but here we have make an attempt to make one of the phase of the particles to soluble with the matrix. So we have the nickel which is form a complete solubility with copper and with the it shows miscibility. we chosen the 3 different composition of silver, copper, and we embedded in nickel matrix using the Mel spinning route. So this is Equidus projection where you can see silver, copper, nickel triangle, where it can show that silver and copper forms.
I think it has gone off actually.
Network.
I'm not able to see it.
No, nobody is able to see. I think it has gone off. A network problem.
Okay.
So shall we go for the next one? We come back then.
I think that will be better without losing some time.
Yeah,
so
yeah.
let us call next.
So Rupam.
Let me see who is the next. I think Rupam Jain. In-situ tensile deformation of silicon doped Fe50 minus X, manganese 30, cobalt 10, chromium 10, silicon X, high entropy alloy. Yes, Mr. Rupam.
Yes, can you see the slides?
Yes, we are able to see. You can make it full screen?
Yes, sir. Yes, now it is there, right?
Yep.
Okay, so hello everyone. And this project is basically dedicated to... Has someone played the video?
Yep, everybody is able to see.
Yes, so the purpose was to study...
You have 3 to 4 minutes. Huh?
Correct. Yeah. So in this study, we are going to learn something about the silicon doping, which is done in the very conventional and very initial proposed transformation-induced plasticity high entropy alloy, where we are having plenty of transformation from FCC to HCP. And let us see what happens if I introduce silicon as an interstitial element in this conventional trip high entropy alloy, which has been proposed by Rabe et al. From their group. So basically the idea, and this can also alter the stacking fault energy of this material, and that is how we can change the deformation mechanisms from transformation to twinning. And then if I further increase the stacking fault energy, then it is possible that we get the planar slip, and further increase gives us the multiple slips starts getting operative because of this change in stacking fault energy. So this is what our initial microstructure was. So here we have the single phase, which is having more of mostly the high angle grain boundaries, and surprisingly, compared to the trip high entropy alloy, it is which is having 2 phases. It is just showing the single phase. So here we can see that because of silicon, this phase has got stabilized, and there is no segregation of any of the elements, alloying elements. And here we see from wet chemical analysis, we got to know the exact weight percent of silicon, which is something like 0.2 weight percent in the alloy. So next we see that this, when we test it for the mechanical testing, here we see that it is showing tremendous, very high ductility, like 80% ductility we could get. And when we see the strain hardening, which is quite sustained throughout the deformation, and here also we can see in the Cox-Mackey curve on the right side, this is kind of plateau, which is indicating some other strain hardening mechanisms which are getting operative during the deformation. So to further understand, we carried out this in-situ deformation, where we get to see that these grains are deforming more by slip from this observations. And here one other thing we can see is that the CAM, basically the intragranular misorientation, is getting concentrated at the grain boundaries, which is indicating that it is getting deformed mostly by planar slip, because if multiple slips are getting operative, then we get to see the misorientation in the entire grain, not only at the grain boundary. So this is something which we can see from this in-situ experiments, which is deformed for 10, 30, 65. Yeah, I'm seeing just these this thing. And we can see that texture is getting evolved towards 111 fiber, where you can see blue and red grains are in dominance as we keep on deforming. So further to understand all those things, what exactly is happening inside, we get some these slip trace analysis we performed, and here we see that whichever the blue grains which are basically parallel to 111 direction, which are parallel to 111 planes, which are parallel to the tensile directions, are basically getting deformed by multiple slips. Here you can see these slip traces can be seen, which are showing multiple slips along those directions, and other grains are more or less are getting deformed by simple planar slip. And to many things which are not visible from this resolution limit because of this EBSD kind of EBSD characterization technique, we further went on doing some electron channeling contrast imaging. Here we get to see some fine bundles of twins, which can be verified from the slip traces also. We are seeing along those lines, we are seeing these fine bundles, which are, some of them are intersecting and some of them are very fine in nature, which is signifying that yes, this is something, the mechanisms which is getting operative and which is resulting in the sustained strain hardening, which is imparting a lot of ductility, which is nearly 80% as we've seen in the stress strain curve. Again, to understand all those mechanisms, we took on to do some simulations like viscoplastic self-consistent simulations, which are very quick.
Rupam, you have 1 minute time left.
Yes, sir. Yes, sure.
Please
And,
finish stuff.
Yes. And also full field simulations. So here we get very good correlation with the stress strain curve, and very good correlation of the texture evolution. This is the first line you see is the experimental curve results, and the second and third are the basically your simulations results, so which are very matching very nicely with the experiments. And here also, with the help of full field simulations, we can match grain to grain how they are rotating towards which orientation they are rotating, and this is how we are approaching towards the virtual experimentation, which is the future in this kind of microscopy, that with the help of simulation itself we can achieve these things, and no more experimentation of these is required for these details. So further correlation we are trying to do with the strain accommodation, particular slip activity, and twin systems which are getting operative, and this is how we are approaching. And thank you very much. Over to you, sir.
Okay. Thank you. Thank you, Rupam.
Okay, sorry, Professor Paul. Okay.
Yes, sir.
Yeah, thank you, Rupam.
Yes,
but let us have a few questions. So, everybody is open for discussion. Any questions immediately? Quick question. Okay, Rupam, I have one question. Hello.
Yes, sir. Yes, sir.
Hello.
Please, sir.
Hello. Yeah. I have one question that you said, what is the role of silicon? So where the silicon goes?
It might be going into interstitial, but I'm not sure about
Are
it.
you sure? Are
No,
you sure?
No,
Silicon
sir,
doesn't go to interstitial.
Yes, sir. I'm not very sure what exactly this silicon is going, where exactly it is going.
Because I noticed that you are talking about interstitial silicon. Silicon
Yes,
size is such that it cannot go.
Yes, exactly.
Now,
People have studied. Yeah. Yes, sir. Yeah.
Yeah. Please look into it. Now, the silicon increases stacking force or decreases?
In steels, trip steels, people have seen it reduces actually, but I don't know why it is stabilizing the phase. Because if it is reduces the stacking fault energy, then we should see HCP and FCC both. But now we are seeing that it is having just the gamma phase. So we suspect that it might be increasing the stacking fault energy. And in some publications also we have seen that they have claimed that it has increased the stacking fault energy. The exact mechanism is not clear to me.
Okay. So by this technique, is it possible to find out the Berger's vector of this slip system and dislocations?
We can
through your technique.
Which technique?
Can you find out Berger's vector of the dislocation which is leading to this slip?
I guess no, we cannot determine.
You cannot, is it?
Yeah, we can just know which. We can just see the slip systems, like the slip traces and just the slip plane, not even the direction of it.
Professor Mukhopadhyay, can I have a small query?
Please, please.
Okay, Rupam, this is really good work actually. I must say that this is a very good work.
Thank you very much.
A small amount of silicon can do wonders. Now coming to the other aspects. Now you have your strength curve shows around 150 or 160 or 170, around 200 MPa yield point. And then your tensile strength has gone to around close to 760, isn't it?
Yes, sir.
So now IF steel also gives that much of tensile properties. Of course, it's strain hardening doesn't is not that much significant, but IF steel is also close to that. Why do you need so much of alloying elements?
At this point, I'm not able to comment on this.
Okay, so please think over it, because there must be some specific use for this particular alloy. Because IF steel also gives the same property, only except that extra strain hardening what you are getting.
Yes,
that
but
is not that is absent there.
Ductility is quite high in this case.
IF steel also you can get 60%.
Oh.
With so low alloying elements, there carbon is in ppm level, nitrogen is ppm level, and only you have little bit of titanium or niobium.
Okay.
So there are nothing in fact in that particular steel.
Okay.
So you got my point. So the query is you should think why you should need so much of alloying elements, just to gain this extra strain hardening factor, or there is some other specific use. Okay.
As we see, sir, there are like the fine tuning of this composition can lead in quite a different changes. Like if we
see, Rupam, the factor is not what fine tuning you are doing. The major thing is no industry accepts 30% manganese.
Yeah, correct. Correct.
And if you have that much of alloying elements, there must be improvement in the strength level. But the strength level, what I am seeing here, it's same as IF steel, because your design factor is yield point.
Yes,
you got my point. So you have to understand that part, because that, see, these alloys are extraordinary, extraordinary thing, because it gives us a huge opportunity to understand phase transformation behavior, but which also should find their specific application. It must have some specific applications.
Definitely, sir.
Look for it. Okay.
Yes, sir.
So that is my small suggestion.
Sure. Thank you very much.
Okay, let us move on. I think Khushbu is back.
Okay, so next talk is, let me just tell you. I think, can we get back to Khushbu?
Yeah.
Khushbu, are you there?
She's there. Khushbu?
Khushbu, are you
yes,
there?
sir.
Okay,
sir, give me 2 minutes, sir.
Okay, so then let's keep it ready. Please keep it ready. So we are going to Vivek Kumar Sahu in order to save time. Okay?
Yes, sir.
Okay, Vivek.
I'm sharing my screen.
Okay, great.
So is it?
Hello?
Khushbu, you wait. I think Vivek is presenting, and then you present.
Okay. Is it visible, my screen?
Okay.
Yes. Your time is 3 minutes, 3 to 4 minutes. Don't spend that much more than that.
Is my screen visible, sir?
Yes. Do.
Yes.
Okay. Hello, everyone. And today I am going to present on the micromechanism of damage evolution in commercially pure titanium using in-situ study. Here we use the tensile stage, that is the Gutton company, and we put this tensile stage in the FEACM, and we deform this sample in front of the EBSD CCD camera. So as we know, ductile damage occur by wide nucleation, growth, and coalescence. So wide nucleation occurs due to incompatibility. So here we will see how crystallographically play important role in the incompatibility. Then we'll see how growth is happening, and then coalescence. So we will come to the directly our methodology. So to do that, what we did, we first deformed this sample till post necking, and then we polish the sample for the EBSD preparation, and then again we deform for the 0 step, 0.15 mm and 0.44 mm. So, and before that, we also did the tomography, and we found that the fracture sample has the mean radius wide is 8 micron and mean sphericity of wide is 0.5. And this sample has the split, CP titanium has the split TD texture, and it is deformed with 0.2 mm. And after deforming for this 3-step, we did the IGMA, means we choose the 3 different cases and we try to see how damage is occurring. Before that, I would like to draw your attention, means what slip system is activating in this SCP titanium. So for that we did the IGMA analysis. So what suggests IGMA? When you deform the sample, slip plane and direction get rotated along the particular axis. That axis is called the Taylor axis. And for a particular slip system, it is unique. Like if a prismatic slip system is deforming, Taylor axis will be the 001. And if basal slip system is deforming, Taylor axis will be 1/100. Like that, each Taylor axis in the inverse pole figure, there will be the specific position. So now if any grain is deforming, so inside the grain there will be the misorientation, and we try to plot this misorientation, this IPF map, and we will see which slip system is getting activated. So let's assume a case 1. So in case 1 we can see that there is the wide, and we name this, and this wide from the IPF map we found that this is at the grain boundary, and in grain A we can see there is a lot of color gradient, and in grain B it is lesser. And from the trace analysis we found that this is the prismatic plane as well as this green color is 10/10 plane. And in the grain B we can see that there is a not much of slip traces. And so what slip system, I mean, since we deform this material till post necking, so obviously there is a sub slip system has activated very largely. So for that we did the IGMA analysis, and from the IGMA analysis we found that in grain A, which is this, there is the dominated prismatic slip system, and in grain B there multi-activated slip system, means all type slip system is getting activated. So from here we can say that B is hard and A is softer one, and because of that their incompatibility is arises. And further we can see that there is the coalescence occurring at the grain boundary by the shear mechanism, and growth along the grain boundary as well as here due to slip localization. And from here we can also see that when there is a deformation is occurring, dislocation coming on the surface, and because of that this step is getting formed. So for that we try to visualize what is happening inside the sample. So we try to understand from this mechanism in grain A, where prismatic is dominated, where in this case slip dislocation is this black color is going on to the surface, and their pileup is occurring, and this prismatic slip system has high Schmidt factor. And in grain B, which is hard orientation, where due to pileup of the dislocation twin is forming. So thus we can conclude that why their wide nucleation is occurring, because of this hard and soft incompatibility. Further we can come to the case 2. In case 2 we can see there is the wide, and it's on further deformation we can see that there is slip traces. This blue color is the prismatic and green color is 10/1. So here I think cross
Vivek,
yes,
Vivek, you have 1 minute time left. Please complete.
And further we can see this is again much revealing. So this is happening because growth is happening because of the prismatic and pyramidal type dislocation, which is nicely explained in this schematic. And in the case 3 we took the 2 wide and one at the grain boundary, which is here, and another inside the grain, and we can see that this is getting coalescence along 1/2 2. And further on deformation, we can see that here it is going inside the means from surface, and here we can see that there is the localized slip band, and this is slip band is the prismatic, and this one is the pyramidal type slip band. And further on deformation, we can see that there crack on the prismatic slip band. So from here we conclude that prismatic is dominating for the crack than pyramidal. Thank you.
Thank you, Vivek. Anybody has any query? Okay, if nobody has, I have small query, Vivek.
Yes, sir.
You talked about nucleation of those failure points, isn't it?
Yes, sir.
Okay, so what's the criteria for the failure?
So, like in ductile metal, first plastic deformation occur, and then failure occurs. So,
but that time, so is it a void coalitions? That's what it is forming at the center, or is it some other thing?
Sorry, sir. Center. Means it's
generally in ductile metal, the usual mechanism is a void coalescence, and then those voids actually connect, the ligaments break down, and
yes,
then you have that cup and cone type failure. Now here I could see that the small failure point is appearing, which is nucleating. Now what's the mechanism of that nucleation of those failure points?
Like, sir, in this case, what we found means here wide nucleation is occurring at the grain boundary. So because of if we see here in this case, here this is much more, this grain is deforming much more than this one. So there are incompatibility getting arises, and because of this incompatibility at the grain boundary, they are wide getting nucleated.
Okay, good.
Yes, sir.
So I think since we don't have much time, we cannot extend. So let's thank the speaker, Vivek Kumar Sahu. Okay, Vivek, thank you.
Thank you, sir.
So let's get back to Khushbu. Okay, Khushbu, you are ready?
Yes, sir.
Okay, please share your screen and make it a little bigger, because I think in one slide you have put everything. So you just make it a little bigger. Is it possible, or this is covering the entire screen?
Sir, is it visible, sir? My screen.
Yes, visible, but letters are small. So that's what, because you have put everything in one slide. So that's the situation is coming up. Okay, no issues. You can continue.
So, okay. Good evening. My topic is phase transformation of silver copper alloy nanoparticle embedded in nickel matrix. So basically, our objective is to prepare a multi-phase nano alloy particle where one of the phase should be soluble with the matrix, whereas one of the phase should not be miscible with our matrix. So for that, we have chosen the silver copper system, which is embedded in the nickel matrix, prepared by the melt spinning route. So we have chosen the 3 different composition in order to understand the effect of matrix onto the nanoscale particle. So first is the silver copper nano phase diagram. Here we can see we see the liquidus projection where the silver copper forms a eutectic phase diagram at the equilibrium, and where the silver and nickel forms the monotectic case, and the nickel and copper forms the isomorphous system. So as the temperature increases, the miscibility gap moves towards the nickel terminal point. So further, in order to understand the microstructure and the morphology of nanoparticles, we have done the TM study. The first one is the first composition is our hypereutectic, where we have seen only the pure nanoparticle, which is homogeneously spreaded over the nickel matrix. And in the next case, we have done it for the eutectic case, where we see most of the particles are single phase nanoparticles, and few particles are biphasic in nature, but the amount is very less. And the third is hypereutectic case, where majority of the particles are biphasic in nature and very less amounts are particles are single phase nanoparticles. So further, to understand the alloying effect of the nickel matrix with our nanoparticles, we have performed the DSC. In the first case, for hypereutectic case, we have seen the single exothermic peak, where after the number of cycles, it shows that as the peak area increases. However, the melting temperature is more or less close to the pure silver element. So we have concluded that this is the pure silver nanoparticle. And next we did the cyclic DSC for the eutectic case. Initially we got two peak at 917 and 962 with 52 degrees Celsius. As the number of cycles increases, the first exothermic peaks get vanished as the number of cycles increases, and the second peaks get more prominent. This indicates that the majority of the range of the particles were there initially at the matrix. So as the number of cycles it increases, this smaller particles get dissolved into the bigger particle, and it gives the prominent peak. And the third, in case of the hypereutectic case, we have seen the two peaks. After the cyclic DSC, the peaks were still the same. There we haven't seen any kind of changes. So further, to understand the kinetics of these nanoparticles, we have chosen the hypereutectic case, since in DSC we haven't seen any changes. So we have chosen the hypereutectic nanoparticles, where initially at the room temperature we obtained the two-phase nanoparticle of the silver and copper nanoparticles, where at 200 degrees Celsius we won't see any kind of changes in the morphology of the particles. After 300 we see the silver nanoparticles, the phase fraction a little bit increases and the copper phase fraction is a little bit decreases. And at the 350 degrees Celsius, close to 350 degrees Celsius, the whole particle get transformed into the single phase nanoparticles. And as the temperature increases till 900 degrees Celsius, the whole particle get transformed to the liquid. So in order to understand our experimental data, we have done the theoretical calculations, where we have plotted the pseudo-binary system, nano pseudo-binary system, and their property diagram. In case of eutectic nano pseudo phase diagram, as the red dot indicated that at the room temperature we have obtained the silver, copper, and nickel phase matrix. And as the temperature increases till 950, it forms the copper get dissolves into the nickel, as well as silver is also getting the smaller amount of silver is also getting dissolved into the nickel. And after 950 degrees Celsius, the whole silver nanoparticle get transformed into the nickel with nickel and in liquid form. And it shows that after 950 it remains the liquid plus nickel matrix. Whereas in case of hypereutectic nanophase diagram, it shows that at room temperature silver copper nanophase particle with the nickel matrix present, and as the temperature increases, the copper get dissolved into the nickel and it remains the silver with nickel matrix. And as the temperature increases, which indicated by the red dot here, at 950 there is small range of area where the silver get transformed to liquid with nickel, and as the temperature increases, it again becomes the nickel.
I think it's in 1 minute time we have to conclude. Okay, so you have taken more than 5 minutes.
Okay, so
please conclude.
So this So in conclusion, sir, we have obtained the microstructure of the hypo and eutectic nanolites, which exhibit the single phase nanoparticle, and in the case of the hypereutectic, we have obtained the multi-phase nanoparticles, and we have done an extensive study on the hypereutectic case in order to understand the alloying effect between our matrix and the multi-phase nanoparticles. Okay, thank you.
Khushbu. And any queries or comments?
I will ask question, Kallul.
Yes, please.
Khushbu, it's a very nice presentation, and I think it requires more time than to understand everything. But just a basic question. when you get the nanoparticle, what sort of interfaces do you expect?
Sir, can you repeat your question, sir?
When do you get these nanoparticles embedded in nickel matrix?
Yes, sir.
What sort of interfaces do you expect? Did you follow the question? Hello?
Professor Mukhopadhyay, your voice got cut in between, so you have to ask the question again.
Okay, just follow. Suppose the nanoparticle silver, copper, when it is embedded in nickel matrix, what sort of interfaces you?
Sir, the interfaces form, the three kind of interfaces will form, one with the silver with nickel, and one with the silver and copper, and one with the copper and nickel. Three different kind of interfaces will present.
No, I'm not talking about chemically, that structurally, what is that interfaces? What sort of interfaces you can expect?
Sir, we have done the HRTM where the local structure we have obtained at the silver and copper, where we have clearly see the orientation relationship between the silver and copper phase.
Okay. You should look into it. That's an interesting thing, and that will help you to understand the melting temperature.
I think, Professor Mukhopadhyay,
yeah,
we have two more speakers. I think let us end this particular part. Let us call upon other two speakers, because the panel discussion will start. They are all waiting. Okay. Sorry, but thank you, Khushbu. Okay, best of luck.
Thank you, sir.
So let's call Shumita Santra, electron microscopic study on nano-size precipitation during aging in alloy 617. And I think I would request you to fix the time complete it within 3 minutes. Sumita Satra?
Yes, sir. Sir, am I audible?
Yeah. Yes.
Sir, I have.
Yes. Please go ahead.
Share the screen. Yes, sir.
3 minutes. 3 minutes, ma'am. Yes.
Yes, sir. Thank you. Myself, Sumita from Nuclear Fuel Complex.
3 minutes.
We have done electron microscopic study on nano-size precipitation during aging in nano.
Please start.
Yes, sir. I have started. Are you able to hear me, sir?
Yes, please. Carry on. Yes, you are audible.
So, okay. So, LS617, it is going to be used as a future boiler tube in AUSC, because at present some steel is used which can operate at 540 degrees centigrade, and afterwards we are planning to go even higher temperature at 700. But because this increase in temperature, there will be some gamma prime precipitation which will help in the creep properties of the material. So the main focus at this was to check the precipitation behavior with respect to different aging treatment. So the sample was solution annealed, and it was aged at different temperature like 700, 750 and 800 degrees centigrade for 100 hours, followed by furnace cooling. And we have done PM study. So what we can see that this is the solution annealed structure, where we can see this is one grain boundary, and some very fine level of some carbides only along the grain boundaries were visible. Whereas if we go for the further aging treatment, we'll gradually see that there will be some new kind of observations are there. So at 700 degrees centigrade aging, this is the PN image, and this is the same image, where we can see that fine precipitation is there, which are uniformly distributed, and these are very fine nanometric precipitates, which are nothing but gamma prime. And we have taken the SAED pattern, and after indexing, it was observed that those things are consistent with NO3AlTi type structure. And this stem mode, EDS was carried out, which could show that aluminum and titanium enrichment at with wet percent of around 1.8 and 0.8. And then further, the average size of the precipitate, it was calculated as 9 nanometers from the particle size histogram plotted. And then the sample which was aged at 750 degrees centigrade. Here we can see once again the TM and STM contrast. For the very bright and dark contrast also, the particles are visible, but of course it has grown in size So there is an increase in size which is observed. And when we have done STEM and DDS, the gamma prime size increased to average size of 20 nanometer. And there is this aluminum and titanium content also, it has slightly increased as detected in the STEM DDS. And further, upon heat treatment at 800 degrees centigrade for 100 hours, further coarsening is observed. And we can see that the aluminum and titanium has grown further in content of 3.9 and 2.9 weight%. So there is our observation is like the gamma prime is coarsening with the aging temperature, and there is further enrichment taking place with respect to aluminum and titanium content. And because the formation of these gamma prime precipitates, increase in hardness is also observed. In addition to this cell, if we can see this SAD patterns, we initially what we have checked at 700 degrees centigrade, it was totally the nickel matrix along with the gamma prime phase precipitates, which are superposed patterns. And then we can go this 800 degrees centigrade. Whenever the oriented pattern is obtained, so always simultaneously very fine carbides are precipitated. So those things are also coming into picture. So at from 700, 750 degrees centigrade, we could see that not only grain boundary, intragranular very fine stage of carbide precipitates are taking place, precipitation, which we expect that it can help in decrease properties while during service it will be there. Thank you, sir.
Thank you, Sumita ji. See, we don't have much time because
actually my colleague Rupesh is present with me only because we are sharing a single computer. If you can allow, he will present from this login only.
Okay, please. Okay. So, Mr. Rupesh Kumar, please start. And see, your time is 3 minutes. It's a very hard time now because our eminent speakers are waiting because there will be a kind of panel discussion. So I would request you to keep it within 3 minutes. Within 3 minutes, you should finish your conclusion. Rupesh,
am I audible?
Yes, you are audible. I would request you to
Yes, sir. I'll try to finish it.
Within 3 minutes, you finish it off. Okay.
Sure.
I'm sorry to say this because the next session is getting delayed.
So my presentation is on grain bonded precipitate settlement in alloy 617. So this is alloy 617 tubes are being manufactured for advanced ultra supercritical power plants at Nuclear Fuel Complex, Hyderabad. So during one of the cold working processes during intermediate filtering stage, the tubes got cracked. So detailed characterization was carried out to identify the root cause and provide the corrective measures. So the hardness measured on the cracked tube and the tubes which were successfully filtered, they were nearly same. They were around 180 VHN. So the fractography using SEM showed intergranular mode of fracture. Here we can see the tracking along the grain boundary in the fracture surface analysis. The microstructure characterization that showed second phase precipitates along the grain boundary very fine. The EDS analysis at spot showed the precipitates were enriched in chromium, molybdenum, and carbon. So mixed carbide has precipitated on the grain boundary, which resulted in embrittlement of the grain boundary. This caused cracking of tubes under loading condition during filtering. So similar condition, similar microstructure we have also observed in as extruded plant, where slow cooling is involved. So here, although solution annealing has taken place successfully, but since the cooling rate might not be fast enough, so precipitation took place along the grain boundary, and that resulted in failure of the tube. Then re-annealing of the these cracked tubes were carried out. So after re-annealing, it is shown here that the grain boundaries were completely free of any kind of precipitation. So it was established the reason for the cracking, and the issue was resolved. Thank you.
Thank you, Mr. Rupesh. I really appreciate for finishing it within the time. And I thank Professor Mukhopadhyay. Please take over.
Yeah. Thank you, Kallal, to really manage the time and to complete it as early as possible. And it's a very hard time to manage both the question answer and also the presentation. But nevertheless, there will be a session in the panel discussion, and I'm sure we all will enjoy this panel discussion. And let me thank complete this session for presentation as well as this panel, this poster session. I wish I could have got much more time in the poster session because most of the results were very interesting, and that requires some more discussion, but that can happen anyway at any time. Okay, so thank you very much. Now, Krishanu, please take care.
Yeah.
Kallul,
Thank you,
Kallul, you want
Professor.
to say anything? Yeah, sorry. Okay, go ahead.
Yeah, thank you, Professor Mukhopadhyay and Professor Mandal for nicely organized sessions. We are only 10 minutes delay. I must apologize for all the panelists who are waiting. Professor Casey is here. Professor Casey is well known.
Hello.
He doesn't need any introduction. And you will have exactly 1 hour. So 10 minutes you will have extra on the other side. I hope Professor Murthy and Eric will be not be so time pressed. So all the panelists are here in the dais. So I just hand over to Professor Casey. Sir, your mic is muted. Your mic is muted, sir.
Can you put them into the platform?
Yeah, I'm doing it. So you can start that.
Because I don't see Dipankar Banerjee.
Yeah,
Asif.
He's there.
I am here, Professor Casey.
Okay.
But I think my video is kind of muted, so I'm not able to put the video on.
I'm just putting it on the dais.
Asif, your video is not there.
Yeah, the video is not coming. It says you cannot start your video because the host has stopped it. So I'm not able to use the video, but my audio is working.
No, but host can restart.
Yeah, I believe.
Or maybe you can just try to log in again.
I can. I tried that already. I think when I logged in, it didn't allow me. But then I re-logged in.
But you have not looked at YouTube. Is it the proper?
No, I'm on here on Zoom, but some reason I'm not able to start the video. It says the host is kind of
you may be able to start it now. Just check.
Okay, let me try that. No, it still says that you cannot start your video.
Oh.
Okay.
No, I have to make it. So now we can start.
Okay.
Can you start now?
Yeah, I did that. Now, yeah, should be able to get.
I think
Dr. I can see Eric.
Very good. Okay. So I think my camera is on.
I like to see Dr. Shiv Kumar. Asif is there.
Hi, I'm here.
And Dr. Shiv Kumar, have you joined?
Yes, I have joined. My video is on. My audio is on. Can you hear me?
I can hear you. I cannot see you, but it's okay.
I can see my video is on.
When you speak, probably it will come. Okay, without.
So the quick suggestion, so in the right hand side corner, you have a view option. If you put it in gallery, all the panel members will be able to see it together. So in view right hand side, you have a view, put a gallery view option.
Yes.
Click on gallery view, then you can see all the panel members. So all the audience, they can do that so that they can see panel members together on their screen. So view, gallery view option, that will show you.
Okay.
We have done that. We have to remove all the others actually then. Right?
Yeah,
So,
you have to remove others except you, so that if you need.
okay, sir. Sir, just two message. I think Eric has a hard pressed time. I think he will.
Yeah, I know that. I know that. I know that.
And second is that we are going to record this.
No, yeah, we must ask all of you that organizers requested to record this. So,
Go ahead.
if agreeable, then recording will start. Is it okay?
Yes.
All right. The reason is that on the basis of this discussion, there will be a short report will be prepared, and we'll try to go for the future. We'll use it. Now, let me very briefly introduce everybody. Dr. Dipankar Banerjee, everybody knows, and so I'll not introduce in Indian audience, but Dipankar Banerjee is a professor, honorary professor at Indian Institute of Science, Bangalore. Professor B.S. Murthy is a professor in IIT Madras and a director of Indian Institute of Technology, Hyderabad. Then we have two speakers from one Professor Eric Starch. Eric is an expert in-situ microscopy. He is a professor in UPenn and also director of Laboratory for Structural Materials. And he worked both in National Laboratory in Berkeley as well as in Brooklyn. And here he is associated with this in-situ microscopy from very long time. In my left in the screen is Asif. Time passes by. That Asif has now spent 30 years. I still remember when he was a student running around in Indian Institute of Science. But more importantly, Asif was also involved in early development of all in-situ microscopy techniques. And I forgot that Eric also is involved in hummingbird, setting up the hummingbird. And Asif is involved in setting up all the things that came out from University of Oxford. So both of them are actually pioneer in development of this in-situ microscope. And we have two very important persons for this because we want to set something up in India. And we have Dr. Milind Kulkarni. Dr. Milind Kulkarni, he is one of the most important person in Department of Science and Technology who has played a key role in National Nano Mission. And I hope that he will also play a key role in our future development in this area, because he's also involved in a technology mission of the country of Department of Science and Technology. And we also have Dr. Shiv Kumar. No, my screen was suddenly vanished. Dr. Shiv Kumar, and Dr. Shiv Kumar is now the director of extramural research, which actually is very important for academics, people like us, because the major funding from defense research and organization DRDO comes through this forum. But that is not the only one. He was involved in most of the Indian research in semiconducting research in GATEC and Sitara, and that is where he played a very key role in developing many, many programs in India. So welcome all of you, and let us start the discussions. As I have circulated to all of you, it will be, I like to have it in a discussion mode. So we have a series of issues and questions, and probably we'll go one by one, suitable person, and start the discussion. The first issue that I think all of us look at is that what is the future of the microscopy, and where the dynamic in-situ measurement stands. This is, before I ask the question, I just want to give few facts that last 1 year, Nature and Family of journals have published 34 papers, and last 5 years, 120 papers, which involve in-situ microscopy. Science and Family in last 1 year, has published 11 papers. So total publications till now is 45 years, last 1 year, which involves some kind of in-situ microscopy. What are the facilities available in Asia? I will not go to other places. TM holders, which are capable of doing in-situ microscopy. Singapore, it is there with 16 different groups. Japan, 25 plus different groups. Korea, 30 plus different groups. And China, 100 plus different groups. But in India, it is only one heating holder prototype is there in Indian Institute of Science. There's a DEN holders in University of Hyderabad. And there may be 1 or 2 I may be missing out. So we are just at the beginning. We do have plenty of heating holders, but I am not taking into account. So we have really, we can start this initiative because we have a lot of trained people who have used these holders in different laboratories all over the world. So we must first like to know what is the future of the microscope and what is the future of both dynamic microscope and in-situ microscope. So I'll start with Professor Eric. Eric.
I was afraid you're going to start with me. So I think that there's a position now where, in terms of some of the key performance aspects of the electron microscope itself, we've seen a tremendous amount of development in terms of the capabilities for both resolution in imaging and spectroscopy, also for high signal rates for spectroscopy through both enhanced sources and improved detectors. And this really makes it a good time to be trying to push on the in-situ methods, because we are less struggling with the difficulties of microscope utilization and exploitation, in addition to trying to do the more complex experiments inside the microscope. My good colleague, Dmitry Zaharov, who I worked with many years, always kind of commented that anytime one of these in-situ experiments worked, it was a miracle, just because of the fact that you had to have the microscope working, the microscope tuned, everything going well there, the experiments set up with the right sample, the sample doing the right thing. And so I think in some ways the increased capabilities of the microscope leave us in a position to focus more on these sorts of in situ experiments, which is one of the reasons I think you're seeing more development of the approaches and exploitation of the methods over the recent years. I think also there's a lot of interesting developments happening in terms of our ability to extract data from these complex data sets with the increase in computational speed and improved methods for data analysis based on statistical approaches, so-called machine learning sort of things that people are doing. And that also leaves us in a position to exploit the types of experiments here to extract quantitative data and match quantitative data with theory to get at real insight. So I think those are kind of two things that are happening that are enabling for this approach overall. There are continuous developments in the sample holders, and in many ways those happen kind of routinely and at pace as people develop new ideas or improve the other parts of the experiment. There's increased demands upon the sample holder capabilities overall. But many of those are being met, I think, pretty effectively by a number of different smaller companies involved in this research area. That's just a big, quick overview. I hope that helps.
Yeah, that definitely helps. If I understand correctly, that we have the particularly pico resolutions and pico compositions, and those depends upon very high capacity detectors that has been solved. Of course, it will continue to improve. And secondly, I understand that there's the strong effort in developing these new techniques. That will continue to go on, but in Indian context, I don't think we are yet ready to take on. So Indian context, actually, in situ becomes very attractive. So I'll ask Professor Dipankar Banerjee, because he is very passionate about developing to do a cutting-edge microscopy in India, and how you see the in-situ microscopy and other things in that context.
Well, thank you, Kamanyo. I am really not the right person, obviously, to talk about in-situ techniques. So I'm not going to directly respond to your question, but I'm going to put on a management hat for this particular panel discussion. And I'm sorry if that disturbs the flow a little bit. But I also want to share my screen. So if you let me quickly do that. I don't believe that's going to take too much time. Is it?
You can do that.
Is it sharing?
You are not seeing the sharing, right?
Are you seeing my screen?
No, you can share the screen, yes. You are a co-host.
Well, I chose it and then it
has not yet come.
Oh,
yeah. Coming.
Right, okay. So first of all, I want to congratulate everyone on organizing an outstanding workshop and state the obvious really at this point of time, that understanding dynamical response of materials to stimuli is an absolutely key component of material science and materials design. And therefore, I'd really like to appreciate the initiative that this workshop represents. It's great that you put it together. Now, what was obvious today already, and I'm sure will be quite clear tomorrow, that there's really a very vast spectrum of possibilities for in-situ work, ranging from the bulk to thin films to 1D and 2D materials. And how do we put together a reasonably coherent national program in this area? And obviously the key challenges are, how do we determine important focus areas? How do we think of implementation? And so the way we've done it in the past is to build capability, okay? For example, at IISc, Kamanyo initially and I later on said, this is what we must have. And we put it together and then looked for research proposals. I think we have to slightly change this paradigm, and what I'm suggesting to you is a sort of stepwise procedure for the way we might want to go forward. And really, I'm suggesting that we develop capability which are driven by research programs rather than the other way around. So what I'd like to suggest is that we have representatives from DST, DRDO, and Gautam is here as well. And can we organize a joint study group with dynamic leadership? And what I'd like to suggest is that this study group will invite white paper research proposals for something like a 5-year duration. It'll determine the top proposals and then expand these to determine the techniques, capability, and resources required, and then look at implementation. So the implementation itself has several different aspects. There is, do we have a new center? Do we augment existing centers? Much of these decisions will actually depend on the kind of techniques that you're trying to implement based upon the research programs that you want to look at. We have to look at human resources in collaborative groups. We have to look at financial resources and then management structures. So I would suggest to you all that we might take this as a way forward. I recognize there are many different ways of going about this, and these are just my preliminary thoughts in this area. Again, underlying very clearly for all of us that the second point, that the dynamical response of materials to stimuli is a very key component of future materials research. So thanks a lot. Thank you, Chandru and Kishanu as well, for inviting me to the panel discussion. So let me stop share.
Thank you, Dipankar. Actually, you have made my life easier. I would have come back to this point slightly later, but you have already started it. But before I move on to this, I'll go to Dr. Asif, because you are involved in setting up of these in-situ facilities, and you have seen the evolution of these in-situ facilities, how these facilities are run all over the world, because you are involved in many of those. So can you give your impressions about how these facilities are set up worldwide? And
okay.
then what is your model for India?
Okay.
So you know
so yeah, I think I will address the second question first. I'm glad. Thank you very much for inviting into this panel. From industry perspective, from a small industry perspective, I have a couple of points that I want to make. The one is that we very earlier on, when we were developing these in-situ holders, we realized that to be part of this ecosystem, our best investment into the ecosystem is the academic collaborations. Okay. And I'm glad that Eric is here. I remember like talking to him at a conference, or later we collaborated very effectively with this group at EMSI. And with that collaboration only, we were able to come up with this all these wonderful holders that we are using currently for Institute of Nanomechanics. So coming to India, I think we would like to repeat the same model. So in 2011, I believe I was able to bring these holders to India, placed it in IISc, both the TEM and SEM holders. The SEM holders were in good use. I think Professor Vikram's group, I think even Divangar's group students, they were able to use. But with respect to TEM holders, we kept it for 3 years. There wasn't any use at all, and it was not at all got used. So I was curious, like, what's happening. One thing was basically when we were doing that collaboration with Eric, we had a good funding mechanism to support through SBIR. We didn't have something similar, but we were able to place the holder. But from the institute side, there was the students' availability was not there. There was some kind of a hesitancy in using this holder inside a TEM because of the, I don't know, maybe because they may something may go wrong with the microscope, the downtime of the microscope and all of that. So I don't know what the real reason is. It wasn't as successful as that we were able to do it back in US. So something we need to look into. So maybe we don't have students, even the students when they graduate out, we don't have the continuation of that effort. We need to even pay attention to that. Also, we need to think about the funding mechanism that to support all of that. So that I think is from my perspective. You have to have this whole ecosystem. Industrial academic collaboration has to be there. It should be funded. Students should be trained. All of those things should go together to boost this in-situ ecosystem.
Thank you, Asif. I can see that problem. You as well, Dipankar, has correctly pointed out. As I see it, that holder has not been used that much because there's no program running. So most of the students are in certain programs, and that programs were for more classical type of things and composition measurement type of thing. And that is where I think you have correctly pointed out that we need to have a specialized program together with the holder. Otherwise, there's a difficulties. Now I'll come back to both one by one, Murthy and Gautam there, because both of them are involved in setting up microscope center and have a different models. I'll first go to Gautam there because he is instrumental in setting up the first collaborative microscope facilities, which was initial funding of IISc, where BRC scientists used it extensively. They used to come here and use our microscope. And later, he set up the high resolution microscope, not in BRC, but in TIFR. So what is your experience and what do you see for this dynamic microscopy the model we should use.
Gautam, you need to unmute.
Gautam, you are muted.
Gautam, you are muted.
You are muted.
Still muted. In this online world, we have to learn many things.
Krishanu, can you unmute him?
I'm trying. I'm asking you to unmute him.
Possibly he is not able to hear us.
Okay, I think I have to call him.
He keeps on speaking, so he is not able to hear us.
Amanyo, let's move on to Professor Murthy and then come back to Gautam.
I will call him. I'll move to Murthy. Murthy, you
can you hear me?
Yeah.
Yeah, we can hear you.
No, it's not that I was not able to unmute from my side. The button was not going to the active mode at all for my best efforts, and I was able to hear you. So, and this is not the first Zoom meeting that I'm attending.
I know that. I know that.
See, for the information of everybody, friends, okay, in IITs we are not supposed to use Zoom. Okay.
No, but
that is okay. Let's not come to that.
So that's why Zoom is new usually.
As I said, I'll repeat that again. I was muted at that time. Thank you, Professor Pamanio, for your comments, and to Krishanu and Chandu for their invitation. As Professor Chattopadhyay said, actually, I was involved in this installation of the ISC facility as a contributor from the DAE side. And it so happens that I have been involved in 3 facilities. That is the ISC facility first, and also the IIT Bombay National Center for Texture, which is run by Professor Samazdar. And there again, we have a sizable funding from DST as well as from BRNS. And last but not the least, Professor Murthy's 3DAB facility in IIT Madras. When my tenure was ending, that's the time when the discussions were going on. And then later on, I had to play some role from the BRNS side to see that things had materialized, and it has materialized, not just due to my efforts, because of the efforts of other people. Excellent centers. I don't have to say anything about these centers running very well, and they're actually role models for, I would say, even the funding agencies can claim considerable pride because of the reason that they have supported these facilities. And these facilities are being accessed by a large section of people across the country. And it so happens that they're dedicated to 3 different domains of microscopy. One for nanoscience, the other is for texture and micro and nano texture. And the Professor Murthy's facility is for 3DAP, atomic resolution composition analysis. So I don't have to talk more about these facilities working very well, and maybe we can have more such centers across the country, because going by our size of population and going by the number of people who are in science, we definitely need many such facilities, many more such facilities to enable particularly young researchers access, which is an issue, as we all know. So that can happen only if we have such facilities being run across the country. Now, coming to the in-situ microscopy, as has been said, it is not done in every center. Actually, it is done only a handful of centers. Why handful? Not even handful. It's ISC to begin with, and maybe DMRL, as Professor Casey said. As far as TEM in-situ microscopy is concerned, they had purchased, DMRL had purchased, I think, a nano indentation holder where you can do the indentation inside the TEM. It was probably from Sweden or some other place.
And
okay?
Hyderabad, the University IIT Hyderabad has then holders.
Yeah, so we need more such equipment training. Now, this is where I would like to spend 1 minute on training. You see, the centers are set very well. They are doing extremely well, but it will be also very useful if they hold tutorials in each of the areas that they are actually specializing in. And that is how the in-situ electron microscopy can also be brought in. You know, the Nanoscience Center does in-situ electron microscopy. Professor Samajdar facility also does in-situ in the SEM. But he is holding some tutorials. It will be good to see I think Nanoscience Center also has held some tutorial lectures, because that will facilitate training of people. As Professor Deepankar Banerjee said, we need also trained people to operate these facilities. It is not enough to just set up these facilities. These have to be operated by trained people. Very specialized training is required, as we all know. So I would put more emphasis on not just the creation of the facility, but also training of people who are able to use these facilities to the fullest. And with those words, I will conclude. Thank you so much for your attention.
Murthy?
Yeah, good evening, friends. First of all, thanks to Kishanu and Chandra for this wonderful meeting that's going on, and thanks to Professor Kamanyo for including us into this thing. As Gautam is pointing out, you know, most of us, when we started our PhD, we just knew only basic. In fact, EM301 is what we started with. The 200 kV microscope, we could only look at it from a distance, which was there in the Material Science Center. Mukho knows this, all of us know this. So the first in-situ microscopy, I had to wait until I go to Germany, my first visit abroad, 96. I went to Bremen, EFOM Bremen, and that's where I started doing some hot stage TEM of some nanoparticles growing and looking at the growth kinetics. So the basic thing that is essential is training people. I mean, first of all, we need to have a critical mass of these facilities with in-situ microscopy facilities available. And it should be, as Deepankar mentions, it should be more like there has to be a need for that. There has to be a project where, I mean, most of us, possibly because of the non-availability, our PhDs used to be more of what you can do with the existing, rather than thinking something which is bigger. Okay, we started, for example, we realized the need of training. For example, when I was in IIT Madras, okay, we started what is our practical TEM course. One full semester course. We used to take about 5 students, and Shankaran helped me in that. And now that course is still running. And now, after the atom probe has come, Pradeep has started a practical atom probe course, where it's again a 6-month course, where one has to go through a theory first, and then even in TM we did the same thing. One has to get a minimum B grade in the theory, and then you can venture into the practical course. So this is something at every institute, this has to happen. And we are doing mostly at our stage, we were only talking about, composition analysis or maybe higher resolution microscopy. But then doing really in situ is something I would say in India has started only around 2000 and beyond that possibly. Okay, definitely not during our time when we were PhD students. So this is something I feel there has to be an effort on, identifying areas. For example, I see Sairam at IIT Hyderabad is doing a lot of electrochemistry. Tomorrow in his talk, he will talk about it. So there are centers coming up. But what is more important is, as possibly, Deepankar mentioned, people can come up with proposals where you want to solve a problem only through an in situ way, and possibly identify 1 or 2 locations where we can put a lot of in situ facilities, and then that facility should generate a large number of people. For example, atom probe, I'm so happy that, Milind is sitting here, really grateful to Milind and of course Gautam. 8 institutions have come together to put up that facility, and we made it, even remotely operable. And that's now about 7 institutions are able to operate sitting in their IITs. And this is something has happened. And in the last 3 years, more or less about 40 to 50 papers have come out. Many of them are real high-end papers. And that's because we are able to do it in a consortium manner. And similarly, in a consortium manner, if we can set up a facility like this at one place or so, where everybody starts using, and now so much of online things are happening, and it's possible to convert some of these microscopes in an online mode, so that anywhere you are, you should be able to use. I think this atom probe that facility that we have set up should be a good lesson. And as Gautam pointed out, it's a pride for the country that we are able to come together like this and able to set up. And I think a similar fashion we can move on, and possibly should have somewhere where a large number of people are trained, and in 5 years, 10 years down the line, you would see everywhere people doing it. Okay, even microscopes, when we were students, the number of electron microscopes are very few. The numbers have increased. Even high resolutions microscopes have come. But what is missing to a large extent is thorough training with a full-fledged, semester-long or year-long courses. And that, if we can start doing it in a number of places, I'm sure 10 years down the line, India will be doing a lot of work on the in-situ microscope. But I completely agree with Kamanyo. It is a need of the hour. I think that's, and also as Dipankar pointed out, to understand materials in a deeper sense, without in-situ understanding, you will never be able to grow much. So these are a few thoughts from my side. Thank you.
I think I will come to this discussions of training and other things. Training, I think now several places training started. Training actually started at ISC very early. Our microscope have no operator. It is only student-run microscopes, and that is how it should be. That is what it is happens in most of the places in the world. Not the operator-run microscope. But the issue is not that. The TM, of course, cannot be done like a atom probe, because I have tried that in our center. But no microscope, both Joel and FEI those days and now, they are not willing to share it into different locations. Actually, we have bought everything, but then they say that it is very risky, microscope will get corrupted. So that is not possible. But what I now want to come, both Milind Kulkarni is here and both Shiv Kumar is here. He is also involved in the collaborative research with our atom probe and the high resolution microscope at ISC and the laboratories in DRDO. So the issue that I like to ask you is that what is the two things. One is the funding models for setting up the facilities. Second thing is that how we'll go ahead. Number one, use of it through a project, specific project. That is difficult, but that can be done. But more importantly, how we are also will look into the maintenance of such facilities so that it can sustain. So I'll go one by one. I'll come to Milind last. Can I get the view of Dr. Shiv Kumar?
Thank you very much for giving this invitation to be part of this panel discussion. Though I am not an expert on electron microscopy, but I am a material scientist and now working for DRDO at DRDO headquarters. And it was nice to hear the views of all the panelists. I have also passed, as Dr. Murthy said, that we have passed through the phases where we did not have facilities. We had limited facilities, and now we have very good facilities. And as both of the panelists said, that we are lacking in training, though IIT Bangalore is giving training, but I also suggest that training should be at all the centers. But as and coming to the point that how to take up the funding part of the this thing, what will be the model for taking, as you said, I think we can evolve various mechanisms. We can take up this as a project model through some project, or like it is we have a atom probe microscopy there at IIT Bangalore. It can be another facility can be created. We can have a number of discussions. We can have discuss amongst ourselves. We can have another meeting on this particular subject, how to go about the funding of this in situ electron microscopy. That can be discussed in a meeting where we can evolve how to go about it. I would say at this moment. That's it from my side.
Milind,
Yeah.
you have quite a bit of experience.
Yeah. What?
Nano mission as well as.
I have 2-3 things to add. Starting from training. Training, as you said, IISc is doing it. It's very good. But I feel it should be an integral part of the curriculum that you are teaching at any postgraduate level. You should make a 6-month course parallelly compulsory for a material scientist to be done in the institute or in the university. Unless he does that, he is not given the degree. This is going to be a changing game now. And now with the yesterday's ministry change, you have PM looking after science and technology through his MOS. It's a big jump that he is going to give a 2%. I am sure he is going to increase the GDP percentage on science and technology, and he is keen that all departments should work hand in hand. That is the main thing, and that is why my suggestion to Secretary was also that let us join hands with DRDO, Atomic Energy, and other institutions and see to it that we build a common lab for materials research. And these material research will be strategic area and other will be general area. For example, if we have an institute in DRDO created only for strategic area, we can do that. There should be a parallel institute created in an institute like IISc or maybe some new structure. We are creating under Sati scheme something, but then I don't know, because Sati is again going to be a Section 8 company. I want these projects to be a 10-year project, so that within 10 years you can make the event, make the whole institute a self-sustaining institute, where you have floating positions. People can come, stay for 3 years, do their research, or come and stay for 6 months, do the particular objective of their research and go back. That is how it should be.
I think you have given a very good suggestions. Actually, let me tell you our experience. Because when we set up the microscope beginning of this millennium, and it was operational in 2003. That was driven by desire that whenever I used to send a paper, they will ask me to do something, and for which I have no facility. Okay. Like one of the questions in the one of the academic reviewer told me to do something which only Berkeley National Laboratory had that facility to do. So obviously my paper will get rejected. I cannot do that. So that is how we have set up. And that time we thought that we'll have it integral to a curriculum. Poor Professor Bikram Jairam and Ravi Shankar given a course year after year and sometimes every semester. And then they are trained on the microscope, practically, tests were given, and they were cleared. But our statistics says that among those who are trained, only about 5% comes back to really use it. That is because of two reasons. One, when people come for training, they think it is very easy. Soon they realize this is a very hard. And professors, their supervisors, do not want to give time unless he is a microscopist, do not want to give that much time to his students for getting results.
So Casey, I was going to say this earlier. I had my hand raised. I think that's one of the biggest problems with the in-situ work is it just takes so much time for students to become efficient at it. And, you know, I mean, my group does nothing but that. So I mean, I'm thrilled if in year three, I see my first set of really good data, right? And that's a long time. And not many students are the type that are able to kind of be that patient with it. You know, it takes a lot of patience and a lot of stubbornness, I guess you would say, to you know, be on year 2 and be like, well, you know, the kid down the hallway, he's just published his second paper because he's mixing some stuff up and taking some XRD. Whereas, you know, I'm still trying to figure out how to make all this stuff work. And so it is a challenge. And there's no doubt about that.
See, for laboratories, it is slightly easier because both DMRL and Gautam will say, they have scientists, not students. And they get trained over a period of time. And some of them become outstanding. This is a real problem, which Professor Murthy also will find that in an academic atmosphere. So I like to go over to Gautam. What is your opinion on these?
So one more thing which I want to say is, can't we popularize some of these machines by bringing benchtop machines through indigenous manufacturing? Because once we have that thing, you know, we have some indigenous manufacturer who is willing to do these things. Because my problem is DST, the instrument development division, is totally dead. Everywhere you see, there is no instrument development now going on, and that is what is the, you know, troublesome thing that I see in the last year of my service, and that is what I want to revive.
So Milind, I see Asif is face brightened up, but let me tell you one thing before I hand it over to Asif and Murthy wants to tell. But microscope, modern microscope, if you want to do cutting rays, it has a 3 pillar now. As I see it, maybe others, Dipankar, Eric can join in. One of the pillar is to going for pico and sub-pico.
Yes.
Both in a composition space and the structural space. And that requires cutting edge. That you cannot do as a start. Even Philips has got out of that game. That is very specialized. Secondly, all microscope development, there's a pillar which is instrumentation. But unfortunately, if you want to do cutting edge research, the instrumentation that required, we need to have few groups, even 1 or 2 groups, which has cutting edge. It is never done by material scientists. We have to get in physicists,
yes,
and the engineers. Unfortunately, that is not there in India.
That is what I see.
And many of us will be happy if we can have that group, but it is just not there. Third aspect is using dynamic microscopy, using whatever. Now, fortunately, these microscopes are available, which are easy to use, and you can do it very, very effectively, particularly after STEM and STEM yields. It has come, you can plan good research. So this is my view that is why the instrumentation part has not developed. But I do agree, unless that develops, I think we'll always suffer. Now, Asif, do you have any view on this?
Sure. And I've been struggling for the last 10, 15 years in India. We have an indigenous company in India, Industron, and we also came up with indigenous product, desktop nano-inundation that we designed and developed in India. Based on my experience, I can tell that there are talent in India that we can set it up and all of that. But the basic thing that we lack is infrastructure. For example, when I want to develop these sensors and actuators, I need to have some precision manufacturing. I don't get that in India. I mean, even for if I want to do a micro wire EDM, I don't have anybody who can do that. There may be CMTI and other some institutions, they have facilities for that. They won't help me to do that. I still have to make them in US and then send it to India. I mean, this is how it is working. We try to work with the vendors. They're not fully trained or not having the capability to do this kind of instrumentation in India. So that infrastructure needs to be there. Without that infrastructure, it's a kind of a struggle to build up this kind of indigenous technology with whatever the effort that you can do. That's why I think we are very behind in instrumentation in India. We don't have that basic infrastructure or the ecosystem, the vendors that who can do all these things to the kind of a precision that we need. That needs to be there first. Yep.
Satyam.
I think we need to close now.
No.
We are close to 6 o'clock.
No, we have a 15 more minutes. There are few important issues I'll do. But before I say, let me tell you one more thing, which is my personal experience, because we will not get these opportunities. And Milind is here. Asif Senior in the lab in IIC wanted to develop some of these holders. And they wanted a dedicated microscope for that. That time I was in administrative positions, Dean Mechanical Engineering, and there's a question of funding a new microscope which will be used for developing this. And ultimately I have to refuse it. Not because I don't want it, but I have to refuse it because what institute got worried, if they buy a new microscope of expensive microscope, then they started manipulating it and drilling and all these things. An auditor comes in, will be totally ruined. Because auditor will say, how can you use this microscope like this? It is such an expensive unit. And that was then ultimately the advice was that you cannot do it with a new microscope.
I think audit people are quite logical if you talk to them that this is required for future research. If we don't do it now,
you can do it. You can do it for 1 crore, but you cannot do it for 7, 8 crore.
Sir, 1 crore and 7, 8 crores is the same amount if
no,
India is there.
I faced a legal problem. We had a court case.
Professor Casey, Dr. Satyam is here. He wants to say something.
I know. He called me. I'll come back to him. We have 2 minutes, 15 minutes, so I'll just come back to him. But before I do that, I like to get an opinion of, we have some clear ideas now, starting with Dipankar Banerjee and how we can move forward. So, Dipankar, can you summarize? What do you think? You are good with the words.
You're mute.
You are mute, Dipankar.
You are mute.
Well, I thought the summary should come last, and since Satyam wants to say something, and I don't know if Rahul wants to say something, if there are a few minutes left, can they say what they wish to say?
Yes. There's time. There's time. Then you can summarize. And I'll also come back to Eric, what his feeling is. Satyam, can you come in? Satyam.
Yes, can you hear me?
Yeah.
So I just, okay. One second.
Yeah, because I know that you are very much interested in developing some dynamic microscope.
Okay, just now we had a meeting with VRC, with Raghavendra and other team members. we just accepted, BRC has been developing one SCM. Of course, Dr. J knows about it. So we hope just the terms and conditions of MOU, we discussed it. And one SCM which will be made, of course, a tungsten based one, that will be delivered to IOP as soon as it is ready, probably in 4 or 5 months now. That's what we are expecting it. We want to really take it as a challenge and try to see what best can be done with this microscope. Even if it's a 20-30 nanometer resolution, we know that there are several users can be done. And some technologies using a harsh environment detectors development, or a new field emitter gun development, or a dynamic SCM development, these are all on our vision. And I'm very thankful for actually Dr. Mohanty and Dr. Ajit Mohanty, BRC Director, as well as Dr. Raghavendra Tiwari, we are very actively working. We hope that this is going to happen, that the BRC SCM one of them will be delivered to the, that's what we think, and that's what today we finalize, I think, kind of discussions. And there we develop the technologies inside in IIT Bhubaneswar with, in combination basically with the BRC. This is one aspect. Other thing is Nigel, I think many of you will be knowing Nigel Browning. Dr. Browning moved from, of course, from the PANL to Liverpool. And he had one program, international program, where dynamic TM development. And some of us, I think IIT Bhubaneswar also, we are partnership with them in developing a kind of a fast blanker development, where how we can do it, so that we can do a dynamic TM measurements. So I just wanted to say, because I'm sorry I came in between, may not be part of it, but because the discussions were a little hot, and wanted to say that definitely I know that Dr. Day knows very well, but we even though the machine what we get is well below the competitors, but we feel that by appropriate use of the uses of the system and developing a technologies, we can play a role and be proud of it. So I just want to say those things.
Very good thing. I know you are passionate in developing this dynamic microscope also. Recently I had one idea, because earlier we failed and all those audit, everything problem. We have several old microscopes which maybe require slight repair, but one can tinker with it. And I do feel that those are the microscopes, if repaired, can be used for intense development of many of these. But the problem is that nobody will fund to repair that and use it for this. So that is why we require support from funding agencies.
Sir, for that, what you have to do is you have to make a project where you say that we will be using the existing microscope with little bit of tuning.
We will discuss it. This is not the platform. We'll have a separate meeting. We'll do that. And but before I do that, I throw it open. Rahul, do you want to talk about something? Rahul?
He's there for the next session. So.
Okay.
Yeah, good evening. So, can I speak? I mean, sorry, I was a little late in turning on.
Please.
Sure.
Yeah, I really enjoyed hearing the discussions and regarding training and also the development of microscope. This is really a welcome step if we can manufacture something in-house, because getting spares for our equipment from abroad is always very time-consuming and also an expensive process. And we also face audit objections at different level. So, but at the same time, I can understand that there is a problem of precision, as I heard. So that is probably stopping us. So, but it is always good that, as Professor Chakravarty suggested, that we refurbish an old microscope and work on it and do reverse engineering in the first place. So that kind of approach will be definitely helpful. And often I've also gotten offers from other places, even from friends abroad, that okay, an old microscope is there, which is available at a much lower price and you can buy it. But our system doesn't allow us to buy an old microscope, a refurbished microscope. We are always going for a new one. And it is also difficult to train a student on a very new microscope or a very sophisticated microscope. I learned microscopy on JM 100B, Joul's oldest model, which was a top entry type microscope with 100% manual. So we need specialized microscopes for training. I mean, and other types of microscopes for research. Unfortunately, that kind of luxury is not there. So if some relaxation is there, where we can probably refurbish the older microscopes for training purpose and also for doing R&D to develop microscopes in our country, so that would be very helpful. I think that approach would be good.
Chandrasekhar, I think you want to,
my perspective on this is, as we want to develop something in, we want to catch up. So there are three things happening here. One, we want to catch up with the world. At the same time, we want to start things and build it up. So taking one approach may not be the right multiple approach. For example, we have to work with industry to develop something. We have to train manpower so that we get resources to build things. At the same time, we have to work on cutting edge so that the science doesn't lag behind. So I think all three need to be worked together so that at the end of the, say, 5 or 10 years, we'll be at the same place or at least closer to rest of the in-situ or rest of the microscopy community. That's what I wanted to tell.
Yeah. We have to be a multi-pronged. Dipankar, I think I want a brief summary from you and then from Eric.
Well, I think my slide was my summary, really, and I'm not sure that I want to add anything to that. I think, I listened to all the discussion. I just want to focus down on the in-situ microscopy part of this. I think we should look at this slightly differently from our normal way of creating facilities, simply because this is not one equipment like an atom probe or one high-resolution capability. It's a multitude of capabilities, with different techniques and different requirements for different research groups. And so you are going to have a problem identifying a first approach, and that should be driven by the interests of research scientists across the country. And I would again, therefore, request that you initiate or launch a study group which gathers together the research interests of people across the country so that you can focus on what kind of capabilities you want to develop as a first step for the first 5 years. Once you have initiated that, it'll acquire its momentum and grow in a way that it should. I think this is what I wish to emphasize again. Okay. Thanks. Yeah.
A good meeting. Eric, you have heard that.
Sorry, yeah.
You have heard the
It's been very interesting to listen to, for sure. I guess I would share maybe a couple comments in kind of listening to all of this. In 1998, I started off as a staff scientist at the National Center for Electron Microscopy at the Lawrence Berkeley Lab. I think I met Casey shortly thereafter on a visit. At the time, in-situ microscopy was not being done very much. Everyone was concerned about beam damage. It was just one of these sort of things that was looked down on a little bit. And that said, Uli Dahman, who was my boss, hired me to do that work. And we had a lot of facilities there. That was what the National Center was for. And it was actually interesting over the next 6 or 7 years that we had people who would come in to do particular types of experiments. There was just basically heating. That's all that we really had. We developed that nano manipulation thing that Asif and I eventually worked on to make for a nano indentation. But I think some of the comments earlier about having a dedicated place to do a particular type of experiment is reasonable. And so listening to Dipankar's comments about a study group, it may be interesting for people to think about how there might be some distribution of specific instrumentation and capabilities at institutes that have people driving that part of the science, where people could come as necessary to do the work in addition. So if there were to be one facility, I missed the name earlier, but someone working a lot on electrochemistry, they may be a group that's well suited for doing liquid-based microscopy, developing that approach there for their facility driven by a specific research project. But once that's in hand, it makes it easier for KC to come and visit because there's a group of people, graduate students or postdoctoral researchers who know how to do the work, because it takes time. So that's just a thought I have on that, because it is about trained labor for sure, and that training takes time to get people to a point where they can do complex experimental work inside the microscope. Those are just some comments or thoughts based on everything I heard.
Anybody has any comment before I just short summary I'll do?
Professor Casey, I just wanted to mention to Dr. Milind, it is interesting to note that the first TEM of Asia was actually made in India, in Kolkata, SINP, Science Institute of Nuclear Physics,
I know.
by Dr. N.N. Dasgupta. Unfortunately, we did not continue that effort.
Exactly.
Had we continued that effort, we probably would have been world leader in also making TEM.
Somehow instrumentation is something I think we have to focus on in India to a large extent. I think somehow most of us, I remember even a 3 mm disc punch, always comes from Getan. Okay, so to make, I remember Harley Instrument, Nilesh, I used to ask, why can't we make it? Must be so simple. So I think that is something, as Chandra also pointed out, we should simultaneously focus on building things. I think now, thanks to India's focus on Atmanirbhar Bharat, probably is the right time that we should all focus a lot. And also most of the engineering colleges, the amount of instrumentation that we teach to our students is very limited. And that's something I think we are trying to do it at IIT Hyderabad. Hopefully we'll be successful. Let's see.
You have forgotten that we all use the punch made by us.
Oh,
and that punch is even now used, not Gatan. But coming to terms, small things, yes, I think we have to start. But the reason our microscope, the N.N. Dasgupta microscope, does not go ahead is because we are often forget the other aspect which Asif will know. It is that there's a commerce aspect. Making a particular microscope is not enough. To sustain it, you have to have a business model and you have to make profits. And N.N. Dasgupta microscope did not flower because there's no business model. Only Siemens at that time has that business model, and later on Philips started doing it. So without that business model, even today, even with a Bharat, all this initiative that is being taken up, those which will have a good business model will ultimately sustain. But that does not mean that we will not try. We must try, and some of them will succeed. This is what my feeling. So to sum up what I understood.
Perseverance pays, Dada. I always remember.
Perseverance pays, no doubt. But to sum up this meeting, these discussions, I feel that we have to take what I understood is that initially we have to have a few good programs that we can have a separate meetings and develop some good scientific programs and their requirement. And based on that, we develop few centers where the ecosystem, the knowledge of in-situ microscopy will be built. Once we have done that, those centers, others can come in and develop that. This is what is the roughly what we find. I get the feeling. And second feeling is that small things, of course, we should start doing it. Because if we want to do really something new, we have to develop ourselves. Otherwise, we will follow what others are doing. But cutting edge research also is important. And for that, we have to develop cutting edge facilities. And for that, we have to also get things from outside, but not without science. because then the facility will be there, nobody will be there to use it. So there should be people, and a program depends on that. It should not be like a Asif's nano indentor in IISc where no student has a program. That will be disaster. So thank you all of you. What I suggest that at least inside India, I have just lost 2 minutes, so we'll stop here. But inside India, we'll have some meetings and we'll take it forward. So all of you who have participated, let me thank you on behalf of the organizers. And I think we should hand over to Krishanu to listen to Eric's talk. Thank you.
Yeah, thank you, sir, for your time and for nicely on managing the coordination among 7+1 speakers. So without much delay, I request Professor Rahul Mitra to take over charge of the next session. I think Eric has strict time limits, is it not, to finish the talk?
I'm okay. I'll be good. Don't worry.
Okay, okay.
I'll make it work.
So I request Chandrasekhar to introduce Professor Rahul Mitra for the as a speaker, as a chairman of the session.
Thank you, Krishanu. Thank you all the panel members, and first of all, thank you Rahul for agreeing to chair the session. Professor Rahul Mitra did his undergraduate from IIT Kharagpur Metallurgy Department, and then he did his PhD from Northwestern, returned back to India, joined DMRL, worked there for some time, and then moved back to IIT Kharagpur. He was the head of the department, and now he is one of the active macroscopists and also head of the microscopy center at IIT Kharagpur. With that, I'll request Professor Rahul Mitra to take over the session. Thank you. Professor Rahul.
Good evening, everybody, once again, and thank you for having me in this session. It's really a pleasure for me to chair this session with 3 distinguished speakers. The first one has already been mentioned, Professor Eric Stack from University of Pennsylvania, USA. So I'll just briefly introduce him before we can start. So he's also a director laboratory for research on structure of matter at the Material Science, Research Science and Education Center, which is NSF sponsored, and he's also the Chief Technology Officer and co-founder of Hummingbird since 2004. And prior to his appointment here, he got full professorship at Purdue University. And he is presently the Electron Microscopy group leader at the Center for Functional Nanomaterials. Of course, he was at the Center for Functional Nanomaterials, Brookhaven National Laboratory, where he was sort of the group leader. And he is also a fellow of American Physical Society, the Microscopy Society of America, and secretary for the Board of Directors for Materials Research Society. He has more than 300 peer-reviewed publications and more than 200 invited lectures. His research interests are in the development and application of electron microscopy techniques to solve a wide range of materials problems, which includes catalysis, energy storage materials, solar voltaics, photovoltaics, nanostructured growth. So with this brief introduction, I welcome again Professor Stack and request him to start. So, great. Professor Stack.
Thank you very much for the kind introduction. I appreciate it. It was a pleasure to also participate in the panel. I hope I was able to contribute something to it. I thought I would give a talk today on some work that we've been doing recently. I hope you're seeing the screen okay?
Yes, correct.
You can see.
Perfect. Okay, I'll put it in the full screen mode. Okay, thank you. Some work that we've been doing quite recently within my research group led by a student, Jay Horwath. I'll be very frank with you. This is the first time I've given this talk. I've been at Penn for now almost 3.5 years, and it takes about 3.5 years, as I mentioned earlier, for students to really get rolling. So these are some of the earliest results I have from UPenn. So hopefully I'll do a decent job in explaining what we're doing and why. The goal of this work is to try to understand how nanoparticles evolve as a function of temperature, and to use new methods for analyzing the large data streams that come from modern detectors and electron microscopes. The motivation for this work is that, let me give you an outline, I'm sorry. So the outline, first of all, I want to do it in 2 parts. I want to talk about how we developed an approach to automate image analysis. And this seems trivial on first pass, but it turns out to actually be a fairly complex thing to do and do in an accurate way for the high resolution and high information data sets that we have. And then I'll show how we take the data from this automated image analysis and apply it to understand the behavior of a very particular system, nanoparticle gold held at elevated temperatures. And we're using gold because it's big and heavy, but also because it's noble. And in our most recent studies, we're expanding it into other materials, but I'll show you the results from the gold. This work was really literally all done by one student, James Horwath, who's in University of Pennsylvania in my group, really bright kid. He has worked with Peter Voorhees at Northwestern on the theory for understanding the coarsening processes. And then a number of folks at both Brookhaven National Laboratory and the University of Puerto Rico have been helpful with the image analysis portion of it. And so we're funded by both the National Science Foundation and the Department of Energy for this. Okay, sorry, there we go. So why are we looking at this? Nanoparticle coarsening is a phenomena that has been of interest to people for almost 100 years. Oswald's paper was over 100 years ago. And really, from a practical sense, it's because heterogeneous catalysts that are supported upon some form of oxide support undergo coarsening as they are in reactive environments. This coarsening process leads to the growth of the catalyst or the loss of the catalyst. And in each case, you end up having a decrease in the overall activity. And this is a industrially extremely important part of the development of fine chemicals, the utilization of crude oil to gasoline. Heterogeneous catalysis is everywhere. Now, this process you would think would be one that could be well described and well understood, but it turns out that it is not yet. There are a number of different competing thoughts on how the process works. In one case, what happens is you'll have a small particle or another small particle. These will move around on top of the support, and by some statistical chance, get close enough to each other that they'll eventually come together and fuse. And that's called particle migration and coalescence. Another process called Ostwald ripening is where just by having high temperatures, the atoms may leave the sample and migrate along the surface or through the air. And if so, they can contact a larger particle, and the larger particle has a higher amount of volume.
Hello?
Yes. Yes.
The slides are not changing.
Really?
Yeah.
I'm on slide 2. Thank you very much for letting me know.
Now
What do you see?
Yeah.
But it's not changing when I'm in the other mode. Okay, that's fine. We can handle that. So we're just going to go ahead and do this, and we're going to do that, and we're going to make them big this way, and it'll be just fine. Is that better?
Yeah, this look good. Please go ahead.
Perfect. Thank you very much for letting me know. I appreciate it. So this was the slide I was talking about, right? So the idea is that you either have the particles moving around and coming together, or because of the high temperature, atoms may leave one particle, travel either along the surface or through the air. And if they land upon a particle that's larger, that larger particle has a higher bulk to surface. And so the bulk energy is lower than surface energy, and it becomes energetically favorable for them to stay on the large particle. So these are the ideas, but it turns out that if you do measurements to look at these processes, there's disagreements about which is the right theory to understand this and how to really work through the details, because they're competing processes. The addition, you can actually have the atoms that leave the catalyst go off into space and evaporate and leave the system. And in fact, we'll show quite a bit of that in the next set. So because these are nanoparticles, right, we're talking about particles that are very, very small, the order of 1 to 10 nanometers, say. Electron microscopy represents really the best capability for looking at this due to the high image resolution. But in particular, you need to have ways of observing the individual processes to try to understand the bulk behavior. Now I have to figure out how to go to the next slide, though. One moment, I guess I am going to have to keep this thing open and small. And there we go. So we've used in-situ electron microscopy for this in order to see these. There's many different things that can happen for in-situ microscopy. You can apply a variety of different stimuli, including light, the idea of doing liquids, electrochemistry. In this case, I'm actually going to show the old-fashioned type of in-situ microscopy, simple heating. But we're also developing and using these methods moving forward to look at this in gaseous environments. I just don't have quite the data yet to pull a talk together on it. But the idea is that by using in-situ microscopy, you can look at individual nanoparticles and track what happens. On the right here is a paper from a number of years ago where we're looking at how this was a group that was looking at this in platinum, studied on silicon nitride membranes. And again, they're tracking individual particles to see how they change as a function of time and temperature. It's interesting, this is not the first attempt at this. I worked at the National Center for Electron Microscopy many years ago, and Helmut Papa was an emeritus professor there with us. And he had a paper in 1976 where they built an entire system, an ultra-high vacuum system, to try to understand these processes. And they kind of came up with the conclusion that in order to really figure out what's going on in both coarsening and mass transport, you would have to have highly accurate statistical nearest neighbor measurements and evaluations of individual particle changes at short time intervals. In other words, you need to see every particle, measure its size and shape as a function of time, and track these over short time intervals to see what happens. And it's interesting to kind of look back at this beautiful old paper and recognize that here we are 50 years ago, and I think finally at a point where we have the capabilities to do exactly that. Our work is based on a camera that we developed jointly with Gatan back at the Center for Functional Nanomaterials at Brookhaven National Laboratory. This is a direct electron detector. It has a very high sensitivity, which you can use for doing low dose microscopy. It's being used for the single particle reconstruction methods in that mode in biological microscopy. But you can also take advantage of that to do high frame rate work. Up to 400 frames per second at 2K by 2K, or 1600 frames a second with just the top strip of it. So that's a really nice capability for capturing these individual events. The challenge with this is that if you do 400 frames a second, you can see that you'll develop 4 terabytes of data in 15 minutes. That's a tremendous amount of data. That data is actually just dumped onto processors that then have to stitch the images back together. It takes quite a bit of time to do so. But if you look at 4 terabytes of data, you recognize that there's simply no way to analyze it without starting to think about sophisticated ways of doing image analysis. So for the next portion of the talk, I'll talk through the things we've been doing to use some of the approaches that have been developed in the computation and probably in the computer science world to take advantage of high computational the high computing speeds that we have, but also the large amounts of data that are present. And so this is the so-called technique of machine learning, which is really just a statistical approach for extracting data from image features. So this is a world that basically my student Jay learned. I have to be honest with you and say that every time he comes into my office to talk about this, he teaches me. I don't teach him. And I think that's really a great relationship to have with your students. So he went off and kind of spent, I would say, a full year or more digging deep into the literature of imaging through machine learning. And really what he tried to do is to see which of the different methods that have been developed by places like Google and Facebook and the like were applicable to the sort of work that we're doing. One of them is a so-called encoder-decoder architecture. And the idea is that basically as you take the image, you break it up into separate units, and you basically find out what levels of features can be extracted at different length scales, and then you kind of rebuild the image that way to understand which portions of the length scale are ones that are capturable. A second one is the so-called U-net architecture. And again, it's a similar idea. You take a given image, you break it up into smaller portions, and you look for common features within the image. And these methods are being used in other approaches. My colleague and friend, Sergey Kalinin and his group down at Oak Ridge are doing this to look at atomically resolved STEM images. And also it's something that's being big in the imaging field overall. So our goal, right, was to characterize this particle evolution through the use of this automated tracking algorithm And if we do it right, what we'll be able to see is we'll be able to track individual nanoparticles as a function of time. The image on the left just basically takes and shows a given particle, its center of mass as a function of time at temperature, as well as you can see that some of them go away. They evolve due to the high temperatures through either Ostwald ripening or evaporation. But by doing this, you can track the individual particles. You can measure the mean size of the particle array. And again, these are the sorts of pieces of information we'll want to look at. Our initial results, we tried to use this encoder-decoder approach. And what we found out was we were unable to capture the information that we needed. We found that the images were both splotchy. If they were too close together, you would get kind of a merging of the particles that missed the stuff in the middle, or either filled in extra data or missed the data in the middle of the larger particles. And so we found that that was an inappropriate approach. Using this UNet architecture, we were able to get very reasonable segmentation, but we did have problems associated with image resolution. You can see that there's parts of it that are just picked up in the background that aren't real. So what we were finding too is that as we have these high resolution images that are 2K by 2K or 1K by 1K, we had a hard time also picking up the edge information. And when we're trying to look at the very subtle nature of nanoparticle coarsening, getting accurate measurements of the edge became an important part of all of this. So what we did is we did a couple of different things. We would go through and use a convolutional layer to spread the image intensity. That was necessary because in the electron microscope, you don't have a perfectly flat illumination onto the sample. And that allowed us to kind of normalize the intensity variations across the image. Basically, it's because if you have an electron source and you use the optics, you just cannot get an absolutely uniform image illumination. That's with a cold field emission gun or a Schottky field emission gun, either one. We then also added in additional convolutional layers that allowed us to kind of capture information features that were of different spatial lengths. And we also then would pre-process these back with a little bit of a blur to basically suppress the high frequency noise that came out of the process. And I recognize I'm probably we're doing okay time-wise. So what we noticed is that when we did this, we were able to get very good segmentation of our images through the use of these different approaches. And by doing this batch normalization process, we were able to produce very stable and reproducible image analyses. And it really gave us nice detection of the particles, but also compared to using a full deep learning UNet, we actually found that it gave us a shorter amount of overall processing time. What we can find is, and this gets a little bit into the image analysis stuff, but basically what happened is that we were really finding out that basically the process of going through this neural network led us to creating kind of its own image filter. In other words, we could go through and use the neural network to understand at each different layer what sort of filtering was being used. And then we worked our way backward to create kind of a general filter for these types of images. And what we found is by applying that general filter, we can speed up the image analysis overall and automate it even much more quickly while giving a very similar overall performance. So effectively, it was by combining several known filters within the image analysis space, figuring out the relative weights of those filters through the use of the artificial UNet network. And that basically gives us the ability to extract all this information. Now, once you have this, you can go through and apply it to solve real science problems. And so here, what we were doing is we took gold nanoparticles that were synthesized with a colloidal method. These gold nanoparticles are more or less all the same size. The idea then is that by having a similar size network, we have very small perturbations in terms of the overall average size, and that leads to kind of interesting complications around what the atoms are going to do. We also used a method where we were able to put specific ligands on the nanoparticles that gave them a relatively controlled spacing. That turned out to be interesting, as you'll see from the data later. But basically what we did is we used bright field TEM, good old standard bright field TEM at relatively low magnifications, and just held the sample at 900 degrees C for about an hour. In this case, we weren't taking advantage of the full 400 frames per second. It wasn't necessary, but I think that you can see that that's something that can motivate things moving forward. But basically here we're showing the data at the beginning and at the end. The beginning is the red circles. This is where all the particles were. And then you can see after 1 hour which particles remained. We've used that autoencoder, that developed filter that we had for doing the rapid automated analysis. And then from that, we can take advantage of the quantitative information to learn more about the materials processes. So first of all, what do we see? Well, you can look at this image and see that particles go away, right? There are many fewer of them after an hour than there were at the beginning. But you'll also notice that there are none of them that are much larger. Just quick visual inspection shows you that. Some of them have maintained their size, but really none of them have grown large in comparison to the others. So this really tells you immediately that Ostwald ripening is not a key process in this. Also, we do see that those particles that remain are generally in the same place that they were. And that again indicates that center of mass motion or particle migration was not one of the key processes in the system. And if we do a quantitative measurement of the particle size as a function of time, you can see that the initial particle size is larger, around 4.2-ish nanometers, than the final particle size. And you can see that there's a lower number of particles with time, again, consistent with the imaging. And that tells you really that what must be happening is that the gold must be evaporating. So at high temperature, the particles leave, and instead of just simply migrating and finding another place to go, because we're in the high vacuum of the TEM, they're pumped away and leave the system. So this is a nice set of quantitative data. We can do more with this. We can look at each individual particle and track it as a function of time. Again, what you'll see that there are always particles that are leaving the system. You'll also note several key features in this. They tend to have some gradual slope until a critical moment where the particle size drops quite quickly. We'll look at that later. You'll also notice that the general trend is that there's a decrease in particle size, but also at the end of our experiment, you'll notice that around 3 nanometers or so, most of the particles are shrinking towards that, but not much smaller than that. And this is, in fact, the overall diameter in this case. We do have evidence of mass transport between the particles. One way that we know this is that if we look at individual particles and track them as a function of time, here's a set of 3, red, blue, and green. And what you'll notice is that there is some small amount of motion of the center of mass for the red and the green. And eventually those disappear. You'll notice that the green particle, however, more or less stays the same size. And you'll also notice that the direction of this is kind of interesting. It's almost as though these 2 particles are gradually giving up their gold to this one stable particle here that is in green. If we look overall, in this picture, we're actually tracking and showing a picture that shows the evolution with time. We're using the same sort of color scheme we used here, where the pinkish color is 0 and the reddish color is 3000. And again, what you can see is that instead of having the particles shrink uniformly, which would be what would be consistent with just a pure evaporation of the gold, you'll notice that they shrink from one side. And again, that's indicative of having some of the gold transporting across the surface and contributing to other nanoparticles. So there are thus competing mechanisms happening, one of which is just the simple evaporation process where the gold leaves and goes through the air and is pumped away by the vacuum, and a separate process where the gold is able to migrate along the surface, contribute its atoms to other particles through a process of surface diffusion. Again, I would say that in absence of having this detailed and time-evolved information about the individual nanoparticles, we would have a struggle to be able to see this behavior and understand the 2 processes. So Peter Voorhees is a professor at Northwestern who's been looking at Ostwald ripening for many years. So we reached out to him with this set of data to help us develop a model to help us kind of go through this. I don't want to go through the details, but I think the material scientists in the crowd will recognize, familiar equations. Basically, what we did is we used a quasi-stationary solution to the diffusion equation, and we included the possibility of having mass loss from a given particle at the contact line between where the particle sits upon the surface. We get a rather complex equation here, but this is the form for it. And you see, the concentration at infinity versus an equilibrium concentration as part of that. We also included in the possibility of having the vapor pressure lead to diffusion, modified by the Gibbs-Thompson size effect. That's this term here. Basically, as the particles get smaller and smaller, there's an increased Gibbs-Thompson pressure on the particle, which may accelerate the removal of atoms. And in fact, as we looked at the data, we see that there's that gradual decrease in all of the particle sizes until they drop off a cliff. And we speculated that that was due to the Gibbs-Thompson effect, and then we'll show you that we actually can fit that. So we combine these together. It gives a rather messy equation. We parameterize this, and normally I would be very upset by an equation that has 5 separate fitting parameters, and think to myself, well, no matter how good the model is, I'm not so sure I can do much with anything that has 5 fitting parameters. But again, an advantage to having the extraordinarily large amount of data that we have is we can actually go through and fit each individual particle. But we can also, we had a total of like 350 particles involved in the image. And in so doing, you start to see that there's consistencies between the fits. You start to be able to use the self-reinforcing nature of the consistency to constrain the fits. And from this, we were actually able to obtain parameters that could be extracted from the model that were measurables of real phenomena. The diffusion coefficients, the partial pressure, the surface energy, as well as the contact angle. And we were able to go through and obtain these through the quantitative fits of the 300 and some nanoparticles and compare them with values from either the literature, or in the case of the contact angle, we did a separate experiment to measure that using high resolution microscopy. And again, we find extremely good fit and extremely good correspondence with other measurements, which gives us a lot of faith that this model that we've developed is able to capture the process as well. One of the other things that came out of this is that among the different parts of this, there's this value, this value here, and this is the screening length. It's basically how far does a nanoparticle look around itself to see gold coming in through surface diffusion. And from our fits, we were able to measure that, and we found that the first mean of that actually resided exactly at the interparticle distance, whereas the second mean was about 80 nanometers or so, which was actually the entire size of the system. And so it basically says that really the screening length means that there's actually 2 continuous processes in the surface diffusion, one of which is a frequent transfer of information via surface migration from particle to particle with the nearest neighbors. But also, if you look outwards, there's a mean field of particle contributions coming into each individual nanoparticle that can be directly measured out of this data. So that's pretty neat. And we also found that if we look at the particles that remained, basically we found that anything that got below 1.5 nanometers would go through this very rapid decline. And that was associated with the effect of the Gibbs-Thompson pressure. But with time, anything that got was higher than that would actually stabilize to a mean particle size at around 1.5 nanometers. So again, kind of indicative of the utility of having this high data set. This stable main particle size can be measured either by looking at the mean particle radius as a function of time, or you can actually see that it comes directly out of our fitting model as well, and indicates that if you can maintain a given size, you're not going to undergo an evaporation that leads to particle loss. So, just to kind of conclude this, maybe bringing us back onto the scheduled time a little bit, I think that the nice thing about this piece of work, and I feel able to say that because really I'm mostly just bragging about how well my student did with this, was that he was able to take advantage of this automated process for image analysis that he developed and use this to develop a model that allows us to extract physical properties that match the expectations of the model. This mean field model captures very general behaviors, but it does not describe the local interactions. We actually can see that although you have the general model capturing this, we can also extract out of that the interparticle interaction distances. And then really what we're learning from this is that our next steps in this process have to be to develop computational models that follow each individual nanoparticle and understand how the processes work on a local scale in order to develop a mean field theory that is overall accurate. And we're hoping that the National Science Foundation lets us have another 3 years of work to do that. It really does also show that there's critical particle sizes for each mechanisms. And really, by understanding that, you can start to think about how to design nanoparticles to be stable as a function of time and temperature. And so with that, I think I'll conclude the talk and offer an opportunity for answering questions that you may have.
Thank you, Professor Stack. So I would like to invite questions.
I see one from Casey.
Yeah,
Maybe.
Thank you very much. My first in-situ microscopy was in 1976 when that came out in Philips 310.
Yep.
And it
That
was
the first
very hard
microscope I
work.
used.
3 days I didn't sit. But ultimately, entire data set could not be analyzed because those days you do not have these automations, and I could not differentiate between surface migrations and due to the age effect of temperature, thermal migration. So nothing could be done out of that. However, one thing we have observed when we are doing in Oxford high voltage microscope, Brian and myself, Brian Cantor and myself, which I wonder whether you have observed. We have seen, we are looking at lead in aluminum.
Oh, no, I know those papers, yeah.
But what we have never published, we have all these videos, is that some of the particles migrate, come close, and then it becomes bigger particle.
Yep.
But some particle repel. That we never understood.
So actually, it's interesting you bring that up. So actually, one of the things, so my student came into my office yesterday. We kind of discuss some of his latest observations. And this is, instead of being colloidal gold, we're now doing evaporated gold. So it's a hemispherical gold on top of a surface. And he was noticing in particular that if you have one particle on the screen, another here, and they're round, as they start to migrate towards each other, they actually will first facet and form 1-1-1 facets. And then once that facet's fully formed, they instantaneously jump together and coarsen. And the issue with that is that he's got some very nice individual observations, a small number of them, but you have to really do that at quite high magnification. So he and I were having a debate about whether or not to spend a lot of time trying to do high resolution imaging and hoping, just to have that happen in the field of view. But it does, I would say, yes, I've seen things like that, and it's an interesting phenomena for sure.
You just find out whether there's any repelling phenomena.
Right, exactly, yeah.
Not many, but some repels we never understood.
Yeah, so I would agree that's an interesting observation. Hopefully we'll have a chance to have a look at it.
Can I ask a question, Ravi Shankar?
Please, yes. Please.
Hi, Eric. Wonderful talk. Thanks very much. So I really love that graph where you showed how the size changes, and I was just wondering, the vapor pressure changes exactly the same way, and that's what you actually showed. My question is actually related to the use of TEM versus STEM mode in these kinds of experiments. Your comments on that. And the other thing is that if this were to be done for supported particles, for example, right? How would the contrast from the substrate or the support, which is also varying, right? How would you take care of that?
Great question. So first of all, one of the advantages to TEM is its ability to do high frame rates. So I think that most everything else that we do in our laboratory, we do in STEM. It's a as much as I hate to admit it, as a former TEM and high resolution sort of person, the STEM's just better these days on a microscope that's capable of it for most everything. But in terms of the things that need speed, the TEM work in bright field mode is often best. But these things are actually happening relatively slow, so it could be done in STEM as well. That was question number 1. And can you repeat question number 2? I'm sorry, it's still early in the morning here.
Supported particles that is
Yes. So these experiments we're doing very deliberately on flat supports. So this was on silicon nitride, a model support, and that's because we're basically trying to start off. I mean, I have like I'm getting old enough that it's okay to say I've got a 15-year goal, you know, on this to try to start off with gold on nitride and do it in vacuum, and now we're moving on to platinum, you know, on nitride, but with reduction and oxidation and gas experiments. And then we're going to move on and do ALD surfaces where we can vary the surface structure. We're going to move on and do platinum palladium, for example, as a bimetallic. And my kind of goal over the next, I mean, it sounds crazy, but you know, when I retire at age 65, it would be nice to be able to say that I think we've worked our way through from the simplest of all systems, gold, right? And added degrees of complication depending upon the relative rate or desire of a given metal to oxidize or reduce, and to understand that also as a function of surface. So your questions are great, and they're the same questions that are going to motivate us for the next decade.
Okay, thanks very much. Wonderful work.
And also, Christian asked, just real quickly, Christian asked in the chat. So we know there's no ligands, and we know that because otherwise, we would be seeing as a function. So basically we go through and do a lot of plasma cleaning to get rid of all that. But if the ligands were there, we would be seeing a different amount of stuff. Basically I'll go through, I'll send you the paper. We went through and confirmed there's no ligands, but it's a good point. And, but because it's the first thing I asked the student, I'm like, how do you know that the carbon's gone? But because it's a big part of it, but we're also doing this work with evaporated systems as well. So there's another question.
There are some raised hands. Professor Abhay Gautam, yep. I can see them first.
Yeah, hi. Nice talk, Eric. Really nice work. I guess if that algorithm can be put into one of the plugins for one of any of the softwares, I think the PhD students would be very grateful because.
So just to be clear, that just to answer that before you go, the papers, we published a paper on that, but we've also got a full set of stuff on GitHub for you to download it. And also I had an undergraduate student write a tutorial on its usage. So if you go to the GitHub, we have a whole separate web page where Lena Vyas went through and wrote here's how you use the Python notebooks in order to make this easy for people. And that was her undergraduate project with us, and it's beautifully done. She did a great job. So please use it. And if anyone here has a question where to find that, give me an email, and I'd be happy to show it to you.
So one quick question. So a lot of times small gold particles tend to rotate under the influence of the beam. So in your tracking algorithm, can you detect those events or there's no?
So I know what you mean. And that's something that you'll see often when you're doing high resolution work with a high image dose, no doubt about it. But this is actually, we're doing this at pretty low voltages. So I would say that the relative beam flux is quite small in comparison. Especially when you're thinking about this being at 900 degrees Celsius. The electron beam can certainly affect materials and give problems that are important. But as you go to 900 degrees C, I think the 900 degrees C is the driving force a lot more than the flux of a beam at a relatively low dose.
Thank you. That's all.
Sure. Professor Dipankar Banerjee, do you have a question? Yes. Not then. Professor Satyam, your hand appears to be raised.
Eric, Dipankar had my mic off as usual.
Sure, no problem.
It's fascinating. I was curious, when you conceived the study, did you actually think of it as a competition between evaporation and coarsening?
No.
So the evaporation emerged as a result of the study.
Correct. That's correct. We were, I mean, the goal of this was to look at osmotic ripening, but it didn't happen. Yes. And so, and interestingly, as I say, this was with colloidal gold, but the data for evaporated gold is turning out to be exactly the same. And more or less at the same temperature. So the data my student was showing me just the other day was, nothing happens at 700, nothing happens at 800, nothing happens at 850, and at 900, all of a sudden the evaporation starts to kick in. So he's now going through and trying to put an activation barrier on that, and you determine activation energy on that. So what I would say that's also really interesting, if you look in the literature, and we have a separate paper that we're looking at palladium platinum on alumina that we published for working with BASF Corporation, and we see evaporation there too. And I think that it's more prevalent in hydrogen than in oxygen. No, in oxygen than in hydrogen. Sorry. So I think that there may be something about the nobility of gold that leads it to be less prone to have the particle migration happening, as well as to have the gold leave the nanoparticle for Ostwald ripening. But I'm excited about the next experiments where we're going to do the platinum and oxygen and hydrogen to see if there's a difference between how platinum operates when it's reduced versus oxidized, and if there's some kind of sense that the clean particle, the one in hydrogen, likes to stay together, whereas the one in oxygen, it may be that the oxygen helps to volatilize the material. So again, these are the things we'll be studying and looking forward to studying.
All right, thank you.
Professor Satyam. I think probably the hand got raised accidentally. So, Professor Stack, I also have a question. I saw in slide 22 showed the direction of portioning from 2 different nanoparticles towards 1 nanoparticle. I mean, the diffusion direction being shown. So, what actually is driving the diffusion here? Is that you said that Ostwald ripening is not happening, and all the particles appear to be of similar size. So what actually is responsible for migration?
I don't know. I don't know why one particle will do something and another will not. But I think it may be, if you look, you can still see my screen, right?
Yeah.
I think it may be that there's a cascade of different things that happen. You'll notice that if you look around this grouping of particles, that all the ones on the outside disappear, right? And you'll notice that in the densest regions, they do not as much. But so there's almost like, I have a feeling, but we haven't figured this out yet quantitatively. But I have a feeling that that for those in the center here, because they're surrounded by this interaction length that's more or less equal, they're able to communicate and provide, atoms back and forth in a way. But with the ones that are on the edge, once they have some atoms go this way, it goes away, right? And so I think there's some collective behavior in this, perhaps, that may be expressing itself, but I don't know that I don't know how yet to quantify that or understand.
Yeah, it's very interesting phenomenon, needs to be investigated more. Okay, there are a couple of other questions. Professor Chandrasekhar Tiwari.
I'm really hopeful that the reviewers for my NSF proposal renewal agree.
yeah. Thank you. A couple of other questions are being asked. Professor Chandrasekhar Tiwari would like to ask a question.
Yeah. Hi, Eric. It's fantastic talk. Apart from this metal nanoparticle, I was just wondering, 2D materials, especially recently this MOS2 or other TMDCs are coming up. The liquid cell holder, when we try to do the experiment, we really don't get contrast. So do you have any tips to handle some of these low contrast materials?
2D materials are very difficult. Please send me an email and I'll send you another paper we just published on blowing bubbles in liquid cell holders to help us with image resolution. But MOS2 is tough because it's very thin. We have something in the supplemental on that.
Okay, perfect. Thank you. I'll drop you email.
There is one more question in the chat. What is the role of support materials on evaporation of these critical size nanoparticles? If it is anchored with substrate tightly, will this critical size change?
The support, as I say, we have only been using silicon nitride just because these are our first experiments. My goal was to do the simplest of all possible things, a noble metal of gold on an amorphous, irreactive substrate, a non-reactive substrate. There is no doubt that having different substrates will have different effects. It'll change the surface energy. It'll change the contact line energy. I think surface roughness is going to be a key aspect in this as well. And those are all phenomena that we look forward to investigating.
Thank you. And the next question is for Professor Satyam. You can, I don't know whether you're able to see it or not. So he has asked, we had gold on silicon 110. We found gold silicon nanorod formation. Is this atom by diffusion or by particle-particle diffusion, particle-by-particle diffusion?
I'm not so sure that I could answer that without seeing more detail. I'm sorry. I mean, I think that what I would say is that many of these things are so complex that that it's hard to know without looking at data in more detail.
Yeah, I think there's no more question. So let us all join in thanking Professor Stack profusely for a very nice presentation today. We all learned a lot. So thank you, Professor Stack. We give
Sure,
you
I'm happy. Yeah.
So someday we'll be
So again, whoever
the
person who asked me the question on the liquid cell stuff, send me a note and I'll send you this paper. Okay.
Sure.
Okay.
Thank you very much, Professor.
And Christian, I'm sorry, it's 9 o'clock here in the US, and I'm gonna have to go on to do some other meetings. So I apologize for missing your presentation.
No worries. It was nice to listen to yours.
Nice to see you. Take care.
So it's my pleasure to invite the next speaker, Professor Dr. Christian Kugel. He is the Deputy Head of the Karlsruhe Nano Micro Facility and Group Leader Electron Microscopy Facility over there. He is Professor for In-situ Electron Microscopy at TU Technical University Darmstadt in Germany. And prior to that, he was also Principal Investigator at Helmholtz Institute Ulm. And he was also the Group Leader of Electron Microscopy and Spectroscopy Group at Karlsruhe Institute of Technology, Karlsruhe, Germany, since 2009. And before that, he has also served as Group Leader at Fraunhofer of Nanostructure and Surface Analysis Group at Fraunhofer, IFM, Germany, Bremen. And he has also worked as Senior Application Specialist on TEM at Philips Research Lab, FEI company, Eindhoven, Netherlands. So he has a detailed. He has also research experience in USA. He was at University of Michigan, Ann Arbor, and also at Max Planck Polymer Research, that's called in Germany. And so his research interests are in solving for materials related questions by high-end structural characterization using electron microscopy, and new electron microscopy characterization and structural approaches for specific applications, in-situ electron microscopy and electron tomography, mechanical properties and structure of nanocrystalline amorphous metals, interfaces and processes, energy storage systems, battery materials, catalysts, nanocomposites, hybrid, LED, stroke PV, carbo nanomaterials, nanoparticles, magnetic materials. So with this brief introduction, I would like to invite Professor Christian Kugel and present his talk. Thank you for agreeing to present on behalf of our organizer. I thank you for accepting the invitation to present, and please go ahead.
Yeah, thank you very much for the introduction. Good evening, everybody. Can you see my slides already?
Yes, you can see.
Okay, very good. Yeah, so thank you very much for the opportunity to come here. It's really nice to be back in India, even though this is only virtually, but it's my pleasure to introduce some of the work that we have been doing in situ electron microscopy over the last few years. And here for this presentation, I want to focus on mechanical and thermal processes in nanocrystalline metals and metallic glasses, and there in particular on how to combine in situ TEM with various advanced imaging techniques to get an as complete characterization of complex materials and processes. And the work that I'm going to show is mainly the work of some of my current and former PhD students, Ankush Kashiva and Lakshmi Manta, as well as Suya Liu. And they were supported very well by my colleague Xiaoke Mu. And the motive, oops, is it moving? Can you see the next slide? Oops.
No, next slide is not coming, but we can see some movement in the front slide. Yeah, now it has come.
Now it should be there. Yeah, and so the The motivation for our work, I think, is fairly straightforward, that in general, we want to link the synthesis and processing of materials with their properties and performance, and actually also push this a step forward to not only really look at materials, but also make a step towards devices ultimately to understand their performance and function. And in general, with the in-situ microscopy, we are really trying to strengthen this by looking at or providing a detailed structural understanding of the transitions in some materials. And in particular, most important, I would say, is really catching some of the transient stages so that we get a better idea of how we can interpret the processes in our materials. And in general, I agree very much with Eric's comment that we really need statistical information as well as local information for a meaningful analysis here. However, in addition, what is also really quite important and often a challenge, in my opinion, is how to relate what we're seeing in the microscope really to the true bulk properties that in principle we would want to understand. And I think part of the difference is simply the way from a bulk sample to a thin film. And I think here everybody is aware of the typical challenges that we're facing with, let's say, a normal FIB sample preparation like gallium implantation, platinum contamination, or also with the mechanical preparation, just the damage that we might be generating on the surface. However, I think there's a lot more to this. And one is that because we're dealing now with very thin samples for the TEM, the residual atmosphere, even in the microscope, is playing or can at least play a significant role. Then we also have to really inherently think about it. What kind of surface or bulk processes could happen? For example, if you're looking at migration, you really have migration of your material through the bulk of it, or is this, or could this be surface migration? Then there might also be various surface relaxation processes involved. And all of this is already there before we start to turn on the electron beam. And then with the electron beam, we do have to consider knock-on damage and ionization. And I think there, I mean, this has been very extensively investigated with a lot of the organic and battery materials. But it might not only be a challenge where you're changing the true structure of your reaction of your materials, but it could also be even changing your reaction pathways without completely destroying the material. And just to give you an idea, what I mean here is when we look at some complex reaction energy landscape where a normal reaction ex-situ would follow this kind of complex path with the electron beam, whether this being ionization or maybe knock-on activation, we're providing some activation, and from there we might really follow a completely different path towards the reaction products. And this is something that is very, very difficult to consider accurately what is going on in the microscope here. And to some extent, we can just hope if we see the same products that we would see in the ex-situ reaction, that the processes involved are also similar. However, in any case, I would always be very hesitant with giving absolute reaction kinetics out of in-situ TEM measurements. Nevertheless, I think in-situ TEM really is a great tool to understand materials, in particular with the recent developments that we have seen on improving sensitivity of the detectors with the high-speed cameras that are now available. We really have opened up the pathway to a lot of new understanding of dynamic processes in materials. And with this presentation, I want to give you a bit of an overview, talking about what we can learn from the different experiments, but also where some of the challenges that I was mentioning before, where they are coming from. And I think here what I will talk about is a little bit first of metallic glasses, thermal treatment and mechanical deformation, and then talking about some nanocrystalline methods. But let me start here with the crystallization of a nickel zirconium metallic glass. We're looking here at this metallic ribbon here with this composition close to the eutectic point, where from ex-situ annealing experiments, it's already well known that this is reacting to form a nickel-rich product, a nickel-rich product here and a zirconium-rich product. And when you're following this with in-situ X-ray diffraction, you can see that here somewhere around 855K. This transformation is occurring, and then at around 1000 Kelvin, the final products are formed, and those are very well characterized by X-ray diffraction. But the question is, what is really happening here at these intermediate stages? Is there any real change in the structure? And also, can we potentially relate this to some of the glass structure? And the motivation for this is from the fact when we look at the metallic glass in high resolution TEM, this really looks quite uniform amorphous. But when we're using stem pair distribution analysis of the glass spun ribbon, we then locally analyze the diffraction patterns by pair distribution analysis. What you can see is that there's regions with slightly different medium range order, so different molecular packing present. And this will also be an indication potentially for some slight compositional variations. And what you can see here is a plot of these changes. We're just following the maximum position, or the position of this maximum for the different locations. With this, you identify some kind of a small patches of a few nanometer sizes, which also fit to some of the intensity variations that we see in the. And so we wanted to see if this might be related to some of the crystallization effects. And so we started the crystallization with simple heating experiments inside the TEM. And what you can see is that here at about 723 Kelvin, we're starting to see the first really good information of some reaction products. If you're holding this longer, then this will continue. And then when you're further increasing the temperature, then the crystallization really proceeds throughout the whole sample. And this temperature is lower than what we see in the X-ray experiments, but this is really quite often the case. I think this is some mixture typically between electron beam activation of the material and also some enhanced diffusion possibility. Yeah, and then when you look into the reaction products form, if you're just looking at a small area, then you might see here high resolution images like this one, or the one on the right side. And you can index this quite clearly to nickel poor phase, and here's the nickel rich phase. And to some extent, you could with this conclude that we have found our products. However, luckily, the student really did pay attention of what else is going on and carefully investigated a large area of the sample. And what she found was that actually we also do form quite a lot of zirconium oxide. And the zirconium oxide formation is then probably also triggering the formation of a very nickel-rich phase, which should not be formed at all. This is what we can see here. With a very elevated temperature, we found in the middle phase zircon monoxide that is apparently also formed here. And these phases are only observed when we're doing the heating in situ inside the microscope, but not at all ex situ. And we can quantify this a little bit more. Simply using electron diffraction to average over a large area of the sample. When you see the evolution of the diffraction pattern, then we can analyze this with a little linear least square fitting to get the phase compositions out. And what we can see is that initially we're crystallizing zirconium oxide and this very nickel-rich phase. And then as the temperature and time is increasing, we're at some point also getting the nickel-10 zirconium 7 that we expected. The temperature is actually relatively close to where you would expect it. But this is really only a small a part of the overall reaction product. The very nickel-rich phase is quite significant in the sample, and this really can only be explained by the fact that we're pushing our average melt composition towards a nickel-rich phase because we're precipitating a lot of zirconium oxide out of the system by the oxidation. And this is also the reason why the actual nickel 21 zirconium 8 phase that we've been expecting based on the bulk experiments is visible, but only to a very small amount. We're essentially already pushed the overall composition of the melt so far. This is hardly formed. And this oxidation you can also then, with a careful analysis, afterwards see as the in an energy filter TEM map. So what you can see here, we have these oxidized patches. This is zirconium dioxide or zirconium monoxide. We have as a major part the nickel-rich phase, and then these small blobs inside the nickel-rich phase. This is really the zirconium-rich phase. So these observations have really nothing to do anymore with the ex-situ investigations, but are just a complete shift of the reaction because we were dynamically taking out the zirconium from the mixture. And this has nothing to do with any original contamination of the sample, but is very clearly related to the residual oxygen and water that is in the column of our microscope. Yeah, but then nevertheless, to further understand how this is evolving, we also did the comparable experiments now with ex-situ heating. And there you can see a phase formation that fits much better to the expectation. So we have here the residual amorphous structure, and inside we see a crystallization of the nickel-rich phase, and around it the crystallization of the zirconium-rich phase. We do high resolution TEM, and here we see the characteristic nickel-zirconium structure that we would expect here. However, when we go look at the zirconium-rich phase, then the story is a little bit different. You see this kind of characteristic pattern here. And when we're analyzing this, what you can see is that here are patches which match very well to the zirconium-rich structure, but they are separated by some other structure. Looking at the residual composition, this is a very nickel-rich phase, and we try to do some DFT analysis of these structures, and essentially these repeats unit, either one of the zirconium-rich phase, either a nickel layer or this bilayer structure, is energetically quite favorable compared to the individual structures. And interestingly, when you look in detail at the images, what you can also see is that this is really a transition product, where we typically have this two layers of the zirconium-rich phase and the nickel-rich phase. And for example, when you look here at this structure, here we can still see the nickel-rich phase, but then it kind of transitions into the zirconium-rich structure. So what is happening in this material most likely is that this is the diffusion pathway for the nickel to get out of the zirconium-rich phase in the, during the annealing experiment. And unfortunately, this would be very nice to observe in situ, at least with the oxidation that we currently have in the system. This is not possible. Potentially, maybe using a gas holder might be a solution to overcome the problem. Yeah, so but I think with this, we still learned a lot from the in situ and the ex situ experiments about the system. But what I want to then now switch is to some more mechanical deformation. And this is here focusing on shear band formation in a metallic glass. This is the first example looking at Vitrolloy 105, which we performed, and then looked at the shear bands formed. And the shear bands themselves are actually in this Vitrolloy very hard to see. You mostly see it from the shear offset. And then you can kind of get an idea where the shear band is going. However, when you analyze it very carefully, again with a stem pair distribution mapping, one of the things that you can, for example, show in these materials is when you look here at this area, this is our shear band, and we did stem PDF mapping around the shear band, and based on the medium range order in the material, we can in principle see the difference between clusters that are edge, face, edge, corner or face sharing clusters. They do have here noticeably different signatures. And when we analyzed our stem pair distribution function mapping, we actually did see a characteristic shift directly at the shear band. And when we're now plotting here the concentration of these face sharing clusters, we see that this is a minimum at the shear band as well as at a few locations around it, which fits very well to the expectation that you need to break up those face sharing clusters in the shear band formation. They are the most stiff clusters in the system, and then they are rearranging to form some either face or edge sharing bonds. And so this is the first direct evidence for this rearrangement inside the shear band. And ideally, we would want to see something like this in situ. And here, together with the group of Gerhard Wilde in Münster, We have already a while ago done some in-situ straining experiments. This was now on a slightly different glass, an aluminum yttrium iron glass, where exactly the idea was, can we somehow follow the shear band formation in situ and see how they're propagating, bifurcating, and maybe also if we can follow any structural changes. And when you look at these STEM images here, the shear band we were analyzing is indicated here in the white box. And when we look at the HADF STEM signal, you can see the change in the total scattering strength in the shear band. And this could either be due to density differences or due to changes in the sample thickness. And already a while ago, with the people in Münster, we have established a process how to separate those two by doing fold thickness measurements in yields, using yield spectroscopy. And when we're combining this, then we can see that here in this case, the whole shear band density, or what the scattering strength difference, is really due to changes in the foil thickness. And we have done some independent AFM measurements that actually show that you are forming a meniscus here at the top of the shear band. And the other indication that where you can see this from is this shear band is something like 40 to 70 nanometer wide, which is much wider than a normal shear band. And a normal shear band formed ex situ looks something like this in exactly it was actually the same batch of material. So you can see these characteristic oscillating high density, low density regions, very narrow in the shear band, as has been established by the group in Münster already for quite a number of samples. And when you look at this here, then you can see again the materials density or thickness changes in the HADF STEM image. So here it's the increase. In this part of the shear band, it's a decrease. But in this case, when you're looking at the yields measurement, there is really no change in the sample thickness. So clearly indicating that these small density changes that we see here are due to real density changes and has nothing to do with the thickness change. And what this means is that here in this case, we can probably really not relate what we're seeing in situ to the real shear band formation. Even so, we have been very careful with the sample preparation. So this was done with electropolishing to really keep a smooth surface, no FIP involved at all. So this is, I would say, as good as you can do it currently. But the problem is that we have very different sample dimensions from the bulk here. So the possibility for stress relaxation from the surface is there. And most likely we have a significant mobility of atoms on the surface, which can then help to form the meniscus. And whether or not this is further activated by the electron beam, lowering the activation energy for some of these surface migrations, this is a little bit hard to judge. But I think in any case, it's really clear that the formation properties for the shear bands in situ and at ex situ are quite different, and we cannot really compare those results. And this is not what we had been hoping for originally, but I think it is also really important to get an idea where you cannot relate the in situ experiments anymore to some bulk experiments. Yeah, but now let me come to some much more positive examples where we really did learn a lot about the system behavior from in situ investigations, and where I'm convinced that this is really also representing true observations. And the first example I want to show here is looking at compositionally complex alloys as interesting materials for mechanical applications. They have, to some extent, good ductility and a reasonably high tensile strength. And what we wanted to look for is starting from something in the area of the counter alloy. How can we improve the strength of the material on the one hand by Hall patch strengthening, and then with a nanocrystalline structure stabilizing this by grain boundary segregation, and further strengthen it with precipitation hardening and solid solution strengthening. And the approach that was used by our collaborators in Irvine and here in our institute at the KIT was to start from something closely related to the character alloy, but mostly introducing here copper because of the high positive enthalpy of mixing, so that this would drive the system a little bit towards precipitation. If you're doing this in the bulk or in a coarse-grained material, you don't really see a whole lot of structural changes, but if you're deforming it by high pressure torsion and then annealing, you see the formation of a second phase. It's an iron cobalt phase, as has also been predicted from Kalfat simulations. However, when you look here at the DSC of these annealing experiments, then you can see that there's a lot of fluctuations indicating various small processes in between. And this is really not understood where they are coming from these bulk experiments. And so we started to look at the system first to get an idea of the ex-situ structure. So initially we have the uniform elongated structure from the high pressure torsion experiments. And then after annealing to 600 degrees, you start to see here the formation of the B2 phase. When you're looking at the orientation relationships using the ACOM system, you see that all of these precipitates either have a Nishiyama-Wassermann or a Kirchhoff-Sachs orientation relationship to the matrix, at least to one of the grains. Yeah, so that this fits. We can also see this in high resolution TEM when we're looking here at the precipitate boundary with the matrix. This happens to be the Kirchhoff-Sachs orientation relationship and seems to be a mostly coherent, sometimes a little semi-coherent interface with a few dislocations present here. When we look at the chemistry, then this becomes much more difficult. So we can confirm the iron cobalt precipitation for the B2 phase. And then at the grain boundaries, you can see here nickel enrichment and manganese enrichment. And the copper, when you're looking carefully, is really segregating mostly around the iron cobalt nanoparticles. And when you look at this in a little bit more detail, now, starting with a statistical analysis of this STEM EELS data using principal component analysis, then you see the matrix phase, the precipitates, and you can identify two statistically meaningful grain boundary phases, one being a manganese nickel rich and the second one being rich in cobalt, nickel, and copper. And when you look at the distribution, you can see that these distributions are really varying locally quite significantly, suggesting that there is some clear dependence on the local grain boundary structure, maybe also on the diffusivity at the grain boundary. And this is, yeah, we see the correlation. We have not been able to analyze them in detail, but for example, you can very nicely see it when you look at this grain boundary here at the very bottom, where we see that this is one single grain boundary with a step. And on the left side of the step, we have a uniform manganese and nickel distribution. And then on the right side, we see quite a different behavior, much more nickel rich and a lot of copper segregation there, suggesting that really with this change in grain boundary structure, we do see changes in the precipitation behavior. And this FTEM analysis is definitely pushed to the limit with this here, but this has also been further confirmed with independent atom probe tomography measurements, where we find actually 3 grain boundary phases, because apparently the manganese nickel is not just one phase, but there's 2 different characteristic compositions that have been detected by atom probe tomography. But the disadvantage of atom probe tomography is that, yeah, it's a much more local information, so we cannot as easily judge the correlation with the grain boundary structure. And yeah, just out of interest, we also looked at the higher temperatures, and there we see an interesting effect. When we're heating this to 600 degrees, looking at the grain boundary segregation, you can see here that the grain boundaries are still enriched in manganese, nickel, and to some extent also copper. But here you see kind of a tail left behind the grain boundary, always on one side of the boundary. And we interpret this as a clear indication for solid drag in these systems, where the original enrichment with nickel, manganese, and copper could not, at least the nickel and manganese, could not follow the grain growth, and then this, this tail was left behind with nickel and manganese enriched structures. However, in none of these cases we saw any kind of crystallographic changes, so it's all of this is still an FCC phase. Yeah, to get a better idea of the real evolution in the system, we then did in-situ analysis, looking here at the orientation mapping. And when you look at the phase evolution and the texture evolution, essentially there is no texture evolution, but the precipitate formation, you can see they are always starting to form at triple points between grains, suggesting that it's probably the higher diffusion rate at the triple points, maybe at the, along the grain boundaries that lead to the precipitation there. And we can actually start to quantify this. And what we can then see is we first have the formation of these precipitates, and at higher temperatures they are dissolving again. And when we compare this with the grain growth of the matrix phase, the grain growth only starts really when the precipitates have significantly decreased, suggesting that they help to prevent grain growth. And the and here we can also confirm again the Nishiyama, Wasserman, and Kuchimov-Sachs orientation relationships that we have already seen ex situ, and now in the growth process we can really see that they tend to grow from these well-defined crystallographic, or forming these well-defined crystallographic orientation relationships to at least one of the grain boundaries where they are growing from. Where it becomes much more difficult is now when we look at the real chemistry, and this is an independent data set now where we performed energy filtered TEM spectrum imaging at low losses so that we can follow the composition here of the metals. And what you can see with this is that at early temperatures already, we do see depletion of iron at the grain boundary. We see segregation of cobalt, nickel, and copper to the grain boundary. Manganese is a bit hard to tell. And then at higher temperatures, we see that the depletion of iron is increasing. And now we also see depletion of manganese, whereas cobalt, nickel, and copper are enriched at the grain boundary. And this is a structure we have not really seen in the ex situ analysis so far, but somehow when we're increasing the temperature a little bit further, then we start to see the precipitations that we noticed of iron and cobalt, and more or less simultaneously, we see that here also the nickel copper concentration at the boundaries is changing somewhat. And here the manganese depletion is also starting to turn around, and then only at the higher temperatures, this is really changing. And we do see the nickel manganese enrichment at the grain boundary. And I forgot the cobalt, this is typically depleting when the iron cobalt, the copper is segregated in the iron cobalt phase is formed here. Yeah, and so I think this really illustrates that we have a very complex succession of processes here. I don't want to go into the full interpretation of what we can learn from it, but just schematically, this is visualized here, the segregation from the grain boundary, the precipitate formation, and then the copper extraction from the precipitates and enrichment of the different phases. And I think this is at least some data that we now have available, trying to understand the formation of in these very complex systems. And this is something ex situ at least would need very significant statistical analysis of a large amount of data to come to any conclusion close to this. Yeah, and with this, I would like to come to the last examples that I wanted to cover. This is now looking at the mechanics of nanocrystalline films. We have been working on this for a very long time, trying to identify the different processes that are playing a role. And what I want to focus on today is really the Bouchinger effect, which has already been investigated also by a number of people, for example, Frédéric Montpieux, that saw here dislocations being emitted from this grain boundary moving across this ultra-fine grain structure, being absorbed on the other side, and then during unloading, the dislocations are moving back from this surface towards this direction, because of the local stress distribution with dislocations piled up here at this grain boundary and then released during the unloading phase. And we wanted to follow a different approach, really getting more information also to include the crystallography and doing a larger statistical analysis, so that we used the orientation mapping again with a straining setup and a push-to-pull device, essentially just acquiring an orientation map, straining a bit, acquiring to have snapshots during the loading and the unloading. And what we can see with this is to some extent the expected normal grain growth as we're straining our sample. So initially there's a high dislocation or defect density. This is driving the grain boundaries out. So it's only changing slightly. And in this case, during fracture, then this reassembled into a small angle boundary forming here in this grain. But we can also form much more complex processes. This is just in the neighborhood. And what we see is actually here the conversion of a grain with a strong orientation gradient. And when you would just look ex situ at this, then you see the transformation of this orientation gradient into a high angle boundary, where you would say this is not really anything special. But when you look at the real process behind it, then you see that actually we have, when we're straining this, more and more fragmentation, subdomain sub-angle boundary, sub-grain boundary formation, all the way to a complete fracture of this grain with new grains forming in between. And only upon relaxation with a very significant Bauschinger effect, we see that this grain is really reforming. So this gives a completely different idea of what is happening here in this system. And one way to follow this, not only on an individual basis, but to do a more statistical analysis, is to look at grain rotation maps. So this is now plotting for each grain how the rotation is changing as we're straining the sample. And one of the things you can see with this is, for example, we see typical rotations here of 60 degrees and 40 degrees. And obviously this is not a real rotation around 60 degrees, but this corresponds to twin boundary formation. And if there's one twin running through the sample, then this is a 60-degree rotation. And if there's a second twin running on an independent plane, then we end up with a region of 40-degree rotation. And you can nicely see this, for example, here in this grain, where we already had two twin boundaries. Those two twin boundaries are moving down here, and in the trail behind them, this is where they are then forming the sigma 9 boundary. And this is also a feature that we very commonly observe in high resolution TEM images of these samples. And when we now look at the small angle rotations, then this really puts very strong constraints on the sample preparation. So you need to be absolutely sure that your sample is completely planar and not bending. Otherwise, this would you would see kind of continuous gradients in your orientation maps or on the grain rotation maps. But as you can see here, my students have gotten quite good at transferring samples without any bending, and we just see individual grains rotating much more significantly than others. And this is some of the hotspots then to analyze. And we can also do this at the sub-grain level. So here's one large grain depicted where we now look at pixel-wise rotations. And what you can then see is the formation of sub-grain boundaries or small angle boundaries that are moving through the sample and to some extent are also then forming high angle boundaries. So here on the right side, you can see that a larger part of the original crystal is missing because a new high angle boundary has formed. And a bit similar, where you're looking here at this very small grain, you can nicely see how originally one single small angle boundary formed in this grain. And as we are straining the sample more and more, this boundary is moving through the grain and at some point leads to the complete rotation of the grain, clearly indicating a dislocation-driven process here. Yeah, but now we wanted to push this a little bit further and really use this to look at the Bauschinger effect in our samples. And we can see this, for example, from the mechanical response of the materials, that when we're unloading the sample, we see the elastic response would look like something like this here. And we have a very strong deviation of this unloading characteristic for the Bauschinger effect. And we followed this with grain rotation and actually then looked at a large area of the sample I think in total, a couple hundred grains that we analyzed. And when you're looking at the grain rotation here, then you can see that the average grain rotation is really quite small, only somewhere around 0.6 degrees, first going up and then going down. And this gives the statistical distribution, but you have to keep in mind here, this is actually the original, the statistical distribution of the orientation variation within each grain. And this includes our subgrain boundary. So the actual precision of the measurement is significantly higher than the error bars that we have here. And when we look at this now in a bit more detail, what you can see here is really how individual grains are responding to the deformation process. And when you're looking at the corresponding microprode stem image, then you can actually see that this is a succession, that the deformation or that some structural changes are starting here, moving through the sample up here, then slowly through this grain, and then are going up in this grain. And this is in here clearly out of plane rotations that we're seeing. And we can also then look at this at the subgrain level. And we see, for example, here again, the formation of a small angle boundary in this larger grain that is then rotating fully. And then during the unloading, again, we see a lot of orientation changes here. And these orientation changes we can interpret in terms of the geometrically necessary dislocations and actually follow a G&D density plot of our samples. And just as a warning, directly at the grain boundary, I would be very hesitant to interpret this because there the accuracy of the measurement is limited because we have overlap between the grains. But when we're a little bit away from the grain boundary, at least the relative changes do seem to work quite reliably. And when you look at this in more detail, you can quite nicely see how originally we have some G&Ds developing here. They have been spreading in this part of the grain. As we're then pulling further, it's moving on, completely filling this grain with a high G&D density and seems to then generate here this hotspot. And as we're then further deforming, the dislocations are driven out here, just piling up close to the boundary. And when we're then unloading, it's actually again something coming in from up here, pushing the dislocations further out here. And then we see again, the complete deformation of this grain, really showing very nicely, I think, how a partially reversible plastic deformation is occurring here because of this strong stress build up with all of the dislocations stuck at the grain boundary.
Mr. Kubel, we are running out of time. So, yeah.
Okay. Oh, I'm sorry.
Very interesting talk, but
I thought we had 45 minutes.
Yeah, almost there actually.
Oh, okay. Sorry, then I'm almost at the end. I'm just going to speed up this a little bit. This is actually then the last point I'm trying to make. You can then analyze this a bit more on a large scale to really statistically look at the variations. And one of the interesting points, if a coarse-grained material would be strained, then you would expect that the change in orientation of the individual grains would roughly follow, would be tilting towards the tensile axis. And this then in the inverse pole figure has been measured for aluminum. And they have seen that for different grain orientations, you get a somewhat uniform behavior in most areas. And they already speculated that deviations here are due to stresses building up at grain boundaries. And when we now do the similar analysis for our nanocrystalline materials, you can see that there is really hardly any correlation of the changes in orientation as we're loading the sample. However, what does seem to work is when we look at the loading and unloading, we typically see again this reverse behavior that I have been talking about, that we have rotation and backwards rotation because of the stress build up and release. Yeah, and so I think these are obviously all things you could only really observe with in situ microscopy. Ex situ, I don't see any chance how to get comparable information here. Yeah, and with this, I'm actually almost at the end and just wanted to make one more point that to give you an idea, when we're, oops, oh, movie doesn't want to play. When we're now using these advanced camera setups, for example, for 4D STEM, this is going to be one of the chances we have to really push the experiments. So I didn't tell you, but typically one of our orientation maps takes about 30 minutes during this training series. Whereas if we're now doing these 4D STEM measurements with a high-speed pixelated detector, where in this case we could reach actually up to 18,000 frames per second, then one of the maps that I'm showing you here, showing the magnetic field evolution, only takes 7 seconds. So with a 4D STEM setup, we're really getting towards measurement times that are, I would say, more compatible with normal in situ experiments. Yeah, and with this, I will finish and skip the summary since I'm already late, but I would like to really acknowledge the people that did the work here from my group. They are highlighted in dark, and the collaborators, in particular, Horst Hahn, Julia Ivanisenko, and Shiram Katanula, Jinsong Chang from Zhejiang University on the metallic glasses, the group of Gerhard Wilde in Münster on the metallic glasses, and Enrico Lavergne on the compositionally complex alloys. And with that, I would like to thank you for your interest and for the chance to talk here. Yeah, if there are any questions.
Yeah, thank you very much for a nice presentation. So we can invite some questions. I already saw a few chat messages. Couple of them are for you. I don't know whether you can see it. The first one is, how much temperature could be reached during HRTM characterization in 300 kilovolt electron beam microscope at higher magnification without in situ heating?
Sorry, without in situ heating or with?
I think without in situ heating. I think this is a question that reviewers also ask at times, that what is the heating due to the 300 kV?
The heating due to the electron beam.
Electron beam, yeah.
I think there, I remember some experiments that were done on cryogenic temperatures, where they put a beam on something that, where you expected to see a phase transition at 15 Kelvin, and they could not initiate this phase transformation. So I think the direct temperature change is really quite small. The other thing, which I wouldn't call temperature, is you will still have inelastic interaction, some knock-on damage, and this might activate your material and thereby trigger reactions at a different rate. But this is not really directly a temperature effect.
Okay, thank you. The next question is by Vishwanath Balakrishnan. The question is, in Bauschinger effect, how does strain reversal from tension to compression is achieved in the in situ experiments?
Sorry, it's hard to understand.
In Bauschinger effect, how the strain reversal from tension to compression is achieved in the in situ experiments?
So we're in the in the classical bulk experiment, you're first, let's say, compressing and then straining the sample, or vice versa. With thin films, this is not possible. So there, the typical analysis is simply essentially elongating it or straining it and then relaxing it again. It's not going into the opposite deformation mode. So we're just really straining the sample and releasing all of the strain. And this is enough to essentially give all of the stored dislocations a chance to react to their strain fields and then move backwards.
Okay. Other questions from the audience? Okay, I have a couple of questions because I have also done in situ straining and in situ heating during my own research. So when you do this in situ straining, I can see this view graph where you have a variation of grain sizes. So obviously, I mean, often we see that a little coarser grain size grains are more likely to deform compared to, or show more dislocation activity compared to the finer grains. So did you notice that kind of feature? Or?
Yeah, we have tried a little bit to analyze this, and to one part seems to be that when we look really at the grain boundary between the two grains, in some cases the slip plane seems to be oriented particularly badly towards each other, so that an easy transfer across the boundary is not possible. And then we do see a lot of dislocation pileup there. Whereas in other cases, the slip transfer seems to be much more easy across the boundary if they are better aligned.
Okay, so you could see the pileup formation.
Yeah, this is what you see actually here on the GND map. We do see here, for example, an increased GND density close to the boundary. And in this case, I would say they're far enough away from the boundary that it's not an artifact of the two structures overlapping.
Okay, okay. Actually, it is not, if you do just look at it in simple bright field, it is probably not visible. But when you do this kind of mapping, stain mapping, it's probably possible to see. Yeah, I mean, we have tried for a while to do bright field TEM of the dislocation motion, and with these nanocrystalline materials, you cannot really orient them very well. I mean, there's not a strong enough texture for all of the grains, and then yeah, sometimes you see some indications that is probably a dislocation moving through, but it's really difficult to interpret. Yes, yes, I felt that problem when I did 20 years ago, because that time these techniques are not available. Regarding this in-situ heating, you have done this nickel. We did work on high nickel, low zirconium alloy. Of course, zirconium content was around 40%, and nickel was 60%. So there also we had amorphous phase, and it got converted into crystalline phase around 300 after holding at 300 degrees centigrade for 10 minutes. So I figured that you have done it at a higher temperature because your material is zirconium rich. It's a zirconium rich alloy. So probably you needed a higher temperature for conversion to crystalline form. Yeah, I mean, I think this we mostly looked at the X-ray diffraction characterization. I'm just trying to get back there. And from the X-ray based analysis, I think this was at 800, around 850 kelvins when the first crystallization happened. 850 maybe. Okay. Okay. So that would be around 450 degrees roughly. Okay. 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 So temperature actually varies. So did you have to hold it for some duration at that temperature before you could see the in-situ crystallization, or it happened instantaneously? Yeah, I mean, in order to see crystallization, we did hold it for quite a while. And the only thing is that, I mean, with this, we didn't really see the crystallization we expected, but a mixture between crystallization of the zirconium oxide and then the very nickel-rich phase forming. Yeah. Okay. Sorry, somehow my computer is really. That's okay. Yeah, I will put the slides. So yeah, there you are. Yeah. Yeah, and so if we look here at the phase diagram, so here was it, yeah, 855 Kelvin when you see the first crystallization ex-situ, and then in the microscope with the oxidation, yeah, we're taking out some of the zirconium and then are shifting towards the precipitation here really of those two compounds as the main phases. Right. Thank you. So any further questions from the audience? Okay, if not, then all of us should join together to thank the speaker profusely for very nice and elaborate presentation, showing beautiful slides and many examples and in different areas. So I thank you on behalf of the organizers. I thank you profusely for accepting the invitation and making this nice presentation today. Thank you very much.
Yeah,
Give you a big hand at our place, sitting at our place. Thank you.
Yeah, thanks a lot for the invitation. It was a pleasure to be here. And yeah, looking forward to the rest of the meeting.
Yes. So.
How can I unshare? Yeah.
Yeah, Professor Kubel, please answer.
Yeah. I'm going to. Okay, now it should be finished.
We will have the last talk today.
Yeah, so it's my pleasure to introduce Dr. Ishan Ghasem, who is presently in Sweden with the Jönköping University. He has done his BSc and MSc in Material Science and Engineering from Ishan University of Technology, Iran. And after finishing his master's session, he was employed as a research assistant at Steel Institute. And after a short working experience in research institutes, in 2009, he was awarded the Singa prestigious scholarship award for PhD studies at Nanyang Technology University. After that, he has moved to Sweden, and where he's, I believe he's there still now at the Jönköping University. And he's actively active in the development of new techniques for analytical microscope studies in metallurgy using 2D, 3D, VSD, ADS, WDS, In-situ and correlative microscopy studies. And his main research interest in relationship between the microstructure and mechanical properties. And he has shown his competence in the area of alloy development. And he has also worked on high entropy alloys, microforming processes, and grain refinement techniques, heat treatment, physical and mechanical metallurgy, and finite element simulation. So with this brief introduction, I hand over to Dr. Ghasem. So please go ahead and start your presentation.
Thank you very much. Yes, I tried to make it shorter because we are running out of time, and I think everybody wants to enjoy the rest of the night in India and the rest of the day in Europe. So first of all, I need to thank our friends in India for inviting me to this interesting symposium. I've listened to some of the talks, and I really got nice inspiration and also good insight for the results that was presented. Today in my presentation, I'm going to present a selective summary of some of the work that we have been doing on in-situ tensile and cyclic testing in SEM at Jönköping University. That has been done together with, of course, my group and some of the PhD students that are working with me and the postdoc working in my group. My name is Ehsan Ghasem, Associate Professor at Jönköping University. It's written Jönköping, but in Swedish it's called Jönköping. And as you see in the map, it's in the southern part of Sweden. Here's Stockholm, capital. And it's a very beautiful city. I hope you all have the opportunity to visit this beautiful university. As you see, we are in the southern part of the second biggest lake in Sweden. That is actually around 100 kilometers long. It for us looks like a sea, but it's a very beautiful city. I'm right now in vacation, but because of this very interesting symposium, it's a pleasure to sit in my office in this building that you see on the picture, School of Engineering, Department of Materials and Manufacturing. In my group, we do specific research on alloy development, as mentioned, which in some cases have some related activities to in-situ microscopy and in-situ testing in SEM that I will today present some of the case studies. I will not go deeply through introduction. I think you are all expert in this field, and there has been many presentations as introducing the methods. So I try to basically spend most of the time on case studies related to room temperature and high temperature in-situ tensile, as well as in-situ cycling testing, sort of low cycle fatigue testing in SEM that we have been developing at the university. Well, in-situ stages, you all know they're sort of scary because they are relatively huge in the chamber in the SEM, and they're very close to a lot of detectors in this, especially if you do high temperature in situ EVSD, needs a good nerve basically to do these tests. This is the stage that we have at Jönköping University, Camrose and Weiss stage, that is produced in Germany, and has the capability of going up to 5 kilonewton tensile and or compression testing. You can do cyclic testing as well, and a lot of more capabilities. You can do high temperature up to 800 degree and compatible with EVSD configurations in the SEM. And down there you see a typical schematic of samples that we use for such tests in situ tensile. The first case study I would like to show you was a collaboration that was done with my colleagues and friends in IIT Kanpur on a Cantor alloy, high entropy alloy that you see the composition in the slide: aluminum, cobalt, chromium, iron, nickel. It's a sort of composition that has been studied extensively, and it's an interesting high entropy alloy just by changing the aluminum percentage in the composition. As some of you might know, you can change the microstructure, the fraction of phases in the microstructure from fully BCC to fully FCC, or a mixture of those. The alloy, the composition that you see on the screen, sort of atomic proportion of all elements, equimolar proportion of all elements in the composition, gives you such a structure that if you look at the phase map in the EBSD, this is before deformation, it's composed of FCC and BCC, around 22-21% FCC precipitates or phases that are if you look at the IPF map, you see that they are populated in the grain boundaries, specifically in the grains as well as the grain boundaries of the BCC. So the microstructure is made of BCC grains that you have FCC precipitates or phases in the grain and specifically at the grain boundary. This is a very special microstructure because normally, for example, in steel, in some sort of dual phase steel, we have the challenge of sigma phase, for example, forming at the grain boundary. And that is a phase that is very brittle and can cause a lot of problems. But in this case, we have FCC phase at the grain boundary of the BCC phase. And as you know, generally speaking, FCC phases are more tough and have relatively better ductility in similar composition of BCC phases. That was a unique case, and here's also an IPF map of the only FCC phase, and we looked at the misorientation angles, and we could see that there are a lot of twin similar boundaries in the FCC phase that is related to that can be correlated to the unlinked twins, and we get back to it why these unlinked twins we showed them presented here. We did in-situ testing and compatible at the same time EBSD, and here's a SEM picture of as the sample near the necking point or near the fracture, before the fracture. You see some cracks initiated at some points in the microstructure and propagated and stopped at the other side of supposedly the grain, or has been deviated at some point. If you look at the EBSD map, you see that most of these cracks have been initiated at the triple junction of the BCC grains, have been propagated until the next grain boundary and has been stopped there or been deviated at the next grain boundary. When we looked at the phase map, we found out that yes, that the next grain boundary where these cracks have been blocked or has been deviated in their route, into propagation route, the main reason is actually existence of the FCC phase that is sort of absorbing the crack propagation energy of these cracks and make a delay in their propagation or stop them from propagating anymore outside of the grain, which is a unique situation for these alloys at room temperature. So this is a lower magnification IPF map that you see. All cracks basically, they have been transgranular. There has been no crack that has been intergranular. That, as explained before, is due to existence of the relatively tougher FCC phase at the grain boundary. Yeah, high resolution EBSD maps that we got at the crack initiation point. You can see precipitates of FCC inside the BCC grain and how these cracks have been initiated at the grain boundary. You can see also the phase map. The cracks have not chosen to go across the grain boundary because, again, of the existence of the FCC phase. I mentioned the annealing twins in the sample before the formation. If you look at the curve on the right side, you see that this 60-degree peak that we had in the misorientation angle have been decreased when we deformed the material. So up to 800 megapascal, you see that it's been almost removed, and that sort of indicates that twinning, of course, is not a deformation mechanism in this material. It's more of slip deformation and then cracking in the material. So, and that is related to low stacking fault energy that we have in the FCC phase that could be related to the lower, relatively smaller grain size that we have in FCC precipitates. That is not the dominant, that is not making twinning the dominant deformation mechanism in this material at room temperature. We did the same test at high temperature, again, with my colleagues at IIT Kanpur. And we saw, yes, there is the same sort of cracking behavior, transgranular, but when we looked at the microstructure in more detail, this is near the crack, this dark area is the crack. Throughout the deformation, you see that this is the phase map, and the red dot shows you the FCC phase. And at some region, you see that the population of FCC phase increases when we deform the material. And with more investigation, found out that this can most probably related to orientation related dynamic FCC precipitation during deformation that happens in the material, specifically at higher temperature where the activation energy is lower, most possibly. And it was not what we could conclude because we looked at the GND maps and investigated more, and we found out that there is not much changes in the GND map in that area that we have recrystal or dynamic phase formation. And we sort of concluded that it's most probably not related to any defect on the material, but mostly related on the orientation. But this, of course, needs more investigation to find out what is the relationship in the orientation where we have this dynamic recrystallization or dynamic phase precipitation on the material. And the conclusion was that, of course, if we can work on these compositions and the temperature, the forming temperature, we can reach to a point that we have enough populated dynamic precipitation of FCC phase that leads to, of course, increasing the ductility of the material and improving the workability of these high entropy alloys. Another case study that I would like to show you is cast material. What I showed before, it was a wrought material. We also looked at the in-situ testing of aluminum 10 silicon cast alloy. It's a very typical cast alloy that is used in many applications, including some part of aerospace and automotive industry and household and such. You see the result of the IPF map, typical IPF map in this material, and then you can see very clearly the dendritic structure in the ASCA structure of these alloys. What was interesting, and of course is sort of known, is that we could see slip bands forming in the dendrites, which is composed of aluminum matrix, and in the eutectic area in between, you see that there was no slip band, or there was basically a very low plastic deformation of the material. That first of all shows that and proves the theory that, of course, in order to increase the strength and ductility of these materials, what we need to focus on is improving the mechanical properties of the matrix, the dendrite. If we can focus on that and improve that and delay the slip formation and cracking in the dendrite, we can improve the mechanical properties of these material. If you look at this picture in the middle, you see that the crack is sort of initiated and propagated in the main body of the dendrite. So that's another conclusion that we could find, that as I show in the next slide, this is again near the cracking area or near the fracture area. Overimposed, you see the EBSD map that shows you basically the grain structure. So in the SEM, you can see the dendritic structure, and EBSD can show you the grain structure. And the research question was, which one is more important when we have cracking in the material? Is it the grain? Does grain boundary plays any role on crack propagation in these cast alloys? And we could find out that basically most of these cracks that are starting to form, as you see, they are forming in the main body of the dendrites in the material, and we had almost no crack going along the grain boundary. So all the cracks in the material were transgranular. You can see also slip bands in the material in 2 different grains that is proven by the IPF map. That shows basically conclusion was that grain boundaries play very minor effect in the cast material. Is this secondary dendrite arm spacing, or basically the size of dendrites in the cast structure, that dominates how the material will fracture and how the mechanical properties would be. Before I show the next case study, a challenge that we had in high temperature in-situ that I think most of you know is heating in this stage. Although we have vacuum and there's less convection heating, but there's anyhow heating in the material. This is a result that I took from my friend René de Cloes, application specialist in EDAX. And he took a picture of the camera, EBSD camera. This is the room temperature test, and this is the high temperature test on the same material with the same SEM parameters. And as you see, we have radiation on the phosphorus screen that can look scary if you, especially you do high temperature in-situ testing for a long time in the SEM. But he did an interesting test also on the phosphorus screen, and so that this is the curve that is actually a very old result. That he kept the material in the SEM, I think, for a few hours, up to 1000 degrees centigrade, and this is the curve for 1000. And as you see, even if you get very close to the phosphorus screen, you see that the temperature does not go above, let's say, 150, 200 degree after a few hours of exposure at this temperature. So there's basically not much scary temperature on the detector, but it needs special skill to do these measurements as quick as possible to avoid any damage to other type of detectors like EDS and other detectors that have polymeric material in them, as you know. Besides the in-situ tensile test, we also developed some grippers to do in-situ cycling tests on the same stage that we had from Kamers and Weiss. You see these grips that we developed ourselves, and we use this miniaturized side dimension of the CT sample in order to look at the crack propagation in the material in a sort of semi, you can call it low cycle fatigue loading on the material. We cannot do high cycle fatigue because, as you know, this stage is the loading is applied by gears, mechanical gears. It's not a piezo motors, and that's why the compensation for the load is slow. The loading is slow. It's not as high as we could have or we would like to have for high cycle fatigue. Anyhow, the cyclic fatigue, we developed it in a way that this is the in a way that first of all is applicable to any kind of material. The example you see here is for cast iron that we did for the first time in 2018. And here you see the CT sample, and if you look at the near the notch area, that's the SEM image. And if you zoom in the real notch, the 0 degree on the notch, you see that there are some spackles on the material. We're developing these spackles on the material using the FIB with very fine dots with very shallow depths, so in a way that does not affect the crack initiation propagation. And we did it with the purpose of following the deformation of the material, the strain on the material. The reason was that we wanted to follow, to monitor the strain mapping while we do the in-situ cyclic testing in order to predict how the cracking would propagate on the material and what are the effect of different phases and different microstructural features on crack initiation propagation during cyclic loading. You see one example here using digital image correlation and following the movement of these speckles during the in-situ testing. We could follow the high, we could sort of monitor the high points, high strain points on the microstructure, and predict where are the weakest points in the microstructure in order to develop the material further for cyclic or fatigue properties. This is one highlighted result that I wanted to show. There are so many other results that I could show later. I can send you the papers also if you're interested. But anyhow, on the left side, you see the DIC, the experimental result. On the right side, you see, in the middle, you see the overimposed finite element simulation that we did using Abacus. And on the right side, you see basically the typical optical microscope image. And as you can see, we have, wherever we have close vicinity of these graphite particles in the cast iron, we could have, we saw very high concentration of strain on the microstructure, as well as the sharp tips that we had on the graphite, which was sort of expected or could be predicted and estimated using theories, but it was not seen experimentally. We could visualize it. And the other thing was that there was a pretty good correlation, at least qualitatively, between the experimental work and simulation work. We're still working on these methods to improve both the experimental work as well as the simulation to get even better fitting. I think here I have a video to show you how it works. At the bottom here, you see the notch of the material. It's a cast iron material, as I mentioned. And you see at 0 degree, a crack starts to propagate. And you might think that these are irregular shape of graphites that are normally undesired in cast iron, in nodular cast iron. And you might think that the crack would propagate from this one. But you see another crack is initiating in a 45 degree. And want to highlight that we have a couple of porosities here that show that there are empty spaces on the material under the surface that might play nasty a bit, which they do. I try to fast forward this one. So as you see, this, by the way, real-time speed. This crack is blunted here in this area, and the area where we had porosities is the area that is opening up, and the final cracking happens. So that shows you where shows us where we have to focus in order to develop these material for higher fatigue lifetime. The next case study, I think it's probably the last one, is to show you is aluminum silicon alloys again that we did cyclic testing this time. And you see the notch area overimposed on the color map. You see the IPF map that we took on from the EBSD before the deformation in order to see where the grain boundaries are and how cracking reacts on the grain boundaries. Again, this is a cast material, so we have the secondary dendrite iron spacing, the dendritic structure as well. And yeah, you see the cracking after 700 cycles. Of course, you can change the number of cycles with respect to cracking by changing the delta K and R value in the fatigue testing. But based on these parameters that we had after 700 cycles, we got this big crack that EDS maps. These at the bottom, you see the EDS maps, and the green area shows you the dendritic, the eutectic structure. So whatever is not green is the dendritic aluminum matrix. And it was clear that the dendritic area, as also mentioned in the static tensile testing, is a strong phase in the material, and the crack does not follow the dendrite structure. It's sort of transdendritic cracking. This is for another material, same material, sorry, but for other a different type of fatigue parameters. And I think I should have another movie here. Just to show you also that it's possible to record the movies while we do the tests. These are type of movies that I personally like a lot. It's sort of hypnotizing to look at it, or very good to look at it before sleep, makes you sleep very well. But very interesting, you can see the material being very highly plastically deformed at the crack tip before the fracture. And of course, you can quantify it, as I mentioned, using the digital image correlation and the speckle patterns that we have developed on the material. And my students have been able to using DIC, just to show you how DIC works and some results from DIC. The pictures that I show you on the left side is where we have the tensile loading in the cycling test, so the maximum opening of the notch. And on the right side, you have the compressive load, where we have the maximum closure of the notch in the cycling loading. And you can see that the crack sort of follows more or less the high concentration strain areas that we predicted experimentally using DIC. I had a lot more to present, but we do mostly applied research at Jönköping University together with companies, and unfortunately, with most of these projects, we have strong NDAs, and therefore my hands are tied in order to show the results. But I hope with these results, we got some taste of what the possibilities are to do in-situ tensile and cyclic testing. These are very general conclusions, but as you all know, these are very powerful tools and very versatile that can reveal many interesting phenomena experimentally for almost any kind of material. And they're very useful to verify the related theoretical models that were not possible to do before, or modify the related theories. The only limitation that I can name, or the main limitation that I can name for these in-situ tensile cycling testing in the SEM is that the observations are mostly two-dimensional. There could be nasty things happening in the material in 3D that we are not able to see. But when it comes to, specifically when it comes to single phase material or wrought alloys, most of the things start from the surface of the material, where you don't have secondary phases. So very powerful tool for those materials. For multi-phase materials, also powerful, but as I said, things could happen under the surface that you don't observe first. Before finishing, of course, I need to acknowledge the funding agencies that we had in Sweden that made it possible for us to do these side collaboration, side research, and my colleagues, and of course my group members at Jönköping University, as well as my collaborators in India, especially my friends Professor Biswas and Professor Gurao at IIT Kanpur. Thank you very much.
Thank you very much, Dr. Ehsan Ali, Dr. Ehsan Ghasem Ali. So for this nice presentation, we need some other questions from the audience. Because the videos and the pictures that he has shown are very interesting and very thought-provoking.
We are doing actually the same thing we got some research question from hospital in Jönköping. They're developing materials for amalgam for the dentistry. Okay. And they want to see how these materials crack, because some of them are very beta, some of them are not. And also we do the same thing on wood material. There's a company here developing, working for IKEA, as you know, this furniture company, Swedish furniture company, and they're developing new wood material, and they want to see how this wood cracks. So there are, as I said, it's a method that is versatile and applicable to any kind of material. That makes it interesting.
Yeah, and the picture that you showed about the plate graphite cast iron and failure that happened because of porosity underneath. That was very interesting, and obviously one would expect that it would start at the interface between graphite flake and the matrix, but it did at some place, but it is also happening in the matrix. So there is a graphite flake beneath, so that is probably not visible. And then after it fails, and one can look at the crack profile and maybe then build up the event, that how it happened.
My student, my PhD student, has done the same test in using synchrotron to look at these cyclic behavior in 3D with, of course, not this type of geometry of samples, but different geometry, the normal fatigue testing. And we are looking at the volumetric digital correlation in order to see what happens inside the material as well. So that is the work that is ongoing.
So, are there any further questions from the audience right now? Okay, if not, then let us once again thank Dr. Ehsan Ali, Ehsan Ghasem Ali. Sorry, I often get your name wrong. The similar name is there. One of my friends of similar name, so excuse me for that. Thank you very much for accepting the invitation and being.
Thanks for the invitation.
And very nice presentation you made, which we all enjoyed. And so we all give you a big hand from our side.
Thank you.
I hope to see you again at some other conference. Thank you very much.
Thank you.
Thank you, Ehsan, for a nice talk. Although we are a little bit,
Thank you.
Late in our schedule, but I'd like to thank Professor Rahul Mitra for nicely managing the session and at least making it nice and vivid. So with this, we come to the conclusion of the first day. We're going to start tomorrow at 9 a.m. With a talk from Professor Chun Lu. So please join us back. Tomorrow we'll have 4 talks in the morning, followed by industry presentations, and then again 4 talks in the evening. So I hope to see you back, all of you. Anything else you want to say, Chandrasekhar, or anybody else?
Yeah, thank you all for joining, and thank you, Rahulda, for chairing the session. Thank you all the speakers for managing the time, and also some of you were odd times, like Eric started very early morning, and also David was very late. So thank you all for coming together and having such a nice discussion and such a nice meeting. Thank you.
It's a very nice conference and excellent speakers you have got, excellent panel discussion. So thank you for organizing this, taking on the trouble. Thank you for that.
Okay, good night, good day, or good evening.
Good
By
night.
then, for today.